Good morning, everyone, and welcome to MPLR of 2020. I hope you can hear me. If somebody can validate that they can hear me. Okay, perfect. Thank you, Stefan. So I will start with a welcome presentation, and then we will continue with our first keynote and then the discussions, and we will describe in the process how you can ask questions and how to organize the whole conference. So I hope you can see my screen. So welcome. On behalf of Stefan and myself, I would like to welcome you to MPLR 2020, which was supposed to take place in Manchester, but due to known reasons, it will be virtual. So to my knowledge, this is the first instance that MPLR, it's virtual. We are running the 17th incarnation of MPLR and the previous conferences that were transitioned to MPLR. And although we are a bit sad that we will not see each other in person, we really appreciate joining our virtual conference, and we hope next year or in the future we can see each other in Manchester or elsewhere. So regarding the program, this year we received 11 submissions, and from those 11, 4 were accepted as regular papers, and 4 as work in progress papers. And 2 keynotes have been organized, one by Steve Blackburn regarding garbage collection and the implementation, the innovation, the performance, and the whole history of garbage collection, and from Martin Mas regarding the hardware support for managed languages and how these ideas that have been iterated in the past, they may be most relevant now. We will be running 3 sessions, one about concurrency, correctness, and consistency, one about security, and of course, performance. Please visit the program at the MPLR2020.cs Manchester SEUK, so you can have all the time schedules, and so you know which sessions you would like to attend. So as you see in our program, or probably you have read in the announcements we sent to all attendees, the presentations will be shown as pre-recorded videos. And after the videos end, then you'll have the opportunity to ask questions to the authors. So you have 2 ways of asking your questions. First, you can raise your hand within Zoom, and then I will pass you the microphone so you can directly ask a question, or you can ask a question on the corresponding Slack channel of the paper, and the chair of each session will ask the question on from your behalf to the authors. And excluding the Q&A sessions at the end of each paper, we have organized some sort of a virtual hallway in Slack where during our coffee breaks, you can join the Slack channel, and in there, there are separate, let's say, Zoom channels regarding each paper, or you can initiate discussions one-to-one, and then by doing /Zoom, there's a plugin for Zoom, for Slack, where you can actually start very quickly in a one-to-one Zoom call with anyone. So when we have those coffee breaks, please, if you like, head on our virtual hallway in Slack and start asking questions about the papers on the separate channels, or initiate your own discussions as you prefer, or of course you can use Slack. So the Slack channel, the links are both on the web page, and each paper in the program has a direct link to the specific Slack channel of each paper. So I would like to thank very much, of course, Stefan, for the hard work, and the whole program committee for organizing the peer review process in a timely manner and with great feedback. And of course, would like to thank Juan and Thanos, who were part of our local organization committee and helped with organizing and testing our virtual infrastructure. And of course, I would like to thank our sponsors that sponsored the MPLR and helped us organize the conference to the best of our abilities. The University of Manchester, the Horizon 2020 E2 Data Project, ARM, and the KTM Innovation. So that was the end of my presentation. If you have any questions regarding the technicalities of how to ask questions, please let me know now. And if you don't have any questions, we can start with our first keynote from Steve Blackburn. Just to iterate one more time, you have two ways to ask your questions. The first one is by raising hand. So I'm having an overview of the raising hand, so I can unmute and allow to ask questions. And of course, we have the Slack channel where it's moderated and we can relay your questions for you. So I will stop sharing my presentation and I will transition to our first keynote.
Hi, I'm Steve Blackburn. It's a real pleasure to be here, and I want to start by thanking Stefan and Christos for inviting me to give this talk. And before we go any further, I want to introduce you to an Australian tradition that when we give a talk, we acknowledge the people on whose land we're giving the talk. And I know this is virtual, and I know that you're going to be scattered all around the world, and I know that I should be in Manchester, England, but COVID being COVID, I'm actually here in my home in Canberra, Australia, and I want to acknowledge the people who have lived here for thousands of years. And this rock painting behind me right here is an example of their history that goes back in this very place thousands of years. These rock paintings are in the hills just outside of the city, and I can actually see those hills and where those rock paintings are from the balcony of my house. And this is a reminder of the thousands and thousands, or 25,000 year long history at least, of the people who've inhabited this land before us. And so I just wanted to acknowledge that before I start my talk and introduce you all to an Australian tradition, which I think is a good one. So here I am. I'm in a workshop apparently, and I'm going to talk to you about toolkits. And specifically, I want to talk to you about MMTK, which is a toolkit that I've played a part in developing. And I'm going to tell you a little bit about why it was developed and the history through which it got developed. And I'm hoping that through doing that, you're going to learn a little bit about the technology of garbage collection, but also about research, the way research happens, and about the social dimension to building a system like this. So before we go any further, I'm here with my friends, the horse and the garbage collector guys, and what they're doing is they're collecting garbage. And I put this slide up here to remind people that garbage collection actually is, in computer science terms, a pretty ancient technology. McCarthy and Collins published their famous papers in 1960, and we've been working on it ever since. Some people might say, hey, it's such a mature area. What's interesting to study there? Well, one of the fascinating things about garbage collection is that it depends so much on the language and on the underlying architecture and on the demands of the users that they place on that language. And therefore, it is something that is very sensitive to the context it's in. And that context is changing and has changed radically from the days when McCarthy and Collins first built garbage collectors. So, yes, they built garbage collectors and they solved some basic problems way back then. And other greats of computer science, people like Dijkstra and Steele, and these people have contributed mightily to the development of garbage collection. But fortunately for us, there's still much, much, much more work to be done. And that's because garbage collection is finding itself in new places. It's finding itself in our phones, of course, which would be unheard of to the likes of Collins and McCarthy. And it's finding itself on servers, in games, in all sorts of places. And as it does this, it places new challenges and creates new challenges for us as researchers, either in academia or in industry, to make our garbage collectors perform better. I'm going to start by just saying a little bit about garbage collection and security. Now, I know with the MPLR audience, I'm to a fair extent preaching to the choir here when I say that memory-safe languages are a good idea from a security standpoint. They avoid use after free bugs because they have garbage collection, so you're not going to free something that might still get used. And they also avoid buffer overflows because they've got checks, balance checks and so forth. So these are some of the great things about memory-safe languages. However, there's an assumption here, and that is that we've implemented the memory-safe language safely. And that's part of what I want to talk about today. And if we look, we can very quickly find there are more than one example of serious security issues that are due to problems in the implementation of the garbage collector. So we've got a secure language, but the implementation may not necessarily be secure. And of course, this gets more troubling and more difficult as our garbage collectors are more complex and as our hardware gets more complex. So can we build more secure GCs? I think this is a really interesting question. I don't have any great answers to that just yet, but I think it's a very, very interesting question. I think that's one direction that my research is currently heading towards. I saw an interesting talk this year. In fact, it was at the start of this year, where someone made the claim, the very strong claim, that performance is the enemy of security. Performance is the enemy of security. And the argument they make goes something like this. Performance begets complexity. If you want something to perform well, it's going to be complex. And once something's complex, then you have a lack of understanding. And a lack of understanding lends itself to insecurity. Therefore, so the reasoning goes, performance leads to insecurity. Now, if you look at something high performance and complex, like this jet engine here, you get the sense that, yes, when you want to engineer something for performance, very often it's hard to do things without complexity. There's a lot of complexity here. And it's easy to get overwhelmed by that complexity. And in fact, if we go and take a look at the source code for garbage collectors in 3 of the well-known runtimes today, on the left there you've got V8, in the center you've got OpenJDK, and on the right there you've got .NET, you'll see real indicators of just how complex they are. If you look at V8 there, you'll see we've opened up the heap folder there, and you can see some of just the very beginnings of the code that sits in the heap folder, which is where the garbage collectors are. And so just a quick glance at that gives you a sense that the garbage collector, which lives in this folder here, is not a simple creature. And in the middle there, we've got G1, which is one of the garbage collectors that lives inside of Hotspot, one of the most mature ones. And again, only some part of the files in that folder are visible in this screenshot, and you get a sense of just how complex the G1 collector is. And then finally on the right there, we look at .NET, and we see .NET, in fact, it's just one file there, which is the gc.cpp, and GitHub won't show us the contents of the file because it says that the file's too big. It's a very, very big file. It's a very, very complex thing. So again, I just want to impress upon you, here we have 3 excellent examples of high performance, very carefully engineered pieces of software that are undeniably complex, which would tend to lead to support the argument that performance is the enemy. However, I want to challenge that. Now, I think most of us would agree that complexity leads to a lack of understanding. Almost by definition, complexity, that's almost a matter of definition. And similarly, lack of understanding will lead to insecurity. I think that's pretty uncontroversial. But I want to challenge the first question, first statement that says that performance begets complexity. I'm not sure I buy that. And I want to make it a case to you right now that that may not be so. And I want to do it by invoking Fred Brooks. Now, Fred Brooks talked about essential complexity and accidental complexity. Essential complexity and accidental complexity. And the idea is this. It's a really nice idea, and it's a very important idea if you're building complex software like this. And that is, when you're trying to solve a problem that is complex, such as building a jet engine for an airliner, or building a garbage collector for an industrial strength system that's going to be under significant load and run on very complex hardware. When you're building a system that is complex like that, the software, the solution, will have a level of essential complexity. That is a consequence of the complexity of the problem. So there's an essential level of complexity in the problem itself. However, most software systems add to that a significant amount of what Fred Brooks calls accidental complexity. And accidental complexity is where we have the problem. So none of us who know anything about garbage collection would suggest that a garbage collector is anything simple. Okay, a realistic industrial strength garbage collector is not going to be simple. However, my suggestion is that the way we build garbage collectors is often riddled with accidental complexity. There's a lot more complexity there than we need. I'm going to go further and suggest sometimes that's an artifact of the choice of language in which we implement the garbage collector. So the statement that I heard at the start of the year was the performance is the enemy of security. And I would argue, in fact, complexity is the enemy of security, and complexity is the enemy of performance. And again, we go back and look at this and we can see once more that we've got this very, very complex systems. And what I want to point out though, is that these systems, although they are very, very impressive systems, they are not ones that change very fast. And in fact, the time it took from the G1 paper to being published to being the default collector was very, very considerable. And these things are remarkably stable, which of course is a good thing. But also, we have not seen a lot of innovation in each one of these things. I'm going to say more about that later. But I want to put it to you that sometimes what happens is you design something very good, very interesting, like the G1 collector or like the collector in V8. And then you engineer it like this and find yourself in a position where it's very hard to move forward. And so what you tend to find is you're at a local minima. And it's very hard to escape that local minima because of the inertia generated by the complexity of the software you've created to solve your problem. So I saw this a while back. Understanding the JDK's new super fast garbage collectors. And it talks about ZGC, Shenandoah, and improvements to G1. And of course, there's also the Azul collectors. What struck me here, though, is the new super fast garbage collectors. They are fast collectors. They're impressive collectors. But they're not particularly new. Each one of these collectors has made minor changes to themselves over time. So, and not only that, they have their roots in some key ideas that go all the way back to Lang and DuPont, which is the algorithm on which the G1 algorithm owes its heritage. Okay, so there's some fundamental ideas here which actually haven't changed very much over time. Now, that in itself is not a problem because it's entirely plausible that this fundamental idea and the fundamental ideas behind G1 and the ones that were then refined in the C4 collector and in Shenandoah and in ZGC, those ideas, the path they hold in common are about the way the heap is structured, and maybe that heap structuring is fundamentally the right way to build GCs. And so we're going to see this heap structure repeated again and again into the future. The alternative point of view, though, is that we find it very hard to be innovative on a grand scale because of the inertia created by the complexity of our software. And I'm going to suggest to you that's part of the problem we have here. And the similarity between these algorithms, although they have a lot of innovation at the mechanical level, there's no question about that, the similarity, the underlying similarity between these algorithms, I think is striking, and I think it says a lot about the difficulty of doing wholesale innovation and really creative work in industrial garbage collectors. So now I'm going to move on to a different topic. I'm going to talk about the memory management toolkit, which is something I helped develop with Catherine McKinley and Perry Chang over a period of years. And so at this point, I'm going to talk about the history of that project, how we got to there, and what it gave us. The story starts in Amherst, Massachusetts, in the fall of 1999. In fact, it's in October of 1999. So 21 years ago. And I just arrived as a new postdoc at UMass. And at that time, I had, in fact, there's a backstory here which is quite interesting as well. I had visited the campus, I think about a year before, and to see if I wanted to do a postdoc there, and to also check out options for my wife who was also going to do a postdoc. And I visited that campus, and the day that I was there was a talk being given by from IBM Research. They had this thing called the IBM Research Day, and they came to UMass, and there was a person there called Vivek Sarkar who was talking about a new VM they were developing in IBM Research, which was extremely interesting. It was a VM targeted at high-performance servers, highly scalable VM, And one of the interesting quirks about this VM is that the VM was for Java, but it was also written in Java. And later on, this VM would come up again in this trajectory of the story I'm going to tell you. But I found it very, very interesting that just by chance, the first I heard of it was on the day that I visited this campus to test out whether or not I should be doing a postdoc here. And I decided I would do a postdoc here. And when I arrived, I soon found myself working with Elliot Moss, and Catherine McKinley. Catherine at that point was on sabbatical at the University of Texas. Elliot was there, and I was working with Elliot on a VM he was building. Now, you might ask yourself, why was Elliot building a JVM? That sounds like an expensive thing to do. Well, you're absolutely right. It is an expensive thing to do. However, at that time, there were no open source JVMs available, at least not ones that were performant enough that you could do serious research in them. And so Elliot had set about, with his students, building a new JVM that would allow them to do high-performance Java research. And my job as a new postdoc was to look at porting that VM to the alpha. And I can still vividly remember, I think it was my very first day sitting down in that lab, having been introduced to the students and explained to them my background in systems programming and so forth. And one of the students, one of the newer students coming up to me and saying that they had a bug. And I said, what's the bug? And they said, the compiler's broken. And I thought, okay, I'll come and have a look. And yes, indeed, GCC had segfaulted. Why had it segfaulted? Well, it had segfaulted because they were using macros, which is what you do when you're writing C code. They were using macros to get performance in this VM, and the depth of the macro nesting had blown some internal limit in GCC, and it caused the compiler to crash. It took a while to debug, but that was the first time I'd ever seen GCC crash. And that made me think a little bit about the way we were building our VMs. And we felt compelled to build it that way because we needed the performance. Anyway, let me move on to another part of the story, which takes us closer to MMTK. Right at the time that I arrived, Upsala was on in Denver, and just a few weeks later. And Darko Stefanovic, who you can see this lovely photograph of him there. Darko, I don't know when that photograph, I think he's skiing. Darko was a PhD student in the lab, and he'd just finished. And he'd done some really remarkable research, and it was on the design of GC algorithms. But what's interesting about it, and perhaps surprising for younger folks, is that the way he'd done it was that he'd generated traces of real programs running on a VM, and he'd done that as an intern at Sun Labs. And he built these traces. Then he'd gone back to the university with those traces, and in the university, he'd built models for the performance of things like the tracing loop, the write barriers, and things like that. And then he was able to design new GC algorithms and estimate their performance using these models, these performance models, and the traces that he'd gathered. Anyway, I was sitting in the lab one day, and I got a phone call from Catherine. And Darko had just given his talk in Denver, and she was calling me from Denver, and said that asked me if I was interested in working on a new JVM. And what had happened was, at the end of Darko's talk, someone from IBM Research, that's Mark Wegman, had approached Catherine and had asked Catherine why it was that Darko was using a model of GC performance and why he wasn't using a JVM. And the answer was very simple. He didn't have access to a performant JVM because they weren't open source. The ones at IBM and at Sun Labs were all closed source. And the only time he could get access to it was when he was an intern there. So, and Mark said, well, actually, we're about to release and make available via open source a new JVM. It's called Jalapeno. It's Java and Java. And of course, that was the VM that I'd heard Vivek speak about a year earlier. And Mark asked Catherine if she was interested, and Catherine said, of course. And that phone call, of course, was one that changed the course of my career, because I responded to Catherine with excitement, said, yes, I absolutely want to follow that. And sure enough, before too long, I was down at Yorktown as a temporary IBM employee doing the first port with my student, John Zigman, doing my first port of GraalVM to Linux so that we could take it back to the lab and we could accelerate the process of open sourcing it. And so it was that I started working with what was then called Jalapeno, which later became known as GraalVM. And the first thing I did was look at the garbage collector, because we're in the lab. Elliot and Catherine and I were all working on garbage collection, and that was my focus. And so the question was, can we do our garbage collection research in there? Well, at the time, in that initial release of, well, it wasn't actually a release, in that repository, there were garbage collectors there. There were a handful of them, but each one of them was a monolithic instance, and they were literally a single source file. They were in Java, because of all of Jalapeno was in Java. And, but they were written in a fully static style. So they were essentially written in the style of a C program. There was no object orientation, and, so they were monoliths. And so the question was, can we do things, more flexibly, more generally than that? And I set about, with Catherine and Elliot, designing a new toolkit, which, we started calling GCTK. But not long late after that, we had meetings with the folks at IBM, and, started collaborating with Perry Chang. And Catherine and Perry and I embarked on building a new toolkit, which we called MMTK. And this would be the thing that I subsequently spent a large part of my research career working on. And we did a number of interesting things in building that. But I think perhaps the most interesting one was that I remember Perry as being very determined that we should have faith in our colleagues who built the runtime, and in particular in Dave Grove and the other folks working on the compiler, that we should assume that any code that we wrote in idiomatic Java would be appropriately optimized. And therefore, we should build our GC toolkit as far as possible using natural idiomatic Java, which was in opposition to the approach that had been taken previously, where they said, okay, we're going to write this as if it's C code because we don't know what the compiler is going to do with it. And so this approach and the idea that, well, if the compiler doesn't do the right job, then we'll get Dave to fix the compiler, or we'll fix it ourselves, or if all else fails, we'll write the code a different way. But that'll be our path of last resort. And so it was, we built MMTK and tried very, very hard as we did so to build it in as natural way as possible in terms of the coding style. And so what did we end up with? Well, it was written in a high-level language. It was a fully static dialect of Java. The reason why it was fully static is because we could not call new. We couldn't call new because you'd go into infinite regress if you called new inside of a metacircular Java garbage collector. But we apart from not being able to call new, we tried to use the language as fully as we could. And in one of the other things we did was make use of Java's strong typing. And we introduced special types to help us do things like identify an address. So we had an address type, which is roughly a void star, an object reference, which was guaranteed to point to the start of an object, and so forth. And we used the type system to help us debug the code and help us gain confidence that our code was correct. The other thing we did was we made very heavy use of assertions. The code was very modular, so we made a great deal of reuse of code. So wherever possible, things like an allocator. So you had an allocator, we had a reference counter collector and a mark sweep collector. They both use the same free list allocator. So we reused the code that did the free list allocation for both of our collectors. Bump pointer allocators used by many different collectors. Things like the work queues and so forth used by many different collectors. All those things, those mechanisms, we optimized those as far as we could and reused them as much as we could when we built new GCs, which meant that the code that was dedicated to actually writing the GCs was actually quite succinct. And we built a lot of debugging features in. So we had things like what we call the sanity collector, which was a ground truth collector, which we had a lot of confidence in, which would work on the side if it was enabled. And it would allow us to check the liveness of anything as reported by our new GC we're developing, and check that against the sanity GC, which we regarded as a ground truth. And that was extremely useful as well. When we finished building MMTK, we wrote a paper. We actually submitted the paper. It was a very big paper. We submitted it to UPSLA, and we're very disappointed that it got rejected from UPSLA. But there was a silver lining on the cloud, because one of the reviewers said, what you really need to do is split your paper in half and have one half be about the software engineering this system and the other half the analysis you did with your system. So we did that, and we wrote this paper here, which we submitted to ICSI. And this paper here simply looks at how we engineered a high-performance garbage collection framework using Java. which at the time was considered a little bit surprising because people didn't think you could use Java to build something as performant as that was doing low level systems programming. There's some interesting results in there. This is an example of one of the results in there. This table here reports a bunch of software engineering metrics with respect to two different versions of the original IBM collectors. We call them here the Watson 2.0 and the Watson 2.2. And you can see there are 4 collectors there, the semi-space mark sweep, generational copying, and generational mark sweep. And then we replicated those in MMTK. We built the exact same 4. But one thing you'll notice if you've got sharp eyes, there's a 5th row there for MMTK, and that's generational, because what we've done there is we've factored out the elements that are common to the generational copying collector and the generational mark sweep collector in a separate class called generational. And you'll see here the numbers of non-comment source code lines is roughly half. Even when you take into account that extra generational file. So we've simplified it significantly, and that is after they had simplified. They did a lot of refactoring. The code at Watson had been developed by professional staff engineers who'd built a lot of production code, and but they did do a lot of refactoring between 2.0 and 2.2, and you can see here that even with that refactoring in place, the MMTK code was substantially simpler. And over on the right here, you see another software engineering metric, which is the cyclomatic complexity metric. And again, you can see that it's nearly twice half the complexity of the Watson code. So that's one example of what we did. So we're building a system which, according to software engineering metrics, is significantly simpler. But we managed to do this without sacrificing performance. And if you look at this graph here, you'll see on the y-axis, you've got time, and on the x-axis, you've got heap size. So we're adjusting the heap size and measuring the performance. And the dark icons are the new MMTK collectors, and the hollow ones are the Watson ones. And I notice here there's actually a typo. We've called it JMTK. That's because for a short while we were calling it JMTK instead of MMTK, J standing for Java. And somehow or other that slipped through the checking in the paper. But anyway, this is straight out of the paper. But what you'll see here is that if you look at those circles, the hollow circles and the dark circles, you can see that even though we've got substantially simpler code by objective measures, it's also performing significantly better. And likewise with the semi-space collector, which is the hollow squares and the filled-in squares, there's a significant performance gap between our new simpler collectors and the original ones. Why am I showing you this? I want to remind you of the statement earlier about performance and complexity. I'm arguing here, I'm trying to use this as a concrete counterpoint, that here we have something which is significantly simpler by objective measures. It's roughly half the complexity, and yet it's performing significantly better. And these are the same algorithms. We've got semi-space and mark sweep. They've got the classic algorithms. We're performing substantially better. So I'm trying to make the case here that particularly when you're building something like a garbage collection toolkit, you can make things substantially simpler and yet not sacrifice performance. The other thing we did was write the second paper, which we sent to SymJEx, which 10 years later won the Test of Time award there, and where we went and use the framework to do a lot of analysis. And that was actually a lot of fun. And we found out all kinds of things there that until that point had been often subject to, essentially folklore. And we're able to concretely measure them because we could compare algorithms, one algorithm with another, holding everything else constant, holding the compiler constant, holding the whole of the runtime constant, holding constant even the lower level mechanisms of the GC. So that allowed us to actually compare the algorithms. And we could do things like look at the locality difference between a mark sweep collector and a semi-space collector, just for example. And this graph here is one of the more fun ones in the paper. And you see here all 6 collectors we had there. We've got the semi-space, mark sweep, and reference counting, and the 3 generational counterparts. And the only thing I want to highlight here is this interesting point that you see between the semi-space and mark sweep. You see a crossover when the heap size gets to a particular size, and you see here when the heap size is small, it becomes more worthwhile to have a mark sweep collector, which is the circles, than to have the semi-space collector, which is the squares. But it's a crossover because once the heap size is bigger, the space inefficiency of semi-space matters less, And what matters more is the fact that semispace has better locality. And the difference is actually fairly significant. But what's interesting is that if you look across these three different microarchitectures, over here we've got the Pentium 4. This was a long time ago. In the middle, we've got an AMD Athlon. On the right, we've got an IBM PowerPC. You'll see that this point shifts. So it's a microarchitecturally dependent point because it depends on how locality affects this particular microarchitecture. So I found that quite interesting. And that's the sort of thing we could do once we had a framework where everything was held constant except these high-level algorithms. It allowed us to do this sort of apples-to-apples comparison, which gave us a lot of new insights into how we might build garbage collectors. We went on and did a lot more like that. And I'd classify this work here as what I would call discovery, which is essentially exploring not new algorithms, but understanding much better how existing algorithms or new mechanisms might make existing algorithms perform better. And we published a lot of things, looking at things like how the performance of write barriers works, how different write barriers perform, how zeroing works. There's a great paper in that stack there from Si Yang on the performance overheads associated with zeroing. We did a lot of studies like this, and MMTK allowed us to do that quickly and allowed us to do apples to apples comparisons. And in doing so, it often gave us insights into how we might build new algorithms. So this is one of the real benefits of a framework like MMTK, is that we could do studies like this, and we did a lot of such studies, and I think they help the community. We're also, of course, able to be creative. And here there are a few examples of new algorithms we've built, completely new algorithms that we built inside of MMTK, which changed the performance in interesting and creative ways. And we're able to build them surprisingly quickly because of the modularity of the MMTK framework. But the question is, how much impact did this actually all have? And as researchers, whether you're an academic or an industrial researcher, you probably care most ultimately about how much impact you're having. And this is where we all need to stop and think for a bit. And it's not always as good a story as I would like. And in fact, if we look at all that work I just showed you, and I reflect on where it's really had a direct impact, I can see just two language implementations that have directly taken on garbage collection algorithms that we developed. And that's the Scala Native and Inco, which both use IMIX as the garbage collector, which is fantastic. But also, I think, to be totally honest with you, that's a little disappointing. For all that work, I might have expected to have had more impact on the way production garbage collectors work. And so the question is, why did we not have more impact than just this? And that's what I'm going to reflect on now, is what are the barriers to impact? First, and perhaps most important, credibility. Work needs to be done within an industrial strength runtime for it to be considered credible, both by our fellow academic researchers, but most crucially by our industrial colleagues. If we're not doing our work in an industrially credible setting, then we won't gain the attention of people who might want to transfer it. Now, I can dismiss it as being something that is curious, interesting perhaps, but not something they're going to invest time in. And the story with MMTK was that at the beginning of the story, when we were using Jalapeno and GraalVM, it was a very fast runtime. And in fact, it was within 5% of the production JVMs. And so we had credibility absolutely on our side. But as IBM pulled funding from that project and they moved on and did other things, the project gradually slowed down and it slipped in its performance, eventually slipping quite significantly. And so this credibility disappeared, and then we were robbed of the opportunity to do research that had really obvious credibility in a way that we found compelling. And the problem there was that MMTK was written in a dialect of Java inside GraalVM, and we couldn't move it outside of that context. So we were stuck inside of a context which was gradually diminishing in terms of its impact. But another question is that of transferability. And that is, can someone outside of our particular context see the utility in what we've done? And that's not going to happen if you're only working in one runtime with only one language. So ideally, what we can do is take our ideas and show how they can translate across language runtimes. And again, that's something that we couldn't easily do with MMTK because it was stuck very much in that one runtime. So in the last part of the talk, I'm going to talk about where MMTK is now. And the good news is that we've actually completely rewritten MMTK, and you at MPLR are the first to hear of it. We've just released it this very week. We've done a full rewrite of MMTK in Rust. It presents itself as a shared library with VM-specific bindings. In terms of credibility, we've been doing this work with close cooperation with product teams. And in terms of transferability, we've got implementations in GraalVM, OpenJDK, and V8. And we're already working on a couple of other languages. Why did we use Rust? Well, it goes back to a paper that we wrote, my student Lin wrote a few years ago at ISMM, where we did an exploration into building a garbage collector in Rust. And what we found was that the static safety guarantees of Rust were actually extremely helpful in building the GC. And the number of times we needed to break Rust safety were actually very limited. So we're getting the safety with very few places where we needed to break Rust safety guarantees. And we did all this with great performance results. So that experiment gave me a lot of confidence that if we moved to using Rust for MMTK, we would have a better performing system and one that we had a lot of confidence in the correctness of it. So what would be the motivation for an industrial partner or an academic researcher to use MMTK with their runtime? So for an industrial partner, the way I see it is that the motivation for them is that it allows them to engage with the research community that they might, in a way that they might not otherwise be able to do so. So if they have an MMTK binding to their runtime, then many people from the memory management research community, whether or not they're using this industrial partner's runtime, can engage with it because the binding's there for free. So if I go and build a new GC algorithm, I can automatically go and test it. So if I build a new algorithm, I can go and test it in OpenJDK. I can test it in V8. So there's a vested interest for someone who's maintaining a system like V8 in allowing and opening it up to the research community by supporting a binding to MMTK. It also, more selfishly, allows them to evaluate research ideas that come out of the community on their own terms. So if a researcher produces something in MMTK and the binding exists to their runtime, then it allows them to evaluate that researcher's ideas using their own setting and using their own workloads. And from the standpoint of the academic researcher, it allows them to conduct research in an industrially credible setting. So you can work with OpenJDK, you can work with V8, and it gives you greater visibility because you're not just demonstrating your algorithm in one runtime, in one language, but in multiple languages and multiple runtimes. So how complex is it? How do we deal with the complexity in MMTK? Our approach is relatively simple. We think of things in terms of 4 discrete units. On the left there, you see the runtime, which in this case is V8, and that's an upstream thing. We don't touch that. Ideally, we don't touch that. We might need to at the beginning. And on the right, we see MMTK, and that's the core of the garbage collector. And in between, we see 2 impedance matching pieces of code, which we call the binding. And the one on the right is written in Rust, and that contains code that is specific to V8, but is in hot paths in MMTK. So for example, if we wanted to trace objects, find all the references in an object rapidly in MMTK, we can write code here in the Rust binding there, which introspects into V8 in Rust and tells us where the pointers are because it's got particular knowledge of the way V8 organizes its objects. And there's no impedance problem from the hot code paths in MMTK that want to establish that. On the other hand, the code on the left, that wedge on the left there, allows V8 to have its hot paths of things like write barriers, allocation sequences, and so forth, written in C++ and inlined into V8, only calling out to MMTK on the slowed path. So this is how we've built it. And we've done this not just for V8, but also for OpenJDK and also for GraalVM. Now, I've put the slide here because I wanted to talk briefly about my stay in Munich. I had a fantastic stay in Munich at this time last year. I think I left in November, and I spent 3 months there. And it was an absolutely beautiful place to visit, and I worked with a fantastic team. That was the V8 team, who are based in Munich. And I took this photograph here at the Olympic Park, and you can see the Olympic Stadium there. And that beautiful piece of concrete there on the left is actually a fantastic path that I ran along many, many times. And this brings back great memories. But the reason why I'm mentioning this is because one of the things I did while I was there, I did a couple of things, but one of the things I did there was further the work that had been done by one of my students in developing a binding from Rust MMTK to V8. And so what I was doing is trying to get that and then upstream the binding. And as I said before, V8 is a complex beast. And this here is a snapshot of the first CL that I developed. And you can see 82 files. It's touched 82 files. And I'm putting this on the screen here just to give you a sense of what it takes to stub out all of the GC relevant parts of a runtime like V8 so that we can intercept them all and bottleneck them through to MMTK. And this is only the beginnings. We end up being the change is actually quite a lot more substantial than this in the end, and it's now upstream. So if you go and look at the V8 source code, you will see the third-party heap, which was written by me and my students. And I put this here as a just more or less for fun. This is me having a debugging session, and it actually brought back echoes of that very first day at UMass. Because here I was trying to debug something deep inside of V8, and I find that I'm on line 88 on the right there. And of course, what is it? It bottoms out into some non-trivial macro that actually very helpfully raised an assertion check. But I'm putting this here to, again, illustrate the complexity of working in a C++ code base that is very mature and that has a lot of built-in complexity. So status, you can get MMTK right now from GitHub. We've got ports to 3 different VMs, and the functionality, there's a lot of functionality there. The actual release only includes 2 collectors, but we've built a lot more collectors, including a family of collectors for G1, and demonstrated them as being performant, and we'll have them public as soon as we can. And with that, I want to finish up, and before I do, I want to say some thanks. One of the things that I found actually really enjoyable about preparing a talk like this was going through and thinking through all the people who are involved in the various aspects of that work. I've talked to you about 20 years worth of work there in building up a whole lot of GCs, and in doing so, I collected the names of the different people I've worked with, and I've put them on the screen there as an acknowledgement of just how much these different people have helped me, and how much this something like MMTK is the product of an enormous amount of work from a very large group of people. And with that, I'll say thank you, and I'll be very happy to take questions.
So thank you very much, Steve, for the very interesting keynote. So let's follow up on questions. I think we have already one from Fabio on Slack. So I can repeat the question for people that don't have Slack access, just to repeat. So Fabio is asking that a question that often comes, it is to select the best GC for the particular workload. And there is a lot of resources, of course, and tweaking parameters for GCs. And he's wondering how automatic our GCs currently really are. And so considering the fact that current GCs, they have integrated machine learning. So the question to Steve is, how does he think the future will look like?
Yeah, Fabio, that's a great question. Thank you for that one. So I'll just quickly tell you an anecdote. When I first visited Google in Sydney, they've got a big lab in Sydney, that's where Maps came from. I was having lunch there, and someone got introduced to me. The people there weren't GC people, but there was this one guy who walked up and he got introduced to me. And that person, their whole job was turning the knobs on the JVM for Google. That was their job, full-time. That's what they told me, right? That, I don't know if it's true, but that's what they told me. The full-time job is turning the knobs on the JVM for Google. So this is not a hypothetical question. This is a very real question. And I know a lot of people struggle with it. I don't have any immediate answers for it, but I think it cuts to the brittleness of our designs. And, if you look at all the analysis that many of us have done in the community, you'll find that naturally different workloads will have very different behaviors and will tend to be suited more to one GC or another. And you'll have different needs as a user. You may be entirely concerned with throughput, or you may be critically concerned with latency. So your needs may be different as well. And so I think it's inevitable that if you're in a critical situation, you'll probably want to highly tune and carefully select the GC for that application. Still, I absolutely agree with you. What we want as GC researchers is to produce GCs that perform really well in most circumstances. And I think that remains a somewhat elusive goal. And I see it on the rest of your question on Slack. One of the things you asked is, you pointed to the work that there's been a bit of work going on. And in fact, Martin might have a response for this. He's giving a keynote later, and I know he's done work that's actually quite well aligned to your question about the use of ML, machine learning, to tune things like this. And I know Martin's got things to say about that. But let me just take my own take on it. This is interesting. I think there's a lot of potential there. But I think one of the problems is we need to be more creative with our GC algorithm design. And I guess that cuts to the heart of what I'm saying. If we have really good frameworks and we allow our research community to be agile intellectually, so we can experiment with really different ideas, then I think we're in a better place. If we take monolithic, long-lived GCs and then throw ML at them and try and tune those dials, I'm much less optimistic. So ML sounds great, but I don't think throwing that in at these monolithic, powerful, high-performance GCs is necessarily going to get us where we need to go. I think we need to be more aggressive and more agile than that.
Thanks a lot, Steve.
No worries.
So the next question is from again from Slack, about the architectural support, how acceleration for GC, and I think that's a good question because this intersects both keynotes. Yeah.
It does. And, I know Martin quite well, and it's a discussion Martin and I have often discussed at conferences, and who knows, we might even collaborate on this at some point. But it's a very interesting question from my colleague across campus. It's a very interesting question, and it's something I've always been interested in. My background, my training is as an electrical engineer, so I've always been interested in computer architecture. And one of the things that appeals to me about GC is it sits right at their interface. One of the things I've been working on with students here, which we're continuing to work on, is looking at near memory processing. I think that's really interesting. I think there's possibilities there. The other thing I've worked on with my colleagues and my former students was heterogeneous computing. And we did a couple of studies. In fact, Ting Kao, former student of mine who's at Microsoft Research Beijing, her PhD thesis, if you're interested in that question, I think her PhD thesis is a great place to look because she did a very detailed study of the energy and performance behavior of different elements of runtime, including the compiler, the runtime, the application, and the compiled code and the garbage collector, and how they perform on different microarchitectures. And the idea that you might want to run the GC on a simple in-order core at a low frequency because it's memory bound anyway, or multiple cores, and it doesn't need the GC needs very few, a very small number of instructions. I mean, it's essentially just a memory bound graph traversal thing. This is really interesting, but I think it's underexplored, and I think the time is right for doing this. So, yeah, I'm very excited and very interested, and I'm working on that. But save some more questions for Martin on that one, because I think Martin will have a lot to say, because of course Martin's background is terrific. He's done GC work in new hardware, and he's come from a great computer architecture research group. So he's a perfect person to ask a follow-up question on.
And also he chairs the RISC-V J working group, so they're doing a lot of work there for acceleration on hardware. Thank you, Steve. Juan is asking about more like a personal take on sacrificing opportunities to obtain further performance in order not to increase complexity.
No, great question. Great question, Juan. But the answer is no. And I tried to make that point earlier. So I was ruthlessly in pursuit of performance, but my philosophy was that flexibility and agility would get me there. And it's, my mental model is that of, the idea of finding a local minima and saying, oh, this is a great idea. Let's stick here. And then building up and building up and building up and then getting very stuck in this local minima. And I think that's a very easy trap to get in with software, with building garbage collectors, because they are so complex. And unless you have a toolkit-based approach, the investment you make in building that one garbage collector becomes so enormous. It becomes very hard, both emotionally and also intellectually, to move away from what you've got. And you have to be prepared to move away rapidly if you want to push harder on performance, because you've got to be agile. So I might be wrong, but my philosophy is that we need really good software engineering and really good agility in our software if we're going to get performance. And that's why I made that claim that performance, the complexity is the enemy of performance.
Thank you, Steve. So Jeremy is talking about debugging the virtual machines that you have mentioned in your talk, that you use a session-based debugging and high-level languages, at least idiomatic version of Java. So Jeremy is asking, what are your thoughts on formal modeling theorem for proving approaches to garbage collection?
Yeah, great question, Jeremy. I really like that question. And some of you may know that I sit alongside of some people who've pushed in this direction. So Tony Hosking is a close colleague of mine, and also Michael Norrish. Michael, he was one of the key people on the team that did the formal verification of the SEL4 microkernel, and he sits in the office right next door to me. And we've often looked at this, and we built a thing called the micro VM, and our philosophy there was that it was formally verifiable. Not that we necessarily were going to be able to do the formal verification ourselves within a short amount of time, but we're going to design it so that it could be formally verified. And we haven't lost sight of that. And Tony has done work on formally verifying GC, and other folks have too. So that's not my expertise at all, but I'm very, very sympathetic to it, and I see the power there. And so I've looked at a distance through my grungy low-level systems engineering lens at the work, say, the Rust Belt project. I don't know if you're familiar with the Rust Belt project, but that's trying to get us formal semantics for Rust. Okay, and that to me is obviously a necessary step if we're going to build out GCs in Rust. So I very much like that idea, Jeremy. I very much like the idea that we could give formal guarantees about some aspects, at least, of the behavior of our garbage collectors. I mean, as a community, but particularly with MMTK. But there's another thread as well, which I'm also very interested in, and that is, which is related to your question, Jeremy, I think, and that is fuzzing. I think that, as far as I know, I remember having a conversation, I think it was the ISMM program committee meeting many years ago, and John Rigueur was on there, and we're at some restaurant or something after the program committee meeting, and we decided we really should look at fuzzing for garbage collectors, and we never did. So I'm actually looking at it right now. I've got students looking at that right now, and I think that's a really interesting thread. So I spent 3 months at Google in Munich, and they have a fantastic setup for testing there. But they're doing it holistically, which is great. So they have an entire stack, which is millions of lines of code, and they fuzz above that stack. What I'm talking about doing is bringing it down to the garbage collector and just fuzzing the collector itself directly, which is obviously far more efficient, but it also raises a whole lot of interesting questions about how you can even do that. We understand how to fuzz an application with the garbage collector sitting inside of it, but how do we fuzz the garbage collector itself? And I think it's a really interesting question, and it's one that we're pursuing right now because I think we need that, and ultimately we would like some formal verification so that we can gain more confidence in the correctness of our collectors, and so people can build language runtimes where they have more confidence in what's going on.
Thank you, Steve. Jeremy, okay, thank you very much. Any more questions for now? Because I also have a couple of questions I would like to ask Steve, especially since the exclusive of the new MTK, which is in direct interest to our. So Steve, I have two questions. The first one it is more like theoretical, and the second one is more technical. So I'll start with this one, technical. So now you will maintain two different versions of MTK, the Java one and the Rust one, or the Java one will start slowly getting deprecated?
Yeah, the answer, that's fairly simple. I haven't been able to work on the GraalVM one for quite some time now. And the reason is simply this argument I made before, that I found it increasingly hard to publish work built on that for kind of reasonably sound reasons. I mean, from the point of view of the reviewers reviewing the work. So I haven't invested in that at all, to be honest. I've done some work. We've published papers as recently as this year that have built on it, but it's really in maintenance mode, to be honest. And so we're throwing all of our effort into this. And one of the reasons why we're doing this with this new MMTK is partly because I want to grow the community wider. I think that when we were just in GraalVM back in the day was, I think you could easily say it was the most vibrant research community for programming language implementation way back, some time ago. That's totally changed, right? But the problem with it is it's very limiting, because the only people there are people who are going to be working on GraalVM, and I want it to be open to people who are working on other Java runtimes. But importantly, I also want to go to other languages, and then we're doing that right now. And so that's why I'm throwing a lot of energy behind this Rust port. And, it's taken us a huge amount of work to get to where we've got now with this Rust port. So it's a big bet. I've basically not written much research for a while now. I've wound back my research to focus on infrastructure. My group has, and hopefully that'll pay off, not for us so much, but just for the whole community. I'm optimistic.
No, thank you very much for all the hard effort that you put for us. So is the Rust MDK could be potentially backport to GraalVM?
Yes, and it is. It is. Yeah, you can go and run on GraalVM today. Yeah, that's one of the ports. We support 3 ports. One is GraalVM, one is OpenJDK, and one is V8. The V8 is the most limited one, and that's essentially the complexity of building any GC port into V8. We're the first to try and put a different GC in V8, whereas GraalVM's had multiple GCs and OpenJDK's had multiple GCs. For V8, not so. So it's a pretty massive task to do that, and we've made a lot of progress. And it's upstreamed. So if you go and look at the V8 source code, you'll see our stuff in there now.
And how do you solve, from the GraalVM Rust port, how do you solve the problem with the native transitions, the performance of going from Java to native?
Yeah. So I had a slide which gave a hint at that, but I did gloss over it really quick. So I'm sure not everyone caught that. But what we do, it's actually an extension of an idea that we started back in the Java MMTK, but it's much more real and concrete now that we actually are crossing language boundaries. So what we think of every runtime, we're thinking in terms of 4 code bases. Okay, on one side, you've got something like GraalVM or OpenJDK or V8. And so that could be written in Java for GraalVM, C++ for the other 2 runtimes. And over here, you've got MMTK written in Rust. Okay, so the question I think you're asking is, how can we get performance with this language impedance? Well, we can get correctness straight away without any problem. I know that's not your question, but we can do that by saying, okay, every time we need to do a write barrier over here, we'll call out to a function in Rust and do the write barrier, and then we'll return. And every time we need to allocate an object, we call out and return. And we do that. And that's how you get your first port up off the ground. You do it exactly like that. But then what you do is you have these layers where you have a layer of, in the case of GraalVM, it would be a layer of Java code. In the case of OpenJDK and V8, it would be a layer of C++ code that interfaces in that direction. And what that does is it provides MMTK logic for that runtime. So Rust MMTK logic. So it will provide, for example, the fast path of our write barrier, the fast path of our allocation sequence. And so that is direct rewrite of that small piece of code that we've written in Rust. It now gets rewritten into here, and it gets rewritten for every runtime. But it's only a few lines of code. That's just your fast path for your write barrier. And And then on the other side, you've got a you've got a Rust interface, and what it does is when we want to say, for example, look at the objects in the pointers within an object, instead of calling all the way out to GraalVM to say where are the pointers, we have a small piece of code here that's written in Rust that is specific to GraalVM that knows exactly how to introspect the GraalVM object and is written in Rust and is inlined and so forth. So you can just go into there, get all the pointers from that GraalVM object without crossing the language boundary. So that's the answer.
Okay, so you identify all the, let's say, the hot paths that they have to be inlined no matter what, and then you implement them in both sides.
In both directions, yeah.
Yeah, both directions, yeah. Okay. Okay, that's good. So that means that the Rust version can be implementable to other VMs. And I think Stefan is following up on that, asking if the GraalVM native image project, the ahead of time Java, it's something that you have considered for adding support for the new MDK.
Not yet, but that sounds great. I mean, I'd be very interested in that. I'd be very interested in that. We've got a number of the projects we're working on right now to go beyond that. Starting with we're in summertime here in Australia. We've got 2 summer projects going right now. One is on .NET, working with Mooney Stevens in the .NET project, and the other one is with is Ruby, and we're actually working with 2 different groups on Ruby. So we're doing that, but Graal would be great. It'd be fantastic to have a port to Graal. And one of my former students worked on that many years ago as an intern at Refat.
Great, thank you very much, Steve. Yeah, because when you told us that you have done a new port of MMTK to Rust, my initial reaction was, I mean, Java being a programming language for systems programming has been something in discussion for many years. And there were like GraalVM and MMTK and Maximilian. And at some point, they were very competitive. But then, as you said, because of the community, they just lagged behind from the production quality. So then the Graal ecosystem came, which is essentially Java for system programming with the Graal truffle and all the system. And so, to my eyes at least, it showcased that it is possible to get really high performance for system development from Java. So I would expect MMTK to follow this trend and go from the Java version of MMTK to the Graal ecosystem.
Oh, totally. I think that's totally possible, actually. Yeah, I thought you were asking about Rust going to Graal, and that's also possible. But yeah, I mean, I think the only thing that made GraalVM fall behind is that just the class libraries in particular weren't updated as Java moved forward, and the support for the optimizing compiler fell off. But back in the day, it was perfectly performant. So there's no reason at all. I think absolutely that you can make a Java garbage collector written in Java that performs as well as anything else. I completely believe that. Absolutely.
Great. So any more questions for Steve? Because we'll take our first break and we'll go to our breakout rooms. Again, just a reminder for people that joined during the call, you can ask your questions on Slack on the channel for the keynote, or you can actually raise your hand on Zoom, and then I can pass you the microphone.
So I do have a question to broaden up the topic a little bit. So the idea was that we kind of go to ask me anything mode, and in that context, so deviating just a little bit from the keynote, Steve, you have been working a lot on evaluation methodology, building benchmarks. So Da Capo comes to mind. Do you have any specific advice to perhaps a PhD student or a young member of faculty who wants to approach a project in that kind of direction to kind of improve the situation of how we do benchmarking, how we do proper evaluation?
Yeah, that's a great question. It's a really great question. And, you know, how many hours have you got for this? I could spend a lot of time on that one, but I'll start with a relatively short answer, but it's something we can go talk about for ages. And by the way, Stefan, if you go to the MMTK website, you'll see there that we're using your framework for benchmarking the performance regressions of MMTK. So that's a plug there for Stefan's work. Yeah, so 2 parts there. One is the methodology side of it.
and the other one is the benchmarking side of it. I'll say two completely different things, which are kind of vaguely related. Building something like MMTK, the whole infrastructure from the ground up, is a huge amount of work, and you don't really want to be doing that as a PhD student. Okay, once it's being able to use that as a PhD student is awesome. Building something like a benchmarking suite, same thing. It's an absolutely massive amount of work. So you don't really want to be doing the building of the benchmarking suite as a PhD student. Contributing to it and having staff program is great. So the actual building of those things, I don't think you want to do. But here's, I guess, one of the, I think I even said this way back when I gave the original talk for the Decoupo benchmarks. One of the problems that we have in academia is that we learn. That's right. I had this picture from the Wizard of Oz. We're not in Kansas anymore. The image, right? He taps the shoes, and we're not in Kansas anymore. The point there was that so often when we're students, we learn this stuff from our advisor. And if you're unlucky, you get some old guy like me as your advisor. And unless they're on their toes, they will pass on to you what they learned from their advisor. There's a risk there, right? And what they learned from their advisor is old ancient history and no longer relevant often with respect to this particular question that Stefan's asking about with methodology. And so back when we started the Decoupo thing, one of the things we found was a lot of people were following the sort of methodology that they'd learned from their advisors who'd done everything in C and Fortran. And methodologically, that's another planet to what you need to do for a managed runtime. So what I'm saying there is I think it's very important that this is more for advisors than for students, that you keep on your toes and that you're able to move with a change in technology. And I think that's really hard to do unless you as an advisor are actually really engaged with the work and really understand how these things work, so that you can be aware that the methodology needs to shift if you're going to measure these things well. So that's one part of the answer. The other thing I'd say, which is perhaps more of an encouragement, I would say that, one of the things I value most in all of the research I've done in the last 20 years has been infrastructure my lab has built that allows us to do things with the sound methodology easily. So we have these tools, which I originally wrote, and then various students of mine rewrote, and there's faint echoes of the stuff I originally wrote now, but most of it's been rewritten entirely by my students over a number of generations. That tool chain allows us to rapidly say, oh, here's an idea. Okay, let's go run it. And within an hour or so, we've got a really crisp image of how this thing's performing, because we've got a methodology that gives us results that we have confidence in because of the soundness of the methodology. And we've got a framework which allows us to run it rigorously. And we've got visualization tools and so forth that allow us to quickly dive into the data and say, oh, it's clear that this is really noisy, or it's not at all clear what's going on, or it really is clear, and so forth. So that is really valuable. So when you're a student, if you have access to tools like that, you're at a really big advantage, I think. So I don't know if I answered your question, but like I say, I could keep going on this. This is sort of one of my favorite topics.
I don't know whether it's an answer, but it's certainly valuable insights. Yes, thank you.
Yeah, well, you feel free to reframe the question or remind me what the question was. I probably got a little lost in my own enthusiasm there.
I think it was general advice. I think it makes a lot of sense. So PhD students, I think, should always be careful what their advisors say. I think that's a very sound advice. And I think we need to question ourselves, but sometimes we get a bit stuck in the things we believe in. So
yeah, and I'm always learning a lot from my students because they do question me, of course.
Yeah.
And you have to be adaptive, but also you have to have an open perspective, right? So you look at what other research groups are doing and look at the great tools they develop and be ready to adopt them if they're open and available.
Yeah, and sometimes we have to bite the bullet and scrap our own tools and move on to other better stuff.
Yep, and I guess there's a message there, which is a trap, particularly for students, is there's a sense in which you can get emotionally attached to things. And that's a really dangerous thing to do, because if you get overly emotionally attached, you lose agility and you will get stuck. And ultimately, unless you're very lucky, you'll get stuck and fall behind. So this is very hard, because as humans, we tend to get attached to things we put a lot of labor into.
Indeed. I know the feeling.
Don't we all?
Thank you, Stefan. Of course, we have transitioned from the question for the keynote to the Ask Me Anything. So now it's like an open discussion we're going to have with Steve. And I would like to follow up on this Ask Me Anything question. Is that if you can let us know a little bit, where do you think that the research for garbage collection will go? So now we have a more heterogeneous architectures, like SoCs with the GPUs and FPGAs and multi-cores and different architectures. So do you think this will influence the design of the garbage collections, of the collectors as systems, like to offload different parts of the computation on different kind of hardware that all runs on the same processor? Of course, we have the problem of sharing memory between those, but let's assume that we are talking for a system that can share memory across the GPUs and the FPGAs or the CPUs that exist on an SoC.
Yeah, that's a really interesting question. There's a lot there. I mean, I think that as a community, as a research community, we've got a long way to go there. And again, I think this is a question that that Martin will have a lot to say on, because he's done such great work in this area. But I think it will have a big impact. I don't think we're going to be able to take orthodox ideas and just jam them into that new context. I think we have to think way more creatively. So, which I find fun. I think this is great. This big, because the trade-offs, I mean, these ideas are built, and that was one of the cool things about that paper that I talked about earlier in the talk about myths and realities. That paper there was really about rethinking a whole lot of assumptions that we'd made and measuring them, saying, hey, does this really hold? And that's going to happen even more radically in the environment that you just painted, the need to do that. And so to question all of our assumptions, because there's so much we do that is predicated on, assumptions that go back a long way, and they soon evaporate. Whether it be some of them based on the behavior of programs, and that too is changing too. As the hardware changes, so too the way people write applications, and that will affect the way programs behave, and the way programs behave will affect the way we want to write garbage collectors. So
yeah, true. And also, as Swab, it's saying on Slack, we also have a different kind of memories now. So the memory has completely changed, and there has been a lot of work, I think, from Urbana regarding how to deal with the non-volatile memories, and especially some blog posts from Mario Rotzko, and how this will affect the design of our, I would say, the systemic design. I mean, from how we think the memory applications to how the garbage collectors and the allocators, they actually implement those. And
yes,
and I would assume that, I mean, of course, you have thought about those things beforehand. And I would assume that the MMTK, it is going, no, at least it will maybe enable this kind of research.
Yeah, I hope so. It's interesting though. Look, I think there's another related point here, which is a little bit related to some of the other points I've made, and that is, I think sometimes our community is terrible at. A moment ago, what I said was we hold on to old things, right? That was what I was saying before. And we tend not to be agile and jump to the new, right, and adapt. But we also are appalling sometimes as a community at realizing that someone else has solved the problem we're interested in a long time before us. And the one you just highlighted is a great example of this. So back at the time I did my PhD, which is a long time ago, I actually did my PhD in this very area, persistent memories. In those days, the persistence wasn't in the form of a spin. It wasn't in the form of solid state memory, but it was in the form of a spinning disk. But the issues were the same, just the latencies were different. Yeah. And so the very first garbage collector I built was actually a transactional garbage collector for a persistent memory, the TMOS, transactional MOS collector. So this goes back a long way. So a lot of this stuff has already been thought through. Now, the ground rules have changed and the time constants have changed, but to ignore all that work is a huge mistake. And I think we actually saw that with, I think, the paper you might have been referring to from Illinois, where they seem to have not realized that actually a lot of what they were talking about was done at Sun Labs and actually by my research group as well, back in the late 90s, where we built a complete system of persistent Java, which ran native Java, regular Java bytecodes. You could take them, you could run them, you could pull the power on the machine, power the machine back up, it would keep running where it left off. We had that with transactions, multiple threads, the whole lot. That was all working back 2002. Now, and it was garbage collected. And it was garbage collected. Okay, so that was all working 2002. But you wouldn't know it if you read that PLDI paper from a year or so ago, because it's not even referenced, which I think is a huge mistake. Likewise, now Martin doesn't make this mistake, but if you talk to Martin, I'm sure you'll find that he will refer back to work done by people like Mario. When Mario was at Manchester, he did great work in this area, the Mushroom Project and so forth.
The Mushroom Project, yeah.
Yeah, that's right. It's really valuable. I encourage, this is going back to Stefan's thing about advice for students. The other thing that I really encourage you to do is to read widely. One of my more creative students, Xi Yang, he was a prodigious reader, and he read a lot of the old literature, and that was very often gave left field ideas into a contemporary setting, which were seeded by things he'd read in old papers. And he'd read Hamming, and he'd read all kinds of stuff from 50 years ago, and understand it and then throw it into a new context. And we did some really surprising things by throwing those old ideas into a new context. So that's another piece of advice I'd throw at grad students. Don't neglect to read great work from the past.
I want to circle back to when you started the discussion that you said that we tend to hold on things from the past. Do you think one of the reasons is because the entry barrier for such complex large systems, even if they are better designed, it's still very high? Like for somebody that is very familiar and cozy with one system software, then to retake all this huge learning curve and learn like a new one in a new context. I mean, I have felt it myself sometimes that I can battle myself like, is it easier to argue about using this system as it is versus another one, or it is easier to actually bite the bullet and migrate to that better system to do my research? So it's always a trade-off between those two.
Well, and that's what I've had to do with this MMTK thing. It was extremely difficult to make that decision, to throw away all that work and start again from scratch is a big deal. And it's very hard to do. And but we need to do that to move forward. To make progress, you need to be able to do that.
Yeah, I mean, technically you didn't throw it away. You just rewrote it in a different language. So the ideas are still there. Yeah.
But that's true. But actually, many of the ideas really change because, given if you're writing it in an idiomatic, if you heard my talk, I'm sure you did. You heard me talking about Perry chain's insistence. Let's write this thing in idiomatic Java. Let's not write it like a C program. Write it in idiomatic Java. We've tried to do the same thing with a Rust, but I'm not suggesting we've done a great job or anything. I'm not bragging about it, but that's what we've tried to do. And that's actually extremely challenging because we push the idiomatic Java so hard in MMTK that it's all based on class-based inheritance, which Rust doesn't have. Yeah. So I had to completely rethink some key ideas, and we have rethought some very major parts of it as a result of that.
And how long did the whole rewrite took? How much time do you take to rewrite the system?
It's hard to say. We've been so flat out trying to get the release out the door, which we did at noon today, like 8 hours ago. So you guys really are the first to hear about this. So I haven't had time to sit back and think about how long it took. But I've had 1.5 full-time years of people working on it, maybe 2 full-time. If I add up the amount of full-time work on it, that's full-time paid staff engineers. These are people with PhDs working on it full-time, not students. Plus I've had a lot of students working on it as well at different times. So I don't know, it's a lot of years worth of work. So in terms of dollars, probably about $1 million.
Wow.
Realistically, yeah.
Yeah.
And most of that came from our sponsors and from the government. On our webpage, you'll see who sponsored us. And so that generosity from those people, it could not possibly have happened without that, because I couldn't have done this project basically just on my own and with my students. I didn't have enough resources to do that, enough time for myself to do that. So I had to employ people in the end, and I employed former students, excellent people who did PhDs with me. And that's how it happened. But I could only do that once I had some real money from sponsors.
Yeah, of course.
So you guys can go and enjoy the fruits of our labor.
Yeah, we have been doing it for many years, to be honest, and we will continue doing probably with the new MPA. Thank you very much, Steve. So, any more questions for this MEA? So, after we until for the next 40 minutes, we'll have our break. We can have our coffees and transition to the Slack channels, where we can initiate our Zoom channels and discussions one-to-one. So yeah, you feel free to engage on the Slack. Yes, please, Steve.
Yeah, can I say two things before I go?
Yeah.
Before we finish?
Of course. Yes.
First one is I want to put a plug in for Da Capo. I'm very, very close to a complete redo of Da Capo. If you want to, you can go look at it. It's in a branch. It's in a branch on the GitHub, but it's very close to being ready, which is a major, huge amount of work. So anyway, for those who are interested in Java and Java benchmarking, just be ready to hear an announcement, which hopefully will not be too long before that comes out. That's the first thing I wanted to say. The second one, I want to just thank you guys. I think we can all thank you guys for organizing this. It's been I mean, I've really enjoyed it, and it's a very difficult time to be a conference organizer. So thanks, guys. I really appreciate it.
No problem. Thank you very much for accepting the invitation and giving us this exciting keynote. And for the couple, one last question: is it going to have more benchmarks? So
yeah, a whole lot of new benchmarks, new metrics. All the benchmarks that are retained are all updated to now, and there are a bunch of new benchmarks. And the other thing is for the ones where it's appropriate, we now have built-in tail latency metrics.
Oh, that's nice.
So you run the benchmark, and it will report the total time, and it'll also give you a tail latency curve.
Oh, okay, that's very interesting. And it is which GDK they're based on? 8+.
I'm testing everything with 11 and 13.
Okay. Thank you. That's nice. So we have so many new announcements today from the group. That's excellent. Thank you very much for the exclusives for today at least. Okay, thank you very much. So let's take a break and go to our Slack channels, and we will resume in 40 minutes at 10 o'clock UK time. Thank you very much.
All right, thanks, guys.
The reasons you should work at ARM are first, technology, right? The massive impact it's had on the world. And you can see that from the 2,000 people we were a few years ago to the 6,000 we are today. Secondly, it's got an awesome benefits package. Next year I go on a month's paid sabbatical. And thirdly, the people are really smart, so they challenge you, and actually more importantly, they're really nice. So they're really fun to work with.
If you want to work on technology problems that affect everyone, and you want to do it in an open, trusted environment where you'll be empowered to get on with your job, then this is probably the right company for you.
Definitely, ARM has changed me as a person. I've opened my mind up to an awful lot that I'd never come across before. It's been an excellent experience.
There's a very nice culture where the emphasis is on the engineering, the quality of the engineering, and indeed the welfare of the engineers.
Looking after my own mental health is something that's really important, and I think ARM gives me a good ability to do that.
There's kind of never a dull day. I'm never kind of working on the same project for too long.
I was in the Budapest office last week, the design centre, and I noticed a poster. It said, "Great minds don't think alike." And I just smiled when I read that, because that's exactly what it's like working at ARM.
Racing, a competition of speed set against an objective criterion, usually a clock. It is where the fastest wins, where the stopwatch doesn't lie, and success or failure is measured at the checkered flag. But for those who live racing, it really is more than just a race against the clock. The tension, the drama, and the unpredictability of the race, all of this adds to what racing really is. In racing, respect is earned the old-fashioned way, and greatness is built one victory at a time. Out there you are alone, with nowhere to hide. Any sign of weakness and you will be exposed.
Coming into the corner,
Lose focus for a single moment, and you will face the full wrath of the laws of physics. When the weight of the world comes crashing down on you, will you quit? Or will you dust yourself off and keep on fighting? Racing is where history is made and where champions rise from the crowd, accepting all challenges fearlessly. Champions aren't only measured by what they have won, but by what they have overcome on their road to glory. Without obstacles, tough battles, and pain, victory is empty. So what is racing then? Racing is 100% commitment to everything you do. At KTM, racing drives us and makes our world turn. This is the world that awaits you. KTM, ready to race.
Hello, everyone, and welcome back from our Brussels hallway. We will start our program with our first presentation from Martin Sulzmann regarding efficient, near complete, and often sound hybrid dynamic data race prediction.
Hi there, I'm Martin. I'll present our work on efficient, near complete, and often sound hybrid dynamic data race prediction. This is a joint work with my PhD student, Kai. Okay, so it's about dynamic analysis of data races. We consider programs that make use of multiple threads that share information via shared variables, and we find lock, unlock, also sometimes referred to as acquire, release operations to protect critical sections of mutex operations. We consider a dynamic analysis, so we assume the program is instrumented, and we let the program run, and the operations we're interested in, they emit events which are recorded in a trace. And based on the trace, we wish to predict if there's a data race. So data race means there are two conflicting events where one of the events is at least a right event that appear right next to each other in the trace. Okay, so here's a simple example. I'm using a tabular notation where for each thread I have it's written its own separate column, the trace represents an interleaved program execution. So we have in thread 1 an acquire on Y, a release on Y, and a write on X. And in thread 2, we have an acquire on Y, and a write on X, and a release on Y. Okay. It's easy to see that the two writes are in conflict. Okay, so of course the conflicting events must result from different threads, and the actual challenge is actually to check if there's a reordering, because as we can see in this example, the writes are in conflict, but they don't appear right next to each other, right? So they are separated by some events, and we wish to find a reordering so that actually that these conflicting writes appear right next to each other. Okay, and the reordering represents an alternative program execution. So that's the main idea. So we have a program run. There are conflicts, but they don't seem to immediately mean that there is a data race. And we wish to check if there's a reordering such that there is a data race. Okay. And for that example, it's quite simple. We can argue there is a reordering, so an alternative program execution, where in the third execution step, I let thread 2 have a go. So I'm using here in the reordering on the right, I'm using here the original trace position numbers. And we see here we have first then the acquire on Y, then comes the write on X, and then we have the write on X. And finally, we see that the two conflicting writes appear right next to each other. And by highlighting the conflicts yellow and then the data races as red, we see, yes, there's a witness that shows the two conflicting writes, they form a data race. Okay, so that is a challenge, and the wish list is, or the goal is actually to be efficient. We would like to report the data race as fast as possible. If possible, run through the trace once and then report the data races. We like to be sound. That means we only like to consider data races that are actually feasible, which can actually be replayed through an actual program execution, so no false positives, and we want to be complete. That means we want to have no missed data races, no false negatives. Okay, so earlier work, there are sound and complete methods. So what they do is, SAT and SMT solving based methods, they effectively consider all feasible reorderings. Okay, the problem is they don't scale well to large program traces. In practice, the traces can make up of 1 million events and more. Okay, so those methods, they don't scale. Method that scale, that means are efficient, happens before and log set. And we're going to look at those methods now in more detail. So the log set method has a simple idea. It says, for each event, compute the set of logs held when processing these events. Okay, we go through the trace, and whenever we see a log, we say, oh, we acquire that log, and maybe if we have an event where we have a log held, then we add that log to the events log set. And then we can argue, well, if we have two conflicting events and they share a common log, meaning the log set is not disjoint, then they can't be in a race, right? The simple criteria that exclude the race. But if they don't share a log, that means if the log set is disjoint, then this is certainly a criteria for a data race. The trouble is, this is only a necessary criteria. Yeah? So we can actually show that in theory, the log set method is complete, but in practice, it yields to a number of false positives. So here's a simple example. So we have here a variant of our running example. We have again 2 threads, and we have a third column where we report the log set for each event. We have 2 conflicting writes on X. Okay. In addition, we also have a write on Z, and we see that write on Z is protected by the log Y. And we have a read on Z, which is also protected by the log Y. That means the write on Z and the read on Z, actually they also are in conflict, but because they are protected by a common log, we don't consider them as being in a data race. On the other hand, the 2 writes on X, they're not protected by a common log because the log set is empty. Okay, that's why we report here data race. The problem is this is actually a false negative, because the issue is the log set method doesn't take into account write-read dependencies. So we see here we have a write on Z followed by a read on Z. Okay, and for a feasible trace reordering, we demand that each read sees the same last write. Okay, So each read sees the same last write. This is important because if we change this write-read dependency order, it means the read might see a different write, and then we can't guarantee it's the same value. It's not the same write, and the read might be part of a conditional expression, so the control flow might be different, and that's why the reordering might no longer be feasible. That means, for instance, in this case, if you have these two conflicting events, and the logset method says, oh, there is a data race, we could argue, well, we just move up the events in thread 2 above the events in thread 1. So that looks like a data race, but the problem is the read here doesn't see anymore the same write, and that's why we don't know if this is a feasible trace. And that's why this is a false positive, meaning there is a program text for which this is a false positive. Okay. Good. What about happens before method? Okay, happens before. Well, the idea of the happens before method is also quite appealing. The idea is we go through the trace, process one event by the other, and while we're going through the trace, we build up a strict partial order. Okay. The idea is if two events are ordered, then the event must happen one after the other. Happens before. Okay, so that means if E is ordered with F, then E happens before F. Okay, so the idea is that if we have two unordered events, that means if they're not ordered under this relation, then they are concurrent to each other. Okay, so that means there's no strict ordering, and in terms of the trace, that means, oh, there must be then a reordering where both appear right next to each other. Okay, and for conflicting events which are not ordered under this happens before relation, this signals there is a data race. So this is usually generally safe, sound, but the problem is the happens before relation imposes the restriction that the critical sections are strictly ordered based on the order in the trace. And this might lead to false negatives. So here's a simple example again. Here on the left, we have the observed trace. We have, again, the conflicts among the two writes. And the happens before relation orders the critical sections based on the order in the trace. So we generally assume the program order. That means the write on X happens before the acquire on Y, and the acquire on Y happens before the release on Y. And now what the happens before order does, because the critical section in thread 1 appears before the critical section in thread 2, happens before says that the release here happens before the acquire on Y. Okay, and via transitivity and the program order, we can see that the two writes are ordered under happens before. But there is a different, there's a reordering possible where we simply schedule first the critical section in thread 2, that's shown on the right. So we first run thread 2, we first process the acquire event on Y, then the write on X, and then the write on X in thread 1. And then we see that actually the two conflicting events, they can really form a data race. Okay, but this is not usually observable by using the happens before relation. Okay, so we see here the pros and cons of logset and happens before, which are efficient method, and it seems like that's the way to go, right? And this is something also others have thought about. So the name of the game is usually trying to make the happens before relation as weak as possible without losing soundness. Okay, so that means weakening the happens before relation so that we can catch more errors. Okay, the approach we follow, we are significantly weakening the happens before because we want to make the happens before weak enough to be complete. Okay, we weaken the happens before relation so it becomes complete. But then it becomes almost too complete. We might run into too many false positives, and that's why we additionally impose the logset. Okay, so we introduce in the paper a hybrid method. That's one of the key ideas, and one of the novelties is our PWR relation. It's a variant of the happens before relation. In that area, it's very fashionable to give three-letter acronyms to your happens before variants. And it's called PWR because we impose a program order, we impose write-read dependency, and we impose a relaxed release order. So we only order release if there's a write-read conflict among critical sections, but all other conditions are not imposed. Okay, and for us, a race arises if the log sets are disjoint and the events are unordered under the PWR relation. So that's one of the ideas in the paper. The other idea is that we actually apply a two-pass method. Okay, because what we observe is that if we only have a single path, so a one-pass algorithm, then we might miss some obvious data races. And one of the objections is to become complete. Now, two passes sounds like extra time. Yeah, we'll see that. But actually, there's an optimization that might lose a bit of completeness where we can integrate the second into the first part. Okay, but let's just look at the highlights of the PWR relation in connection to prior work. Okay. Some of you might heard about the WCP relation, the weak causally precedes relation. It's a variant of the happens before relation, and the idea of WCP is not imposing a strict order among critical sections. Under WCP, critical sections are only ordered if there is a write-write conflict, write-read or read-write conflict. So here on the left, I have an example where I have two critical sections, the one in thread 1, that they are in a write conflict on Z. Okay, so the two critical sections are in a write conflict on the shared variable Z, and therefore they are ordered under WCP. WCP doesn't order the release to the acquirer. What WC is doing is WCP orders the release to the closest conflicting write. So that is sufficient. Okay. Anyway, what we'll see by imposing that WC condition, or like the order, we see that the two conflicting writes on X actually they are ordered. Okay, so that means they are no longer unordered. So that means they are ordered, and because they are ordered, they can't be in a data race. That's what WCP says. But in this case, we see that we can reorder the events. So we can first have the thread 2 run, because there's no harm in reordering the critical sections in case of a write-write conflict. There's really no harm. Okay, we can simply reorder them, and that's what we're doing here in the reordering. We first have the thread 2, and then we have the thread 1, and we immediately see then the two conflicting events are in the data race. And PWR drops that condition that is imposed by WCP. That's why it's more complete relative to WCP. Okay. Another important related work is WDP. It's called the weak dependently precedes relation. Like PWR, WDP is complete. Okay, so it's a complete happens before variant. Okay, but WDP is significantly weaker. So here's a bit more complex example that shows one of the advantages of PWR over WDP. So WDP only orders critical sections if there is a direct write-read dependency. But here there are two joint write-read dependencies. So I have here thread 1, and I see here that that write is in a write-read dependency with that read, and that write is another write-read dependency with that read. Okay, so therefore under PWR there is a order among the critical sections. That's why under PWR, the two conflicting writes, they're ordered. Okay, so the PWR would say there is no data race, and rightly so. Okay, because there is actually really no data race, because to exhibit the data race, we would need an infeasible trace reordering, which would violate the write-read dependencies. But because WDP doesn't combine these intermediate write-read dependencies, PWDP would wrongly say here there is a data race, and that is a false positive. Okay, so the precise connections to WDP is actually explained in the paper with all the formal details. Okay, so the point is PWR weakens WCP to become more sound, and it also strengthens WDP to become it weakens WCP to become more complete, and it strengthens WDP to become more sound. What a mouthful these three-letter acronyms are, right? Okay, good. The other point is the limitation of a one-pass algorithm. I said usually all the algorithms, also actually interestingly the WDP algorithm, although the relation is actually complete, the WTP algorithm is not complete because it's a one-pass algorithm. And the issue is with the one-pass algorithm that the one-pass algorithm, the idea is that it only maintains the most recent write per thread. So we only looking here at writes. That's why I say we only consider the most recent write. That means for this example, that the write at trace position 3 overrides the earlier write at trace position 1, right? So we immediately see based on the program order, there's a consecutive write, so that's why we only maintain, there is now a write at trace position 3, okay? So once we see, or once we reach the write at trace position 6, we've forgotten about the write at trace position 1, okay? So that means we only see the write at trace position 6. That means we only see, there is here a conflict, okay? We are here in a conflict, and we see, these two guys are unordered, okay, they're unordered, but of course these two guys are protected by a common lock. That's why we don't report any race. The issue is there is actually a data race, right? So the earlier write, which we kind of ignored when we were processing the second write in thread 1, is actually the earlier write here is actually in a race with the write in the thread 2, okay? But that information is kind of forgotten because we override that earlier write by the subsequent write in thread 1, okay? So that is one of the limitations. And our idea, how we cope with that, is we actually perform 2 passes. We do a first pass where we do a bit of bookkeeping, okay? What we'll do is when we override an earlier, kind of we remove the earlier write by a subsequent write, we record a history, right? So at that point, we record the history that the write at trace position 3 overrides the earlier write at trace position 1, okay? While we go through it, we record all the unordered pairs, okay? All the unordered pairs. We do know unordered pairs means the writes involved, they're not ordered under the PWR relation. We do know, of course, this unordered pair is not a data race because they share a common log set, but the critical point is here that via that unordered pair and the history, we reach another unordered pair, and that unordered pair is in a data race. How does this work? It's actually quite simple. We see that we have here an unordered pair, and by following the history, we kind of can conclude there's another unordered pair that is formed by the elements W write of X at position 1 and the write on X at position 6. So that means these two guys, right? So we see here from that unordered pair via the history, we conclude there's a new unordered pair, okay? And we see that this new unordered pair obviously is in a conflict, and we see that the elements in this unordered pair, they don't share a common log, hence it's red, highlighted red, hence we have a data race, okay? So we have this idea of 2 passes, okay? And it's really critical to really catch all the data races. Okay, so all the details how this work is done in the paper. So another important thing we do actually show in the paper is it's possible to integrate a second into the first pass, right? So because if we always strictly use 2 passes, it's still kind of efficient, but it's only semi-efficient. It's only semi-efficient because by using 2 passes, we actually need quadratic runtime, okay? It's shown in detail in the paper, but now comes a nice idea. We can simply maintain a limited history, okay? A limited history is different from a limited window size, okay? What we mean by limited history is that we only maintain a maximum, let's say, of 25 history relation. That's the number we came up with going through real-world examples, okay? It seems like for real-world example, it's sufficient to keep the most recent 25 writes per thread, okay? And then we can actually easily integrate a second into the first pass, and that turns then that 2-pass quadratic runtime algorithm into a single linear time, a single pass linear time algorithm. And of course, by imposing a limit, we lose a bit. That means in theory, we are no longer complete, but it doesn't seem to bite us much in practice. Okay, good. To sum up, we have a bunch of novel algorithms. We have a novel happens before relation. All the details are in the paper. In theory, we have a quadratic runtime algorithm that is complete. It is not sound in general, but in practice, it seems to work out quite well. If you integrate the two passes in one and impose a limit on the history, we are linear in runtime and near complete. We have a lot of benchmarks, performance benchmark, precision benchmarks, full implementations. We compare all the state-of-the-art works in the area. Please read the paper. It's all written up on in a lot of pages, and you will enjoy reading it. Okay, thanks a lot.
Thank you very much, Martin, for the interesting presentation. So as usual, we will take now some questions regarding your presentation. Of course, for the people that just joined, to give you some heads up regarding how to ask questions, you can raise your hand in Zoom and I can give you the mic, or you can ask your question in Slack, and then of course I can relay the question, and of course Martin can read it. So so the first question is from about Stefan regarding to elaborate a little bit about the requirements for traces to apply such analysis. So so they have to be special traces or generic, let's say, instruction traces?
Sorry, I didn't catch the question. I was just typing in an answer in Slack.
Okay. No problem. So the question is from Stefan about the requirements, what the requirements are for those traces to apply the analysis. Do they have to do some post-processing on the traces?
Yeah,
or
so it's in the paper. Actually, we are using the Roadrunner framework, right? So the real-world benchmarks, they all are Java programs, although it doesn't matter if it's Java or whatever, because actually we only analyze the traces, and the Roadrunner framework, actually what it does the hard work of instrumenting the Java programs and then storing all those traces, and those are the traces we then process.
Mm-hmm. Thank you. Next question, I think it's both from Juan and Stefan regarding to elaborate a little bit about the limitation regarding the 25 relations in the living history. I mean, you said in the presentation that it's based on real world scenarios, right?
Yeah, so we were just fiddling around with it. We're using Da Capo and Java Grande and all the benchmark part of these two benchmark suites. And we were just fiddling around with that number. So it turned out 25 seemed to be a good number. As far as I recall, there's one case where 25 is not sufficient. But actually for that particular case, I can't recall. I will type it later into Slack. For which case is not sufficient, because for that case even it would need almost an arbitrary large number. Okay, so often the take-home message is often a constant number of a history is sufficient, but there could be cases where actually it need to be arbitrary. That means you would need to switch back to a two-pass algorithm, which means you have a quadratic runtime. Okay.
Can I ask a follow-up question on this particular topic? In your analysis, when you're trying to find this, the number of the maximum rights to maintain, did you find any relationship or correlation between the type of applications and how much this number increases? So did you notice some specific classes of applications in your analysis that require more, a larger history?
So we haven't really looked into the Java programs, I have to admit, right? We only see the traces, okay? Mm-hmm. So, and I don't think we experienced any particular patterns, but there was one Java program for which actually the limited history is not sufficient, okay? I'll type it in later into the Slack channel, okay?
Thank you. We have one more question from Peter on Slack. But it says that the Roadrunner used to have an issue with volatiles. instrumentation is always either before or after, with open space for races. And I think this was later that was fixed with logs. So the question from Peter is whether you did your benchmarking with lots of volatiles.
I would know actually. So my PhD student did the benchmarking, and as I said, we're using the latest version of Roadrunner. Again, I will double check. I mean, obviously, the analysis results have to take with a grain of salt, because there could be still some bugs. Actually, there was unknown bugs in Roadrunner, right? And obviously, if the instrumentation has a problem, and if the traces are inaccurate, then obviously the analysis results are inaccurate. But this is shared by all the works in the area, right? So I think most of the earlier works, the competitors, that we all use Roadrunner.
Thank you very much. I think we have time for one more question. So if you have more questions regarding Mark's presentation, please let me know. Otherwise, I will take the opportunity and I will ask one more question. We are doing a lot of work in our group regarding debugging databases stuff. So my question is, what would be the workflow by using your tool to go back to the initial, let's say, source code and then try to fix the problem there? So as soon as we discover a bug, let's say, or data race with your framework, what would be for us the next thing to do to correlate this with a Java monitor, for example?
So at the moment, the output of our tool is just like the source locations, right? For each data race pair, we would be able to refer to the source location. But actually, how to explore the information, we haven't thought about it. Okay, I mean, there are issues like which data races should be looked at first, right? Is it like the first data race, or you want to collect them? Probably there's a pattern, right? This is something we haven't really explored yet, right? So we have all the raw information there, right? It's a complete analysis, but actually how to use it and feedback it to the user, that's something we yet have to do.
Thank you. And I think that's a follow-up question from Juan in Slack. If you could expand in which cases you can get false positives with your solution.
It's a bit more elaborate example. It's in the paper. What I'll do is I'll add a link to the paper, and you will find in the paper then the reference that it explains. Yeah. So I mean, the false positives, it's like finding the sweet spot, right? So being as complete and as sound as possible, right? So and we're actually striving for completeness. That's why we have to live with some false positives. Yeah.
Thank you very much, Martin. So if you have any more questions for Martin's work, please write them on Slack, and in our hallway break, we can actually continue discussing. So we will continue with, thank you very much, Martin. We will continue with the next presentation, which is from Thomas Pointhuber from JKU Linz regarding symbolic execution on the GraalVM.
Welcome to our presentation about SymJEx, a symbolic execution engine based on the GraalVM. I'm Thomas Pointhuber and will now present you an overview of the current state of this project, its operating principles, and the different ideas which influenced our development. So, how can we check application for errors? For example, program testing techniques such as JUnit tests allow us to write unit tests for concrete values. Every one of those test cases executes a concrete execution path and checks for the expected results. However, we cannot find bugs which are not coded into one of such tests. Program verification, on the other hand, does not check specific input values, but all of them. You can write a specification which encodes the behavior of a function, and the tool verifies that you adhere to the specification. A very simple specification would be, for example, this function will never throw an exception, anytime. A program verification tool, such as a simple execution engine, then can check if there are any paths violating the specification. If this is not the case, we have proven that the function is indeed valid to the specification. Like in this example, the function can not ever throw an exception because there is no reachable path which would throw an exception. Symbolic execution is a program analysis technique operating on the program path level. Every possible path is encoded into mathematical formulas, which then can be checked by SMT solvers for satisfiability. This allows us to verify programs as well as to automatically generate test cases. Looking at the given example, we have a triad function, which includes error checking codes. If the index is out the array boundaries, an exception is thrown. On the right-hand side, we see the different paths which can be executed in this program. Execution. If we now want to check if an exception is possible, we use the SMT solvers to either tell us, we use the SMT solver to check if there is a solution given the selected path conditions. The SMT solver will now either tell us the formula is unsatisfiable, which means that the given path is in fact unreachable, or it will return satisfiable, which tells us the path is indeed valid, and it even can give us a model which satisfies all those conditions. And thus would lead to the given program path. This model can then be used to help programmers reproduce the fault or to automatically generate test cases. GraalVM is a Java virtual machine written in Java, which allows the execution of Java bytecode as well as of so-called truffle ASTs. Due to its polyglot language execution capabilities, it is a virtual machine designed to execute a wide variety of programming languages on one system. For this example, we can execute the truffle implementations of Python and JavaScript, interacting with each other. Inside one virtual machine, the Graal compiler sits at the heart of the GraalVM. It is a dynamic just-in-time compiler that optimizes programs by using profiling information gathered at runtime. With SymJEx, we primarily aim to achieve three major goals. First off, we want to use compiler IR to allow simple execution of the whole range of Java virtual machine bytecodes. Secondly, leveraging the proximity to the compiler, we want to apply compiler optimizations to simplify the program before simple execution. Lastly, there is an ongoing effort of ours to integrate SymJEx with other components of the GraalVM ecosystem, such as native image, which allows points-to analysis, as well as the truffle framework for language interoperability and polyglot symbolic execution. SymJEx is a symbolic execution engine built on top of the Graal compiler. We use compiler components such as the bytecode parser and the graph builder to generate Graal, which is then simplified using compiler phases from Graal as well as custom one. Then SymJEx iterates over all the program paths of the I, thereby accumulating path constraints and tracking memory modifications. Whenever exception paths are encountered, we use SMT solvers to determine satisfiability and if so, allow the generation of test cases or error reports. In fact, SymJEx is a backend for the GraalVM, which executes symbolic values instead of concrete ones and can execute multiple different paths instead of only a single concrete one. Through the analysis, SymJEx maintains a symbolic state, which represents a single location on a distinct program path. A symbolic state, in our case, captures the current heap configuration, the path constraints that must be satisfied to actually reach this state, as well as additional information such as the position on the call stack or the current loop iteration count. We can arbitrarily fork, suspend, or resume individual states in order to visit more promising paths first. With the current search strategy, we order states based on the depth and the complexity of the current path. The constraints of a symbolic state are generated directly from GraalVM, which is a compiler intermediate representation structured as a directed graph. During symbolic execution, we follow the control flow of the GraalVM, which are our program paths. The data flow information, on the other hand, tells us how data is mutated along this path. For example, we have this given source code snippet, where we apply some mathematical operations on some variables. This example only has a single control flow, because there are no state splits such as an if present. For our return value, we add the product of a floating point multiplication to the result of an integer division, including implicit type conversion. Using this graph, we can then convert the nodes from GraalVM into an intermediate representation which can be handled by SMT solvers. This IR resembles a directed acrylic graph and is strongly typed. While the GraalVM is based on Java semantics, the intermediate representation uses SMT semantics. Differences are, for example, that SMT arrays do not have a length compared to the Java equivalent, and are not initialized with fixed values. Array assignments, furthermore, can only mutate one element per operation. Floating point operations also differ between Java and the SMT representation, even though they are based on the same floating point standard. Whenever a solver has to be invoked, SymJEx translates the constraints from the intermediate presentation to SMT-lib, a standardized language that is supported by a majority of SMT solvers. To furthermore prevent incompatibilities, we use a limited set of SMT-lib extensions, thus restricting ourselves to quantifier-free formulas using bit vectors, floating point, and array theories. Quantifier-free due to performance reasons, and bit-exact theories to allow sound and complete analysis of path constraints so we can model the same behavior as on real hardware. The exemplary expression IR in this case results in the SMT code on the right-hand side. Here we only use bit vectors and floating point values. In the usual compilation process, the GraalVM goes through several optimization phases before being converted to machine code. For symbolic execution, we want to find real errors in programs and prevent false positives. Therefore, we have to ensure that the produced IR retains the semantics of the original source program without using speculative or optimistic optimizations, and as usual for just-in-time execution. We apply a number of optimization phases provided by the Graal compiler, namely strength reduction, conditional depth code and read elimination, as well as partial escape analysis. Additionally, we can preemptively simplify loops via unrolling or extract and peeling of individual loop iterations. Graal furthermore allows us to inline method calls. All of those optimizations limit the overhead of the analysis later on while preserving all relevant program semantics. As all of those optimizations are designed for just-in-time compiler architecture, they are inherently required to reduce execution overhead, which allows us to scale with growing method sizes. Besides the compiler optimizations which we use from GraalVM, we added custom optimizations for symbolic execution to reduce the number of basic blocks, apply constant folding on arrays, and to apply path merging inside the GraalVM. Furthermore, symbolic values are introduced using custom compiler intrinsics. For our memory model, we had to take the Java memory semantics into consideration. In contrast to lower-level languages, Java doesn't support pointer arithmetics or row memory addressing, which simplifies our memory representation. Nonetheless, our memory model has to support pointer aliasing and object references. To produce context sums, we further need to be able to reconstruct valid Java objects out of the memory model, including the correct type and value assignments, even though our representation differs from the one used by Java. Let's take a simple person class as presented here and take a look at how we can express such objects in a rather simple format such as SMTlib. If we have 3 objects as present on the right-hand side, with 2 of them being concrete and 1 of them being unknown or symbolic. How can we transform those values into SMTlib structures? As already mentioned, SMTlib mostly supports numerical data types and arrays, with limited support for structs. Therefore, we have to get creative. In SymJEx, we use a structure known as field heap, where we essentially break up objects into their individual components and store those in distinct SMT arrays. For example, to store our persons, we would create 3 distinct SMTlib arrays. 1 for each field: ID, name, and age. Each concrete object now receives an entry in each of those arrays, always at the same index position. The person variables now merely contain the indices, the addresses, so to say, of the position where the components of the objects are stored. All that remains is our special case, the symbolic object P3. Based on our current heap configuration, we now have to distinguish between 3 possible cases. P3 may point to one of our known objects, P1 or P2, or it may be a new yet unknown object as represented in position 3, or it may be null, which we denote via the indices 0. Due to our memory model, we can now encode those 3 cases directly without assigning a concrete index to our P3 variable. It remains symbolic. Naturally, Java strings are also objects, which have to be stored equivalently. As each string is composed of a byte array, we get an additional SMTlib array, which stores the reference to the byte array. The byte array consists of 2 additional SMTlib arrays, where the first array contains the actual array content, the names, while the second array contains the array lengths. With our memory model and the constraint framework now in place, we have yet another challenge to solve. State explosion represents a major problem in symbolic execution. It occurs whenever the number of program paths grows exponentially, such as in loops, dynamic dispatches, or when reasoning over arrays. As we are bound to quantify 3 formulas, we also cannot simply relate those problems to the solver, but have to deal with them directly. The initialization of an array with symbolic length is such an example, as SymJEx previously struggled. A popular technique in modern symbolic execution engines to handle this kind of problems is to trade completeness or coverage for performance by using approximation. For the array example, we therefore may either under-approximate the solution by limiting the arrays as artificially, thus perhaps missing paths, or we may initialize only parts of the array, which in turn enables false positives. In SymJEx, we actually use a solution based on the method of counterexample guided abstraction refinement, where we use over-approximation during analysis and then verify potential spurious counterexamples by using under-approximation. For unbounded arrays, we therefore loosen the constraints and then use artificial length limits to verify whenever a counterexample is still valid. While this approach is still somewhat limiting, we currently cannot execute counterexamples on the actual program itself. To get a comparison with other symbolic execution engines, we integrated SymJEx into the SVComp benchmarking sphere. As shown in the table, our work-in-progress engine could achieve an average score among all the other competitors, with no false positives or false negatives. We actually run SymJEx with multiple configurations. The right line in this graph represents results where we use Graal native image. to perform a more thorough analysis of the IR with the cost of additional optimization overhead. This overhead is directly visible in the graph, although it later converges with the results of our ones without native image. We furthermore use different solvers and different interfaces to those solvers, notably Z3 with and without native binding, CVC4 and Bolector. While Z3 and CVC4 achieved fairly similar scores, Bolector ran slightly below due to missing floating point and array-in-array support. As shown today, SymJEx is already tightly integrated into the Graal compiler infrastructure. Future work on SymJEx nevertheless mostly focuses on providing connections to even more components. Most notably, we would like to support truffle languages, a feature which would immediately increase language support and make SymJEx a truly polyglot symbolic execution engine. The current problem in this undertaking stems from the lack of information we can extract from the initial truffle ASTs. Since truffle gradually specializes its AST nodes, it requires several concrete executions to get actual information, a problem that is especially prevalent in dynamic languages. We can already use Graal native image as an alternative to our custom graph builder process, as seen in the evaluation. A future goal is to better integrate the points-to analysis to gain additional information for symbolic execution, such as more restrictive types for symbolic variables, or to identify invocation targets on symbolic objects with better precision. With that in mind, I would like to finish my talk by thanking you all for attending. We are now open for questions.
Thank you very much for the presentation. It was very interesting. So please, if you have questions for Thomas, let me know, either by raising your hand in Zoom or in Slack. I would like to start with a couple of questions to Thomas. My first is this tool is open source? Is it available for download and testing?
Unfortunately, SymJEx is not open source for now. It was sponsored by Oracle, and at least until Oracle says we can make it open source, it's unfortunately a proprietary system for now.
Okay, so for the time being, it is a proprietary, but it might be open source in the future.
It's the question what Oracle says in the future.
Okay,
but I would like to see it open source.
And I have one more question. Because I'm not very familiar with how the performance is being assessed for symbolic execution frameworks. So comparing the SymJEx with other similar tools, we measure the speed, right? So how much time it takes to actually solve the state of at least the constraint space that you set, right?
In the presentation there was a so-called cactus plot, where we can see how many benchmarks the symbolic execution tool can solve in general. So the more we can solve, the better it is, as well as how fast we can solve the first 200 benchmarks in what upper bounds we can solve the next 200 what upper bounds. And you try to have a curve which is very low for a very long time until path explosions come in or you can no longer reason about it.
Thank you. I have a couple of more questions from Slack, from Stefan and Juan. So Stefan is asking if you could elaborate a little bit more how symbolic execution interacts with optimistic optimizations, for example, in liming, which is also often done optimistically.
I don't know the term optimistic optimizations.
I think
my colleague is answering it. GraalVM contains many let's call them optimistic optimizations, like this branch is very unlikely to happen because it throws an exception. So we do a de-optimization target. So if the code reaches that, it goes back into interpreter mode. We deactivate all those optimistic optimizations or anything which would cause the GraalIR to force us to do some interpretation. We want to have the whole graph to contain all information. We have all exception edges in the IR, and we do not optimize them out like GraalVM would do for execution.
Thank you, Thomas. Juan is asking about your ongoing work to extend your current work for truffle languages. So she's asking, so since you are based on GraalIR and at some point the truffle AST will be transformed to the GraalIR during execution, what are, theoretically, you could run out of the box any truffle language. So what are the challenges in doing that?
When we started with the development of SymJEx, we actually ran SymJEx on a truffle language, on a very simple one. The problem with real truffle implementations like Sulong or with the Java implementation of truffle is that they're not really optimized. So you have a lot of different branches for a simple addition operator because you have specialization for integer, long, for normal object types. And at least to my knowledge, GraalVM cannot optimize them out statically, but it uses runtime information to do so. And this would require us to solve all those different cases, which would make it very slow.
Yeah, would it be possible to take some snapshots of this, the IR? So when Graal gathers runtime information and then specializes the graph to take this one and then run it through SymJEx instead of running the initial one, which will have all the branches?
It should be possible. The problem is we don't use a specialized graph because we want to explore all paths and not only the specialized one.
Okay, yeah,
there's some work in the background where they want to optimize, for example, LVM has type information, so we can optimize it before compilation, but that's work in progress for now.
Okay, thank you very much. Any more questions from our Zoom attendees or from Slack? I hope I didn't skip anyone from Slack. So of course, we will have a separate channel in Slack to ask more questions, elaborate more during our hallway break. So I would like to thank Thomas for your presentation and for answering the questions. And then we will go ahead and continue our presentation. The next one is from Jim Bauwens, titled From Causality to Stability, Understanding and Reducing Metadata in CRDTs.
Hello everyone, my name is Jim and I'm a researcher at the Software Languages Lab at the Vrije Universiteit Brussel. And today I'll be talking about my work from causality to stability, understanding and reducing metadata in CRDTs. So first off, I'll talk a bit about replication. Nowadays, a lot of distributed systems replicate data in order to achieve higher availability. And this is possible because if some information is replicated over several components, if one component fails, another component of the system can take over. Additionally, replication means that users can access the closest server to them, which will introduce dropped latencies and higher, faster connections. Ideally, you'd have that all these replicas are strongly consistent with each other. And what do I mean with this? Well, that if I perform a write to a particular replica, that all successive reads to other replicas will return the same value. Practically, this is really hard because this means that when you're performing a write, you'll have to log all replicas. And of course, this introduces higher latency, synchronization waiting times, which then again hampers your availability. So in the real world, what you mostly do is you will want to lower your consistency guarantees. And one way to do this, for example, is by using eventual consistency. And eventual consistency says that temporarily replicas might be inconsistent, but eventually, if all updates stop, they will end up in the same state, in a consistent state. And something that takes advantage of this are CRDTs, or conflict-free replicated data types. And basically, they are a family of replicated data structures where replicas can be updated independently and concurrently. In this case, replicas may temporarily diverge, but we know that eventually, if all updates stop, they will converge to the same state. So let me give an example of this to clarify this a bit. So imagine we have a counter CRDT. A counter could be, for example, the likes on a Facebook post. And say we have two replicas and we add some likes to the server in America. Concurrently, we add also some likes to the server in Asia. And you can see at this point that our states differ. However, once we propagate all updates, we will end up in the same state, in a consistent state. And this is possible with a counter because the add operation is commutative. Now, of course, for a lot of data structures, their operations are not commutative, but there are a lot of research has been done to figure out how this can be applied as well to other more complex data structures. So I'll highlight this for a set. So let's say we want to replicate a set. So we have three replicas, A, B, and C. And let's say we want to perform an add operation to this set. So let's say we perform an add operation on replica A. We add element X, and concurrently on replica B, we do the same, but we add element Y. Now this can be propagated to replica C. And of course, replica C can receive these updates in a different order. But of course, because we have an unordered set, because sets are always unordered, it doesn't matter, and we will always end up with a set which contains X or Y, regardless of in what order we receive this operation. So far, so good. Seems we can replicate a set. But the real problems start when we introduce removes to the mix. So let's say at replica A, we add an element Z. Concurrently, at replica B, we add Z as well, and then we remove Z again. Now, if these operations are propagated to replica C, then the state of C will depend on in what order it receives these operations. If it first receives the operations from replica A, that means that the remove from replica B will be lost and our set will be empty, because the remove from B will remove the Z from A. If you first, however, receive the operations from replica B and then the add from replica A, we'll end up with a set containing the Z. So you can see that we can already run into inconsistencies here. And the key problem here is that the remove actually is unable to identify what set it should remove. So the one way to solve this is basically by making every operation unique. And you can do this by tagging every item that is added with a unique identifier. So let's do that. So here you can see that now when we add an element set to the replica at A, we tag along some unique identifier, in our case A2. We do the same at replica B, so when we add B, we generate a unique identifier B2. And the key to this here is that when you remove an operation, you will only remove the items with identifiers that you have observed. So in the case of B, because it never observed because it hasn't received yet the updates from replica A, it will only remove the Z, but B2 edition. So if this is then propagated to replica C will always end up in a state where it contains one Z element, albeit the A2 edition, because the remove did not affect this, cannot affect this identifier. So of course this unique identifier is hidden to the end user, so you just have a set with C. But now we have a set which we can replicate and where the ordering doesn't anymore matter. So this is what we call actually an observed removed set, which is a particular kind of CRDT where only observed elements will be removed. This is really cool, but it actually introduces a secondary problem, namely that you have to now have some extra bookkeeping for all these unique identifiers, and this can lead into several memory issues, which I'll now explain with another example. Imagine we have a replicated set, and we will add some items to this set. You can see that when we add an item that indeed our state, say we add X, our state now contains X. Internally, in our representation in memory, so what's not visible to the developer, you can see that this element X is tagged with a unique identifier. Now, if we perform the operation again, of course, our state doesn't change because a set can only contain an item once. But internally, because all our operations are unique, we still need to keep track of this information. We can still add other items, but another problem arises once we remove elements. Again, we cannot remove these internally because we need this information if we receive maybe concurrent operations to have a correct ordering. So the problem here actually is that while our visible state, the state visible for the developer, can shrink, in our internal representation can grow unboundedly, which is of course problematic if you're having low constraints and more. So what you want to do is, of course, remove this metadata whenever possible. So in order to remove this metadata, you first have to understand why it's needed. And in our case, basically to ensure that operations can be commutative, that you can have that regardless of the ordering, you will end up in the same state. And actually, more correctly, is to ensure that concurrent operations are more are commutative. Now, of course, when an operation has been observed by all replicas, meaning it has been applied to all replicas have received the operation and applied it, there can no longer be concurrent operations to that operation because everything will follow it. And we call this state causally stable. So when when all replicas have performed that particular operation. And in that case, because we can no longer have concurrent operations, the metadata is useless and could be removed. Baquero et al. Show in 2017 how causal stability can be determined by comparing causal clocks of operations. So basically, instead of using unique identifiers, they tag every operation with a vector clock, and they use these vector clocks, and by comparing these vector clocks, you can see what nodes have observed a particular operation already. Because if all replicas return vector clocks which have a number which is higher than that when the operation was performed, you know that they have already observed it. So they use this technique in their pure operation-based CRDT framework. And what's nice on this framework is that, well, they actually use a log-based approach. So instead of somehow in a complex way storing the state of the CRDT, they just keep everything in a log along with the timestamp. So every operation is just added to the log, tagged along with the timestamp, and to compute the state of this log of the CRDT, they will just iterate over the log. Now, of course, when an operation becomes stable, you want to remove it from the log or make it a bit more compact. So what you can do is you can have a sequential data structure where you put these stable operations in, and then you remove all extra metadata, tags, logical clocks, and you will have a much more compact state. And in that case, then your state of your CRDT is basically your sequential data structure plus your log. And what's interesting about their approach is that they actually rely on the fact that they have a reliable causal broadcasting layer or middleware. So with reliable causal broadcasting, you ensure that all your operations are causally ordered and that you have reliable delivery. And this is something that's used a lot in middlewares. And they basically piggyback on the vector clocks that are already flowing in the system to determine these clocks, which you can use in their log. Now, is this a complete solution? Well, no, not quite, because there are actually two problems with this approach. First of all, in order to determine causal stability, because you have to look at all the clocks, this means that all replicas need to regularly propagate new updates because you need information from these clocks to be able to know in what state they are. Secondly, because they're using reliable causal broadcasting, they're enforcing causal ordering on all operations, and this may actually hamper the reactivity of a CRDT needlessly. To explain why these are really problems, let me show this with a couple of examples. So we performed an experiment on several systems with 2 replicas, 4 replicas, and 8 replicas. And all these replicas were replicas of a remove win set or reset. And the idea is that we're constantly adding items to these sets, to a particular item, to a particular replica in the set. and every 100 operations we switch this replica. So in the case of the system with 4 replicas, we first add 100 items to replica 1, then we switch to 2, then we switch to replica 3 and 4, and then we start again. And this ensures that we have enough causal information flowing through the system so that we can determine causal consistency at all. So what the graph shows is the number of entries in the log. And what you can see is that it can take quite some time before items are removed from this log, depending on the number of replicas in the system. And this can be quite problematic because if you have a low memory constraints, you wouldn't want this to affect you. So what you can see is that we have this zigzag pattern, and this is because, well, every 100 operations, enough causal information is available because you switch to the next node. And the grow in the beginning is because you first have to complete an entire cycle through all replicas to have, well, yeah, enough causality information. Secondly, for hampered reactivity, I will elaborate on this with a small example. Imagine we have three replicas, A, B, and C, and there's a disconnection between replica A and B, meaning that no updates can be propagated between these replicas. So let's say we perform an operation on replica C. This is properly propagated to A and B. They can add it to their log, no problem. But this is not the case when we do the same on replica B. The update, when we apply an update on replica B, it will only be propagated to C. And if we then perform an update on replica C, and this will be propagated to both A and B. However, A will have to buffer this operation because A can notice in the causal information that's flowing in the system that it's missing a causal dependency from B. So let me highlight this by actually showing the clocks in the system. So you can see for the operation Z that there's this 1 on the second index, and basically that's the causal dependency for operation Y. So A can see that it's still missing something, that it hasn't received the operation which causes increment, so it will wait and buffer operation Z. And of course, once the connection is restored and operation Y has arrived, then operation Z will be applied. Why is this a problem? Well, if Z wasn't actually dependent on Y, I mean, maybe there was a causal dependency, but maybe in reality they were totally unrelated, and then actually we waited for nothing, and we could have maybe had a more updated state, plus we could have used the information to perform possibly some metadata removal. So that was impossible now. Our approach to tackling these two problems is, well, one, we'll introduce a way in how we can eagerly perform metadata cleanup by actually by being faster in determining causal stability. For improving the reactivity of CRDTs, we'll show a way for opening up the reliable causal broadcasting buffer so that information from here can be used to compute state information. So to determine causal stability sooner, what we do is we rely on the fact that we have reliable delivery as well as causal ordering. Because pure operation-based CRDTs, recall, they used reliable causal broadcasting. Reliable causal broadcasting doesn't only give you causal ordering, but also reliable delivery. And we can use this because, well, let's say I propagate an update, broadcast an update to all your replicas. Because we have reliable delivery, you will respond with an acknowledgement saying that the operation has arrived, has been delivered. And actually at that point, I already can know that the operation is stable because everyone has acknowledged it, because that means that everyone has received it. So, but of course, at that point, only I know the fact that the operation is stable, so I will broadcast this to all other replicas. And of course, you don't want to do this for every operation, but that's why we allow you to set like an interval for every 10, 50 operations, we only send a stability message, or if the log size reaches a particular size. To reify or open up the buffer, we introduce an incomplete partial log. So recall that our state of our CRDT was computed by one having a sequential data structure and the log of the pure operation-based framework. And now we still have additionally this incomplete partial log, which represents basically the entries in the buffer. And with this, you can compute a new state or a more up-to-date state, or use the information to clean up the log. For our implementation, we all implemented this in Fleck. And Fleck is a middleware I'm working on, a framework I'm working on for my research, which allows me to create simple peer-to-peer applications and easily work and extend CRDTs. So I have here a small code snippet to make a new replica, CRDT replica in Fleck. Basically, you just have to instantiate the CRDT type and pass along a special tag name, here shared counter. And once you do this, it will be automatically linked with all replicas in the network with that same tag name. So it's really easy to quickly perform some experiments. So what we do have here in Fleck is we have a layer for reliable causal broadcasting, then we have a pure operation-based layer, and then we have the layer where you can implement any concrete CRDTs on. So for the eager approach to garbage collection, we first have to start by extending the reliable causal broadcasting layer. And basically what we did is, once we broadcasted all our operations, we waited till we get all acknowledgements back, so that when the operations are reliably delivered, and then basically we'll update our clock locally to basically mark the clock as stable. And if we meet a certain interval, so maybe every 10 operations or 50 operations, we'll broadcast this information to other replicas. Of course, we don't here implement an actual semantics of the CRDT, so we provide some abstract operations methods that have to be implemented for this, such as on operation and GC stable, which can be used to add semantics to the CRDT. And we have some extra methods like is causally stable or perform pending stable message that can be used to poke with the stability message themselves. So we use this basically in our pure operation-based CRDT framework. We extend the on operation basically to construct a log, etc. And then we use the GC stable to check when items in the log may become stable. And of course, again, on top of this, you want to build your actual pure operation-based CRDTs, such as add win set, remove set, and that you can do with the following abstract methods. So I'll give a quick example of the implementation of a remove win set, which builds on top of this then. So first thing what you do is you define what operations your CRDT can use. So here in our case, our add, clear, remove. Then we extend the PO-log class. We have a basic constructor, and then we start with implementing the methods of the pure operation-based CRDT framework. And here we have is redundant by operation and is redundant by log, where we define what entries in the log or new entries may become redundant by other existing entries. So to give a really quick example of a small part here, imagine we receive a new add operation for add x, and we already had in our log somewhere an existing add x, which was preceding in logical time the new one. Well, it's redundant. We don't need it anymore because we have a new one replaces it. So that's what we check here. If an existing member precedes a new one, and the existing has the same argument, so x as a new one, well, remove it. Besides doing this stuff, of course, what we want to do is we want to compact our log if it becomes a bit more. We want to compact our log if it becomes a bit more, if it grows and if elements are stable. So we do this with set entry stable. Basically, whenever an entry becomes stable, we'll take it and put it in our sequential data structure. So you can see here, basically, we put it in a simple TypeScript dictionary. Of course, you have to keep this part consistent with the rest of the log. So whenever a new operation arrives, we will check if the information in the sequential part is still valid and if it has to be cleaned up. Finally, if you want to observe the state of the CRDT, you will have to combine the sequential port and the log, so that you do in two lists, the bottom listing where you basically just iterate over the log and add it to the sequential port. For our reified open implementation, again, we had to extend the RCB port, reliable causal broadcasting port. Basically, we added some operations like on-buffered operation, get buffer data to hook into whenever when there are events on the buffer, and we use this in the pure operation-based log framework to expose new buffered operation, and it's redundant by buffered rate operations, which can be then used to check redundancy in the log and more, and basically just collect and remove metadata when needed or modify the state. For our evaluation, what we did is we had several questions. So basically, we wanted to compare our approach to the vanilla pure operation-based CRDT and see how our log size changes, so what elements are removed. And we wanted to check what the overhead was for using this method, and what the effect was of using the log size as heuristic. So first of all, we measured our log set in several different situations. So the blue line on top is the traditional approach, and it's actually the experiment we performed before. So we kept adding items. So we have a system here with 4 replicas, and we're keeping on adding items. Every one of those operations we switch. And you can see that the 2 bottom lines, which represents the log size in our approach, is definitely lower. The red line is when our interval for stability messages is every 50 messages, and the green one every 10 messages or operations. So you can see that our approach indeed helps keeping the log size down, which means that we can have a reduced number of metadata going around. Of course, we have a higher network consumption. So you can see here in this graph, which is the graph representing the number of messages sent over the number of operations in the same experiment as just before. You can see when our interval is set to 10 operations, it's of course higher than the one when you have an interval of 50, or even higher when you have no interval at all, as is the case with the vanilla approach. And so it's very important here for your developer to set trade-offs in how many messages he wants to send when you want to send a stability message, which you of course can do with the methods from the RCB layer. Additionally, you can set a limit to your log size or a trigger whenever your log size reaches a certain limit. And in this graph, you can see that when we had an interval of 10, we set the log size limit to 25, the trigger size to 25. And for an interval on 50, we set our log limit to 75. And you can see it does indeed, compared to just only using a particular interval, it indeed still improves the memory consumption a bit more. So to conclude, we showed you an eager approach to memory management. So we show how you can use reliable delivery to compute causality earlier, improving memory consumption. And we show you how you can easily improve the reactivity of your CRDTs by actually reifying the buffer of the reliable causal broadcasting layer and using this for to define the semantics of your CRDT itself. So future work is we want to have, of course, a more efficient implementation of partial logs and a formal model of the system, and because we want to verify the correctness and ensure that future extensions will be correct. Thank you for listening, and if you have any questions, you can contact me with the details below, or I'll be available here in the MPLR channels. Thank you.
Well, thank you very much, Jim, for the very interesting presentation. As usual, we'll take questions by raising hands on Zoom or from Slack. So we have a couple of questions on Slack already. The first question is from Stefan. He's asking whether CRDTs is something that one could benefit from an environment where somebody has a reliable communication without the typical distributed systems failure.
Yeah, so it's a good question, and the answer is yes, because one of the things is if you're, for example, in an environment with a lot of nodes, you still might want to avoid putting locks, because he's adding locks, locking a system because you either choose, either you have strong consistency or eventual consistency, right? Or something in between. But the thing is, if you want a strong consistency, then you have to use lots of locks. And if you have a lot of low embedded devices that are communicating in a particular network, you might not want to do that. So in this case, with CRDTs, you could you can have, without locking, some synchronization constructs where you will have to have a lot of less communication in between. So it might be more you might have a more smooth data structure, which is more reactive. I hope that answers the question.
Stefan is typing, so probably he will follow up on that. I think you touched a little bit on low power platforms, and this is the second question from Thanos. And we're going to circle back to Stefan. Thanos is asking whether there are any specific challenges in terms of reliability or consistency posed by the integration with low power SoC platforms like the ESP32 that you mentioned in the paper.
Yeah, another good question. So indeed, there are quite some questions that are need to be answered when implementing. So right now, I am porting my framework, and well, I have a port for the ESP32, and you have a low amount of memory in it. So the difficulty here is getting your framework to even work properly, because you have these low memory constraints, and you want to make sure that you can store these data structures and the related related constructs and everything, because you have to also tag along. If you manage your Wi-Fi stack, and all these components have to be part of this, so you're using memory for your Wi-Fi stack or for your Bluetooth stack if you're using that, and all these interactions can be quite hard. So it's an optimization challenge already, and then of course you never know. So right now I'm also running into some problems with garbage collection on the devices themselves, because not all VMs that are capable of running can easily perform these things. So there are quite some engineering challenges to it, and of course these engineering challenges translate into practical aspects that might have to be thought about when putting a CRDT on the platform.
Yeah, and Stefan is following and with a question that I was going to ask. So that he's asking whether CRDTs could be complement to things like software transaction memory systems. I did my PhD on distributed software transaction memory systems, and I relate to your discussion here. So I would be very interested to know what your opinion.
Yes, there is actually ongoing work also at our university on mixing consistency levels, so that you have mixed consistency, and in some cases you have strong consistency in transactions where needed. In other cases where it's not needed, that you can switch over to eventual consistency, so you have higher reactivity. So there's ongoing work on checking on what ports can be eventually consistent and what ports must be strongly consistent, which can then, for example, use transactions. And then you can have, for example, get the benefits from eventual consistency, that some ports can be more reactive when needed, but some ports can be definitely very with transactions, and which might be important for example, bidding and all these sorts of things. So yes, the answer is yes, there is ongoing research, and it's a very interesting topic to go into.
That's very interesting, and I mean, I want to follow up on that. So, how would you? I mean, what would be the threshold where you should switch between a transactional-based approach versus, let's say, more relaxed-based one? Is it based on the criticality of the data, or like another you define?
And so, this is not my research, so it's my colleague who's looking into it. But he has, for example, he set several invariants on the data, so he tries to ensure that particular information conforms to certain rules, and then with some statistical analysis you can indeed check that these rules are still applying, while trying to get the most flexible reactive approach. So you will try to optimize towards having, well, low memory, low network bandwidth by having more eventual consistency, but you will also want to ensure that these invariants are still always guaranteed, and that's when you will want to maybe use a transaction or not.
On this topic, Stefan has a follow-up question regarding if you have any experience between the performance trade-offs around locks, STMs, and CRDTs in a shared memory system setting.
No, I don't have experience yet. In the shared memory system, I haven't tried to, so I presume you mean like locally, where you really share. No, I haven't tried yet, experimented with that. I mostly just experiment with networked nodes.
I have one last question. It's a bit, maybe a bit naive and technical. So the approach you described is based on the fact that you have, let's say, some clocks, like tagging the data, and then you use these clocks to understand the redundancy by comparing the timestamps. And the question is, how do you guarantee a shared clock between all replicas?
No, so your clock, what clocks we use are vector clocks. So we only can construct basically a partial ordering. So you have your causality information, so you have all your happened before relations. So you know these are, you know that certain operations will be partially ordered. And then you have, of course, the concurrent operations where you cannot apply a particular order. And for these operations, then you have to implement your particular semantics. For example, for remove win set, you will say, if I receive a concurrent operation, and in my log, for example, I already have an add, and now I receive this concurrent remove, then this add operation, which is in my log, is redundant. And then the remove wins, which is how I get the remove win semantics. So that's the thing for CRDTs. You will always want to pick a particular semantics that fits your use case, either add wins or remove wins in the case of a set. And that's how you will have to deal with these concurrent operations, by basically saying what concurrent port will win or trump over the other concurrent operation.
Okay, so in that context, there is no draw. It must be a winner always, right?
Yeah, so you will, for your concurrent operations, you will want to somehow have a particular ordering, which then, of course, is important for the semantics of your data structure itself.
I see. Thank you. Any more questions from Slack or Zoom? I think if we do not have any more questions, then of course we can take our lunch break, and then in parallel we can visit our visual hallway where we can have additional discussions per paper, and we will resume at 1 o'clock UK time for our next session regarding managed security. So have a nice break, and we'll see you in 90 minutes.
The reasons you should work at ARM are, first, technology, right? The massive impact it's had on the world. And you can see that from the 2,000 people we were a few years ago to the 6,000 we are today. Secondly, it's got an awesome benefits package. Next year I go on a month's paid sabbatical. And thirdly, the people are really smart, so they challenge you, and actually, more importantly, they're really nice. So they're really fun to work with.
If you want to work on technology problems that affect everyone, and you want to do it in an open, trusted environment where you'll be empowered to get on with your job, then this is probably the right company for you.
Definitely, ARM has changed me as a person. I've opened my mind up to an awful lot that I'd never come across before. It's been an excellent experience.
There's a very nice culture where the emphasis is on the engineering, the quality of the engineering, and indeed the welfare of the engineers.
Looking after my own mental health is something that's really important, and I think ARM gives me a good ability to do that.
There's kind of never a dull day. I'm never kind of working on the same project for too long.
I was in the Budapest office last week, the design centre, and I noticed a poster. It said, "Great minds don't think alike." And I just smiled when I read that, because that's exactly what it's like working at ARM.
Racing, a competition of speed set against an objective criterion, usually a clock. It is where the fastest wins, where the stopwatch doesn't lie, and success or failure is measured at the checkered flag. But for those who live racing, it really is more than just a race against the clock. The tension, the drama, and the unpredictability of the race, all of this adds to what racing really is. In racing, respect is earned the old-fashioned way, and greatness is built one victory at a time. Out there you are alone, with nowhere to hide. Any sign of weakness and you will be exposed.
And then neck and neck coming into the corner. He's down!
Lose focus for a single moment, and you will face the full wrath of the laws of physics. When the weight of the world comes crashing down on you, will you quit? Or will you dust yourself off and keep on fighting? Racing is where history is made, and where champions rise from the crowd, accepting all challenges fearlessly. Champions aren't only measured by what they have won, but by what they have overcome on their road to glory. Without obstacles, tough battles, and pain, victory is empty. So what is racing then? Racing is 100% commitment to everything you do. At KTM, racing drives us and makes our world turn. This is the world that awaits you. KTM, ready to race.
Okay, welcome everyone. Welcome to session 2 of MPLR. This session is about managed security. We have 2 papers in this session. The first paper is by Daniel Pikarek, and he's gonna talk about TR-CView and interactive architecture agnostic execution trace analysis.
Welcome to the presentation about TR-CView, Interactive Architecture Agnostic Execution Trace Analysis. My name is Daniel Pikarek. Imagine you have a program and the program is buggy and it crashes, and your task is to figure out why it crashes. You will probably use a debugger, for example a traditional debugger like GDB or R2, and in a traditional debugger you can run the program and halt it at any point in time, and then inspect memory contents and register values. You can then single step through the program, which means run the program instruction by instruction or line by line, and you can also set breakpoints. So you run the program, and once it reaches the breakpoint, it halts, so you can continue with analysis there. But this is not exactly efficient because you will probably have to run the program over and over again, and you might have to interact with the program, so it's quite time consuming. An improvement is record and replay debugging, where you run the program only once and you record an execution trace. And then using the execution trace, you can replay it in the debugger and basically debug the same program run over and over again. But it still does not really solve our problem, because what we really need is a way to go back in time, because once the program crashed, we want to know why it crashed. That's what reverse debuggers do, like for example RR. They are again based on record and replay, so you run the program once, and then you can replay it in the reverse debugger. In this case, it means you can go directly to the program crash, and then you can go back in time step by step and try to figure out why the program crashed. There is still a small limitation. In a reverse debugger, you can usually only go forward and backward, but you cannot jump arbitrarily. Some debuggers which implement random access to the execution trace exist, for example like Kira, and some people call this timeless debugger. A different area where also debuggers are required is reverse engineering. Imagine you are given a program, just a program, a compiled program, and you have to figure out what the program does. If you run it in a debugger, you can observe the behavior, and this is usually called dynamic analysis. In both cases, you want to use a timeless debugger, but if the program that you have to analyze is for an architecture that's not supported by your debugger, you have a problem and you cannot use your debugger. Extending a timeless debugger is usually not simple, so what you need is a tool that can easily be extended. It's even worse if you are debugging interpreters or virtual machines, or especially programs running within interpreters or virtual machines, which might be written in some custom bytecode, or if you're working with an emulator for some hardware architecture, CPU architecture, it's also possible that this is not supported by current tools. In this case, you want a timeless debugger that can easily be extended to any architecture. And this is exactly what our work, TraceView, focuses on. It implements a timeless debugger using execution trace analysis that can easily be extended to any architecture. We assume that the program execution trace is already recorded, therefore we only focus on the analysis part. Our approach is split in two parts, an architecture-specific part and an architecture-agnostic part. In the architecture-specific part, the trace file is parsed and the events from the trace file are transformed into so-called generic events using an architecture module. A generic event has the same structure for every architecture, which means architecture-agnostic analysis algorithms consume these generic events. These analysis algorithms create internal data structures, for example, to reconstruct memory contents, as well as to parse an execution tree, which I will explain later. The user can then interact with the internal data structures and also annotate them if necessary. But which generic event types do we need? First of all, we need step events. A step event corresponds to the execution of a single instruction. Therefore, a step event stores the executed machine code, disassembled machine code, as well as the program counter, a timestamp, and all register values. We also need memory access events. Whenever the program reads from memory or writes to memory, this is stored in a memory access event. And we also need memory management events. Whenever the program allocates memory or frees memory, this is recorded in a memory management event. These three event types are technically sufficient to analyze Linux user space programs, and in related work, for example, the Kira timeless debugger, only these three event types are used. But we want to debug also system level software like operating systems, and we want to debug and analyze programs that directly run on bare metal hardware without any operating system, so we need a few more events. First of all, we need I/O events. A Linux user space program usually has standard input and standard output, and it can use that to communicate with the user. Some embedded systems might have a serial line for communication, where messages can be passed to the user. In any case, these messages can be recorded in I/O events. We also need trap events. Traps, or exceptions, or interrupts, are a mechanism in a CPU that allows the CPU to interrupt the currently running program and invoke a predefined subroutine. For example, if the program performs a division by 0, a trap handler might be invoked. Or if the program wants to request services from the operating system using system calls, this might also invoke a trap handler. And finally, if you press a key on your keyboard, this might interrupt your CPU and again invoke an interrupt handler. All these events can be recorded in trap events. We also need device events. Imagine you want to analyze a program that's running on a system with a hard disk, and it accesses the hard disk. So it sends a command to read some sector from disk. This command can be recorded in a device event. Once the hard disk finished reading the sector, this again can be stored in a device event. Device events are extremely useful for navigation through the execution trace, because if you know that the program interacts with hardware, you can directly jump to the right location in the trace. We also need symbol events. Imagine the program dynamically loads code at runtime, like for example a dynamic linked library, or maybe it even generates code at runtimes, and maybe there is symbol information for this code. This symbol information can be stored in symbol events. If all symbols of the program are stored in symbol events, the program file itself is not necessary during analysis anymore. And finally, we need memory dump events. Whenever large amounts of memory change, this can be efficiently stored in memory dump events. For example, if a memory mapped file changes, or if external hardware which maps some information into memory changes the mapping, this can be efficiently stored in a memory dump event. As you might have observed, some events seem to be redundant. For example, memory management events could be derived from step events because, for example, on Linux, system calls are used for memory management, and the same for I/O events. But since this approach is architecture agnostic, all these events are modeled as individual events, and the architecture module can derive these additional events if necessary. But we don't always want to develop an architecture module because this is time consuming. So there is also a way to store an execution trace in the generic trace format. The generic trace format consists of an architecture definition header. In the architecture definition, all the registers of the CPU architecture are defined, including register names, register sizes, and also the location of registers in the following step events. The endianness is also stored, rather the default endianness, as well as the size of addresses, words, and the number format. Number format in this case means hexadecimal or octal or maybe even decimal, which is used to represent numbers. Following the architecture definition header, all the serialized events are stored, which are essentially just the generic events. Remember that we don't have an architecture module here, so all the various events have to be stored, and it's not possible to derive some events from other events. Also remember that, for example, step events store the machine code and disassembled machine code. Since we don't have an architecture module here, both information have to be stored in the step event. And this means there is a certain overhead with the generic trace format. How do we actually display the execution trace? In a traditional debugger, the program code around the current program counter is disassembled and displayed. So basically you see the code of the current subroutine. And if there is a call, you can step over the call or step into the call. In related work on trace analysis, this works completely different. On the left side, we see a trace file, or rather the step events of the trace file illustrated using the disassembled machine code. This is roughly what is displayed in related work. So you just see the flat execution trace, and if there is a call to a subroutine, you see all the instructions that belong to the subroutine too, even if you're not interested in the subroutine. This is why we chose a kind of hybrid approach, which means we parse the execution trace into a tree, which we call execution tree. The algorithm works as follows. It parses all the instructions, and if it's just straight line code, it puts it into the current node in the tree. Once it sees a call instruction, it creates a child node for this call instruction and attaches it to the call instruction. And then all the following instructions are attached to this child node. And once a return is reached, the algorithm continues at the previous node again. With this approach, we basically have the features of step into and step over in the trace analysis. So we can quickly see what is going on in the current function, and if we're interested in the subroutines, we can also look at the subroutines. Subroutines are usually not interesting if it's, for example, library code. But these subroutines tend to be long, so we really want to have this step over functionality. Of course, we are not only interested in program code, we are also interested in memory. We assume a flat memory layout, and memory is split in pages. Whenever the program allocates memory, we allocate pages. Pages store metadata, for example, the file name if the page corresponds to a memory mapped file. It also stores access permissions, and most importantly, every page has two lists, a read list and a write list. All the memory access events are put into these lists, sorted by time. If we then want to know what's the current value at the memory location at some point in time, we can use a binary search on the list to find the most recent write event. And if we're interested in when this memory location is going to be read again, we can use binary search on the read list to find the next read event. We implemented a user interface which roughly resembles a traditional debugger, and in the center we can see the execution trace. As you can see, calls are just displayed as call instructions. The instructions belonging to the subroutines are not displayed. Below the execution trace, you can see the strace, which is similar to what the strace utility on Linux outputs. It's the system calls that are executed so far, as well as the system calls that will be executed in the future. Using system calls, it's quite easy to navigate through an execution trace. System calls are decoded using an architecture module, which provides a system call decoder. On the left side, we see a symbol table. Remember the execution tree? It corresponds to subroutines. And of course, we can use this information to derive a symbol table. Combining the symbol table with symbol events, we finally get the symbol table that we see on the left side. Below the symbol table, we see a stack trace. The stack trace is basically the path on the execution tree leading from the currently selected instruction back to the root node. On the right side, we see the current register values with changes indicated in red, as well as the memory contents at exactly this point in time. It's worth noting that calls are decoded, so you can quickly see the arguments that were passed to subroutines. This decoding happens again in the architecture module, which provides a call argument decoder using the system calling convention. And of course, we can also add our own comments to the execution trace, because this makes it quite easy to keep track of what we already looked at and so on. We said our approach is architecture agnostic, so of course we implemented a few different architecture modules. First of all, an AMD64 architecture module, because AMD64 is a widely used CPU architecture on computers. We also implemented an architecture module for PowerPC, because PowerPC is a RISC architecture and it's easy to implement. It also has a few interesting features, for example, conditional calls and conditional returns, which are interesting for the parsing algorithm of the execution tree. And finally, we also implemented PDP-11, which is an old 16-bit CISC architecture that was widely used in the 70s and 80s. We chose PDP-11 because no current tool supports such an obscure architecture. We also evaluated our approach and challenges from capture the flag competitions. Capture the flag competitions are usually online competitions where you have to either reverse engineer a program, which means you are given a program and you have to figure out what the program does, or you have to find a bug in a program and then use that bug to make the program do something it's not supposed to do. There were two interesting challenges. One of them was a virtual stack machine, and we had to reverse engineer the bytecode and then write a custom program for this virtual stack machine. Of course, there was no way to easily debug our program code that we were supposed to write. So we instrumented the virtual stack machine interpreter to output an execution trace in the generic trace file format. We were then able to use TRC view to analyze this execution trace. It's worth noting that TRC view assumes a register machine, but this was obviously a virtual stack machine. So we had to map the virtual stack machine architecture to a register machine, which is rather trivial because all you need is a program counter, the top of stack register, and the operand stack can then be mapped to memory. Another interesting challenge was where we were given a text trace. Basically, some program was recorded as an execution trace, but this execution trace only consisted of disassembled machine code. So we had a big text file and line by line the executed machine code. We transformed this into the generic architecture trace format and then loaded it into trace view. Trace view reconstructed the execution tree, and using the execution tree we were able to quickly understand what the program does so we could solve the challenge. Of course, we evaluated TRC view also on real-world programs. So for example, we recorded a run of the GNU C compiler called GCC, or rather the backend of the GCC compiler, which compiles C code to assembler text. Running this on a Hello World program creates an execution trace of about 3.7 gigabytes with about 58 million steps. Loading it on a ThinkPad T580 takes about 100 seconds time, and in the end TraceView consumes about 11 gigabytes of memory. Of course, this also works with other tools like, for example, the GNU assembler, and running it on an assembler text file with about 11,000 lines of code creates an execution trace file of about 4 gigabytes with about 65 million steps, and loading it takes about 2 minutes. If you run this on many more tests, you will realize that this scales roughly linear, but there is a limitation, of course, and that's memory consumption. As you can see, memory consumption is quite high. That's because everything is kept in memory, and this also limits the trace file size that we can actually analyze, which already leads to the future work. Obviously, we will have to make this approach more scalable by implementing some kind of database system to store the in-memory data structures on disk. With this approach, it will be possible to analyze much bigger traces because only the information that's required right now is loaded in memory and the rest is stored on disk. It's basically just a serialization problem for the internal data structures. But serializing this data has to be fast, as well as loading the data also has to be fast. The next big thing is compression. Of course, right now execution traces are compressed using delta compression, so only information is stored that changes between step events. But it would be interesting or useful to use more advanced compression, for example, something like gzip. Even gzip already achieves a high compression factor of about 80% when performed on an execution trace right now. Remember the analysis of the virtual stack machine and the program running within it. It's not always easy to instrument code, or rather an interpreter. So sometimes it's easier to just record the whole interpreter with the program running in the interpreter. And then it would be useful to extract the execution trace of the interpreted program so we can analyze the interpreted program. Parts of this are already implemented, but it's not yet finished. And of course, literature describes many different automatic analysis algorithms. For example, automatic type recovery, or taint tracking, or even pattern recognition in a program execution trace, or even something like entropy analysis to find, for example, compression algorithms and encryption algorithms. Many of these algorithms can be ported to TraceView and made available on all architectures. Thank you for your attention.
Great, thank you, Daniel. So we're ready to take questions. As usual, we're gonna take questions from Slack. Meanwhile, I see Stefan is writing. Meanwhile, I have a question. Is Daniel is available? Yeah, is available.
Yeah, sure.
So,
Can I start with the questions, please?
Yeah, of course.
So,
Christos, yes.
okay. Okay, I wanted to ask Daniel. So I think one of the, probably, as you mentioned in your presentation, one of the scalability reasons for TRC view is the fact that you have to save essentially the whole state, right? The register files and the memory, and then you have to load it into in-memory and then do the step-by-step. So have you considered to do a hybrid mode? So you have a simulator running underneath and then use the simulator to actually reconstruct the state of the registers, at least during stepping, instead of actually saving from the whole trace for every step, the whole register file.
It's already only storing the differences between the steps, but the real problem with using an interpreter here is that it's much harder to make this work if you already have some interpreter and you want to debug code running within this interpreter. And that was one of the main motivations for this whole work.
Okay, so because by looking at it, it reminds me very much of the Maxim inspector, which it wasn't a trace analysis tool; it was like a real-time analysis tool. And then I was wondering whether a simulator could help you to avoid some of the overheads.
I mean, what other people do is they only record non-determinism in the first step, and then they expand it in a second step. That's, for example, what RR and so on does. But then again, it's tightly coupled for a specific architecture.
And one small question, to your experience, how much effort is to provide a new descriptor for a new architecture?
For a new architecture, all you need, basically, you have to define a trace file format yourself, and then you need a disassembler, and that's roughly it. And if you don't do this, and instead you use the generic format, you can do this within maybe 1-2 hours to transform your trace file into this format. And this was also relevant for the capture the flag competitions because they are all time limited. So you have in total like 24 hours to solve everything. And there you really don't have much time for programming work.
Thank you very much.
Okay, so that's related to the Stefan question that says, could you elaborate a bit more on how difficult it is to support? I think your answer covers that. And there's also, are there any difference between supporting RISC or SYS architectures in that regard? Have you seen any differences?
The biggest interesting feature in RISC architecture I've seen so far is conditional control flow like calls and returns, because the parsing algorithm for the tree somehow needs to know if this was a call or return. And then you have to add some logic in the parsing of the trace file to correctly annotate the instructions again. But that's the main difference I've seen so far.
Okay. We don't have more questions here. Meanwhile, people ask questions. I have a few. So you mentioned that one of the future work you're working or you plan to work on is to reduce overhead by providing compression. So
yes,
I wonder if you provide too much compression, your analysis phase is going to slow down. So what's the trade-off here?
The basic idea with compression was it's recorded sequentially, so you can compress it without much overhead technically and replay the same. But I did not have too much time to look into this so far. So of course you have a trade-off on, and right now with the delta compression, you already have a trade-off because at some point you have to decompress and resolve all the deltas. And if you do this in a stupid way, the performance is unusable.
Is your tool available open source? Is on GitHub?
Yes, it's available open source. There is even a link in the paper to a GitHub repository.
Okay, we'll be good also to share the link now in the chat as well.
Yeah.
Okay, more questions. I see Stefan is typing.
Can I ask one more question, Daniel, please?
Yeah.
No, this is more related because in my teaching, I use it's not a similar tool, it's completely different, but essentially it is a system that emulates ARM architecture. From what you said, Daniel, for Hello World, compiled by GCC, we are reaching around 11 gigabytes of memory. So my question is, if I would like to, from this whole program, even if it's Hello World, just to take a snapshot of that, and although I save the whole trace, I want just to display the state of the execution from one point and onwards. Is it possible to do snapshotting and then reduce the size?
This completely depends on your recording tool for the trace, but the analysis tool can perfectly deal with it. You just have to be careful if you cut away parts in the middle of a trace.
Yeah.
And the other thing you have to be careful with, of course, if you're in the middle of some subroutine, the first part of your execution trace, you will only see the tails of all the subroutines. And then at some point, you will see calls into the next subroutines again. But it can perfectly, it's perfectly fine.
Yeah, so I mean, you have to cut off in a good state, like in a safe point. So you are in a root function, and you haven't chopped something in between. But if you do that, you should be able to continue execution on TRC view from that point onwards.
Yeah, and you can even cut away parts in the middle of a trace, but that's also part of the reason why memory dump events were introduced. So you can kind of run the program and see the initialization, because that's maybe interesting for your analysis. Then there is some part you're absolutely not interested in, so you can cut that away. And then you make a memory dump event to inform the tool about all the things that changed in the meantime. And then you continue with the trace, and the tool can handle it. Of course, the tree might degenerate a bit.
Thank you.
Okay, I think time is up. We can take over the questions in the next session, the Ask Me Anything session, so we can jump to the second paper. So the second paper of the session is by Jakob Kreindl. I hope that's the right pronunciation, otherwise my apologies. And he's going to talk about multi-language dynamic time analysis in a polyglot virtual machine.
Hi, my name is Jakob Kreindl, and in this talk I wanted to tell you about the work we did on dynamic taint analysis. Now, let me start this presentation by giving you an example of what dynamic taint analysis is and what we can do with it. We have here some JavaScript code that asks the user for some data. It then stores this data into a property of an object. The getCode function then reads this data again, concatenates it with some string literals, and the resulting string here contains now JavaScript code that would print this data. This JavaScript code is then executed using the eval built-in. What we have here is an example of a code injection vulnerability, because a malicious user could enter code like that, which would basically allow them to execute arbitrary code. One application of dynamic taint analysis is to mitigate such injection vulnerabilities. And how can it do that? Well, in dynamic taint analysis, all data that originates from so-called taint sources is marked as tainted. Now, a taint source can be any program location that produces some sensitive data. In our case, this is user input. Marking data as tainted means attaching a taint label to it. This taint label is then propagated together with the data as the data is propagated through the program. And we call this process taint tracking. This means that when the getCode function reads the data from the property again, this read operation now produces tainted data, which flows into the string concatenation. And usually a propagation semantics would say that if tainted data flows into an operation, the output value of that operation is also tainted again. So now the string that contains new JavaScript code is also tainted. And this string is now returned from the getCode function and passed to the eval built-in. Now in our case, we consider eval a so-called taint sink. Conversely to taint sources, taint sinks are any program locations where you want to see if dangerous data arrives at it. And here you could now set any actions that you want. For example, you could just abort your program to prevent this vulnerability from being exploited. Now, this is just one example of what dynamic taint analysis can be used for, but dynamic taint analysis has actually been used in many fields. Also, why is dynamic taint analysis called dynamic? Because this taint tracking here is performed at runtime. Now, our example here consists purely of JavaScript code. And this is not necessarily realistic, because of features like foreign function interfaces, native extensions, or language embeddings that are very commonly used in modern applications. For example, the getCode function could be implemented in Python, and the object, instead of being a JavaScript object, could really be pointed to a C++ struct. Now, these kinds of language interactions, although they are common in many programs today, are a problem for dynamic taint analysis. Because consider now we would have to propagate taint from the C++ object over Python code into JavaScript code. Current taint tracking systems cannot do that. For them, the language boundary is an opaque barrier, and this is the problem that we have set out to solve. As platform for our research, we have chosen GraalVM. GraalVM is a state-of-the-art ecosystem for running all kinds of programming languages. At the heart of this ecosystem is the Truffle framework. Truffle enables the implementation of runtimes for all kinds of programming languages. GraalVM already contains such runtimes for JavaScript code, for Python code, and also for LLVM-IR. LLVM-IR is an intermediate representation that, for example, C and C++ programs can be compiled into. There are also Truffle-based runtimes for more languages available, for example, for Ruby, for R, and also for Smalltalk. Also, Truffle is open source, so you can always implement your own Truffle runtime for your own language. Now, programs that are executed using a Truffle language runtime are also aggressively optimized using the GraalVM compiler, which is a dynamic JIT compiler. GraalVM also has strong support for language interactions. This means that, for example, JavaScript code that's running on GraalVM's JavaScript runtime can easily call and interact with Python code that's running on GraalVM's Python runtime. Similarly, Python code can easily interact with C code that's running on GraalVM's LLVM-IR runtime. And actually, GraalVM's Python runtime uses this functionality to execute native extensions of Python programs on GraalVM's LLVM-IR runtime. Truffle also contains an API for program instrumentation. This instrumentation framework can be used to instrument programs that are running on Truffle language runtimes. Based on this framework, GraalVM already contains a debugger and profiler that are language agnostic and work for all these languages. However, this instrumentation framework also supports the implementation of dynamic analysis. These dynamic analysis can also be language specific. Based on this instrumentation framework, we implemented Truffle Taint. Truffle Taint is a new taint tracking infrastructure that is integrated with Truffle language runtimes and can propagate taint in programs that are running on these runtimes, which means it supports multiple languages. Truffle Taint also supports language interactions and can track tainted data as it passes from one language to another. Truffle Taint is also very versatile, which means you can use it to implement all kinds of applications of dynamic taint analysis by just specifying what kind of taint sources, taint sinks, and propagation semantics you want to use. To understand how Truffle Taint works, we first need to understand how GraalVM executes programs. We have here again our demo program, and the Truffle runtimes that would execute this code now all parse this code into an abstract syntax tree representation that looks like this. So we see here the call to the eval built-in, which has one argument, which is a call to the getCode function, and here we have the body of the getCode function. To execute this program, this abstract syntax tree, we call it a Truffle AST, is executed from top down. So the first node that actually produces a value is the literal node here, which corresponds to the left string literal that we see here. After that, the read field node is entered, which first executes the read var node, which reads this C++ pointer here. Next, the read field node takes this input and reads from this object the secret field. Then the second string literal is produced. And now that the string concatenation has all its inputs, we can concatenate these strings and return it from the getCode function back to JavaScript code. So after this call has returned, it has produced a call argument for the eval built-in. And this argument is next returned from the read arg node here. Then the eval built-in function is executed and returns. And actually, the return value of this eval built-in would now be the return value of this call. So as you can see, each node in the truffle AST represents one operation in the source code. To instrument a program that's running on GraalVM, Truffle's instrumentation framework allows us to insert so-called instrumentation nodes into the abstract syntax tree. An instrumentation node executes custom instrumentation code whenever the node that it instruments is entered, whenever it receives an input from one of its child nodes, and when it returns with an exception or with a value. Taint nodes are a special kind of instrumentation node that we implemented to propagate taint. To this end, we came up with two language-agnostic tainting techniques, which we implemented in these taint nodes, which can be used to attach taint labels to values produced by an instrumented node. Analysis implementers can themselves implement custom taint nodes to add a propagation semantics, which tells the taint node whether or not the value that's produced by the noded instrument should be tainted. In this way, analysis implementers can also implement their own taint sources and taint sinks. The instrumentation node can be targeted to the instrumented node, even without knowing its implementation, by just looking at the semantic tags and the additional metadata that this node provides. Semantic tags and metadata are already provided by the Truffle runtimes from the nodes they implement as part of their support for Truffle's instrumentation framework. Now, these tags can be language specific. For example, GraalVM's runtime for JavaScript code provides a semantic tags for binary operations in JavaScript code. Also, GraalVM's runtime for LLVM-IR code provides another tag for additions that occur in LLVM code. By targeting taint nodes to nodes that provide these language-specific tags, you can propagate taint on language level. And what is more, you can also provide separate taint nodes for separate languages, which means you can have separate taint sources, separate taint sinks, and separate propagation semantics for each language that you want to support. This feature is currently unique to Truffle taint. However, you can commonly find some operations in many programming languages. For example, most languages have a concept of literals or of reading and writing local variables, which usually have some kind of name, or also of just common unary or binary operations, which have usually a one-letter operator. Now, these operations are also often instrumented in a very similar way for each language. So we defined a set of language-agnostic semantic tags for such kinds of operations. These language-agnostic tags are provided by Truffle language runtimes from their nodes, so from the nodes they implement, alongside language-specific tags for the same kinds of operations. Now, these tags are generic enough to support various kinds of dynamic analysis, but we use them for taint tracking. And what's the cool thing about this is that these tags allow you to specify taint propagation semantics for these kinds of operations only once, instead of having to define it for each language separately. Now, these tags alone are not sufficient to really cover the entire semantics of a particular language, like for example JavaScript. But they are sufficient to cover a very significant subset of it. And we found that implementing a default taint propagation semantics for these tags is sufficient to propagate taint in non-trivial Python and JavaScript benchmarks. And we use the same taint nodes that implement the same default propagation semantics also for tracking taint in LLVM code, but here we target language-specific tags for technical reasons. Another benefit of these tags is that it makes adding support for a new language very simple. You can reuse your instrumentation that you have for these tags. All your language runtime needs to do is to actually provide these tags. Beyond that, you only have to add separate instrumentation for language-specific features that you usually do not find in another language. And here is how a taint node works. When an instrumented node returns a value, a taint node first checks with its propagation semantics for whether or not this value should be tainted. And if a taint label should be applied to this value, it then checks with the taint node that instruments the parent expression for how this taint should actually be propagated. And this tainting technique is then applied. Now, truffle taint knows two separate tainting techniques. One tainting technique it employs for values that flow into a potential language boundary. In this case, the taint label needs to flow together with this value into the language boundary. Now, whether a parent expression would actually push a value across the language boundary is known to the parent taint node that instruments this parent expression. And this is why we need to query the parent taint node. If, on the other hand, the parent taint node instruments an expression that would never push a value across a language boundary, for example, because it's just an addition or a subtraction, then we can just push the taint label for the operand directly to the parent taint node, which can store it and then use it to later decide whether the value produced by the node that it instruments, so the parent node here, should be tainted. So what are possible language boundaries? Generally, tainted data crosses this boundary in one of three occasions. With function calls, both the caller and the callee may belong to separate languages, and these languages may exchange data in the form of call arguments and return values. We see this, for example, in our running example when Python code returns a tainted string to a JavaScript call. Also, in object accesses, the source of a read, for example, as we see here, or the target of a write operation could be an object that belongs to another language. A tainted exception object could be thrown from one language and then caught in another. Truffle taint supports these kinds of language interactions using a special tainting technique. This tainting technique consists of boxing values that flow into a language boundary and unboxing values that flow out of one. And here is how that works. We have here an excerpt of our running example where a Python function returns a value to a JavaScript call. Now, in our running example, that return value is tainted. As we have already said, the taint node that instruments the instruction that produced this value now asks its parent taint node which tainting technique to apply. This parent taint node now knows that it is instrumenting a return instruction, which may move data across the language boundary. And so it tells this child taint node to use boxing as a tainting technique. The child taint node complies and replaces the value that flows into the return instruction with a boxed value. This boxed value contains both the original return value and a taint label. This boxed value is now returned in the JavaScript call. Now, truffle taint uses a common representation of such boxed values. As part of their runtime support for truffle taint, truffle language runtimes must support such values flowing into all nodes that implement a language boundary, for example, a return instruction. And such runtimes also allow nodes that implement operations that receive data from another language, like for example function calls or also object reads, to be able to return boxed values. And so the JavaScript call node now returns a boxed value. This boxed value is received by the taint node that instruments the call, which now sees that the call returned a tainted value. It didn't matter if this tainted value now came from a call to a JavaScript function or to a function from any other language. The taint node now asks its parent taint node how to propagate this taint label. If the parent taint node now instruments a language boundary itself, for example another function call, then it would again request that boxing be used as a tainting technique. But the return value is already boxed, and so nothing else needs to happen. However, if the parent taint node instead instruments a language expression that needs to understand the kind of value that it operates on, then we need to unbox this return value. This means that the taint node for the call node now replaces the boxed value with the original return value and lets that flow into the parent node. The taint label of this return value is now propagated using a second tainting strategy employed by truffle taint. A truffle taint uses boxed values to propagate taint in all kinds of language interactions. For example, also when a value would be written to an object, this means that even if another language then reads from the same field that we stored a boxed value into, it now receives a boxed value. And we also do the same for function arguments and for exception objects. One implication of this is that truffle runtimes must actually support storing boxed values in their own data structures, and they do this as part of their runtime support for truffle taint. Truffle taint's second tainting technique is applied for values that do not cross a potential language boundary. These are typically intermediate values that are discarded once the expression that they flow into has computed its result. Instead of allocating another short-lived boxed value for such already short-lived values, truffle taint instead stores taint labels for such values into taint slots. Now, a taint slot is just a container that can hold a taint label, and here is how they are used. We have here a node that implements an addition. This is a binary operation, so it receives two input values. The taint node that instruments this operation has a taint slot for each of them, so it has a taint slot for the left operand and a taint slot for the right operand. Now, as we can see, the left operand here is tainted. The parent taint node, so the taint node for the addition, now requests that taint slots be used to taint this operand. And this means that the taint node that instruments the node that produces this operand stores its taint label directly into the taint slot for the left operand. Now, as we can see, the right operand instead is not tainted. And so the taint node that instruments the node that produces that stores an empty taint label into the taint slot for the right operand. Now that both inputs for the addition have been computed, the addition is performed, and finally the taint node for the addition has to decide whether the resulting sum is tainted. And to that end, it looks into its two taint slots and sees the taint label for the left operand. Now, for binary operations, it is common to consider the result tainted if either of the inputs is tainted, so that's what we do here. Depending on what happens next to the result value, the taint node for the binary operation may now store the taint label into another taint slot, or it may box the sum value. To evaluate truffle taint, we implemented a reference taint analysis application which provides built-ins to taint values and to check if they are tainted. This reference taint analysis application uses our default propagation semantics, which targets our language agnostic tags, and it also uses taint nodes to implement taint tracking in language-specific built-ins. Now, this reference application currently supports a subset of JavaScript, Python, and LLVM-based languages that is sufficient for running some of the shootout benchmarks. Now, to evaluate truffle taint, we took some of the shootout benchmarks in versions that are implemented in C, in JavaScript, and in Python, and we extended these implementations to propagate taint using our reference taint analysis application. So here you can already see that truffle taint is able to propagate taint in multiple languages. Now the green bar shows you how much truffle taint slows down each of these benchmarks when we disable all our taint sources. This means that there is no taint to actually propagate in this case. And we have optimized truffle taint for this case, and you can see that these optimizations were quite effective, because most of these benchmarks do not experience any slowdown at all, or only a couple of %. Now when we actually introduce tainted data, this slowdown becomes worse, rising to up to 40x as seen here in the Mandelbrot benchmark in the Python implementation. To show that truffle taint can also propagate taint between multiple languages, we also implemented our selection of shootout benchmarks in versions that exercise all kinds of language interactions. Here we can see that truffle taint propagates taint between C and JavaScript, as well as C and Python, and also between all three of these languages. So where do we go from here? Our next goal is improving truffle taint's performance impact. And to that end, we want to look into how we can leverage the GraalVM compiler and all the optimizations that it can do. Besides that, we also plan to extend truffle taint's language support, including language-specific features and built-ins of, for example, JavaScript that are not currently supported. This is just a matter of engineering though, and the goal here is to be able to run more applications and evaluate truffle taint on them. In addition to these points, there are quite a few existing applications of dynamic taint analysis that we think could benefit from truffle taint's cross-language propagation capabilities. And we also want to see what else we can do with it. And with this, we are already at the end of this talk. Thank you for your attention, and if you are interested in truffle taint, I encourage you to read the paper and reach out via email if you have any questions.
Great, thank you very much, Jakob. So I have a question. I will start with a question. So when you show the results, I was impacted by Python, the overhead of Python, when you run Python state analysis. So I wonder if you have any insight about what it is. It's because obviously this depends on how good or how the interpreter is implemented. I wonder if because Python is using more intermediate values, or because Python, the Python implementation contains more language boundaries that you have to box and unbox all the time.
Actually, in terms of the number of intermediate values, the LLVM implementation would really be worse, because here, well, what we are running isn't really C code, but we are running LLVM, which, I mean, it's a low-level representation, so you have a lot more instrumentation events, and therefore you would potentially see a lot more taint propagation going on there. Really, why Python is so slow? In the concrete case of the Mandelbrot benchmark, I'm not really sure. I didn't get to investigate this particular implementation of this particular benchmark, but we saw also quite a bit of slowdown for Mandelbrot in the other languages, and there we fixed many of the problems. In general, the slowdown comes partly from the way we implemented our instrumentation. So in truffle instrumentation, to actually replace a return value of a node, you throw an exception. That already costs quite a bit of performance.
Okay.
And this is one of the larger reasons. Now we tried to implement some optimizations so that this doesn't impact execution quite as much. But in some cases, there is still work to do.
Okay. I guess I just saw the Stefan question. I guess it's related. He's talking now. He's asking about the overheads. Where this is coming from?
Yeah.
One of the I didn't get that. So you create those nodes at the AST level. Okay, it's a truffle AST. Are those nodes supposed to be compiled after parsing evaluation? So the binary will contain also the taint nodes.
Well, truffle instrumentation is designed to when you insert these instrumentation nodes, you de-optimize all the currently running machine code. And once you have actually inserted all your instrumentation nodes and the interpreter has collected enough profiling information, everything gets compiled again, including the instrumentation nodes. So the partial evaluation is also executed again and can, at least this is a property of GraalVM, the GraalVM JIT compiler that we already use. This partial evaluation can then also remove parts of the instrumentation again if it can see that, for example, a value should never be tainted.
Right. So do you have any estimation, or have you measured how big is the binary with these taint nodes compared to not having them? Because the binary is not fat enough.
No, we haven't measured that metric yet.
But it's something that you have
currently the only
or?
performance metric that we have is actually peak performance.
Okay.
But we are currently working on, well, first of all, we are working on improving the peak performance of truffle taint when we actually have to propagate taint. And after we are there at a point where we could say we are competitive with other applications, we take a look at other properties like, for example, in slowdown in the interpreter rather than peak performance, or also memory overhead.
Okay, so we're getting quite a few questions. Thanos is asking if there is any particular characteristic of the application that you plan for your future work.
Not really at the moment. So we are currently really trying to optimize the taint agent with respect to its performance. Since also dynamic taint analysis is quite a fast evolving field, I would say, with regards to applications of taint analysis, we don't really want to fix on one particular application just yet.
Okay. Stuart is asking in your example, where you have a time source, a read line, goes to time sync with the eval function, does the dynamic taint analysis have functionality to strip taint from values in circumstances where taint values could be validated at runtime?
So this reference taint analysis application that I talked about in the presentation has a built-in function to so that you can use to manually remove taint from a value. Yes.
Okay. One thing I missed from the presentation is, can you describe a trace where the actual code injection is happening? So that was the motivation in one of the first slides. That
it isn't really a motivation for truffle taint. It was just an example to basically illustrate that taint analysis is basically about tracking data as it runs through your program. And code injection vulnerabilities are one field where you can really apply this taint analysis to its full effect.
Yeah, my question is around, so imagine that the code injection is happening, your taint framework will detect it at the first level where the node is happening. You don't have to search code down, right? Because it's already propagating in the next node, if you like, in the truffle AST. Is that correct?
Yes. So basically we are doing taint tracking with runtime instrumentation. So we don't really take a look at the entire data flow graph. We just look in each taint node, are my inputs tainted? And if so, I apply a taint label to the output.
Mm-hmm. Okay, Christos, go ahead, please.
No, I just meant to say that no taint node really knows exactly where a tainted value came from. So there is no place in the system that really builds an entire data flow graph from the application. That would be static taint analysis.
Mm-hmm. Okay,
but of course, with truffle taint, it would be feasible to also implement a case where you could use additional static analysis if you wanted. So this is one of the great benefits of truffle taint, that you have the flexibility of actually defining your own taint nodes.
Okay, I guess one of the questions, related question to one of my questions before, Christos is asking, what's the maximum overhead that you can safely say this is acceptable for deployment?
Well, this is a good question, and I think the answer really depends on what kind of use case you want to implement with taint analysis. So do you want to have a taint analysis, for example, to prevent code injection vulnerabilities where you really need to apply it in a production environment? There, of course, every % of slowdown that you have counts. On the other hand, there are also applications for taint analysis, for example, for debugging, where you don't necessarily care this much about how much slowdown you have. In general,
I guess Christos
we don't have
production applications or performance.
So there, our goal is to get within comparable taint tracking frameworks. So for example, for LLVM, there is, for native code, there is currently, for example, libdft, which is very fast, which has slowdowns from roughly 2x to up to 6x, for example, even for larger applications. And this is where we would want to get.
Okay, I think Christos is typing maybe a follow-up questions. Yeah, is it possible to have an adaptive mode where you can activate or deactivate dynamically? That's a good question.
It would absolutely be possible.
Mm-hmm.
You could implement such a thing on the basis of truffle taint, so within taint nodes themselves. This is actually quite simple because, well, for example, GraalVM compiler supports a speculative optimization. So you could just have, for example, an assumption that your taint tracking is currently enabled. And when you want to disable it, you just de-optimize the compile code, and then you can basically completely disable this. On the other hand, truffle instrumentation in general is also designed to be dynamically enabled and disabled. So you could just throw away all the instrumentation nodes that you currently have attached when you want to disable the instrument, and then later attach them again.
Okay. Final question for this blog. Is this implementation now open source in Truffle, or is something internal?
Unfortunately, it is not open source yet. So this is a joint project with Oracle Labs, so Oracle would need to approve open sourcing it. And of course we want to, but whether or not they will agree with this is another question.
Yeah, I understand. Okay, so I don't see more questions. Time is up. I think now we have the Ask Me Anything session, but I don't see any pending questions from the sessions. So we can go directly to the virtual halls. Yeah. So we join again. Let me check the calendar program. 30 UK time for session 3. See you then.
The reasons you should work at ARM are first, technology, right? The massive impact it's had on the world. And you can see that from the 2,000 people we were a few years ago to the 6,000 we are today. Secondly, it's got an awesome benefits package. Next year I go on a month's paid sabbatical. And thirdly, the people are really smart, so they challenge you, and actually more importantly, they're really nice. So they're really fun to work with.
If you want to work on technology problems that affect everyone, and you want to do it in an open, trusted environment where you'll be empowered to get on with your job, then this is probably the right company for you.
Definitely, ARM has changed me as a person. I've opened my mind up to an awful lot that I'd never come across before. It's been an excellent experience.
There's a very nice culture where the emphasis is on the engineering, the quality of the engineering, and indeed the welfare of the engineers.
Looking after my own mental health is something that's really important, and I think ARM gives me a good ability to do that.
There's kind of never a dull day. I'm never kind of working on the same project for too long.
I was in the Budapest office last week, the design centre, and I noticed a poster. It said, "Great minds don't think alike." And I just smiled when I read that, because that's exactly what it's like working at ARM.
Racing, a competition of speed, set against an objective criterion, usually a clock. It is where the fastest wins, where the stopwatch doesn't lie, and success or failure is measured at the checkered flag. But for those who live racing, it really is more than just a race against the clock. The tension, the drama, and the unpredictability of the race, all of this adds to what racing really is. In racing, respect is earned the old-fashioned way, and greatness is built one victory at a time. Out there you are alone, with nowhere to hide. Any sign of weakness and you will be exposed.
And then neck and neck coming into the corner. He's down!
Lose focus for a single moment, and you will face the full wrath of the laws of physics. When the weight of the world comes crashing down on you, will you quit? Or will you dust yourself off and keep on fighting? Racing is where history is made, and where champions rise from the crowd, accepting all challenges fearlessly. Champions aren't only measured by what they have won, but by what they have overcome on their road to glory. Without obstacles, tough battles, and pain, victory is empty. So what is racing then? Racing is 100% commitment to everything you do. At KTM, racing drives us and makes our world turn. This is the world that awaits you. KTM. ready to race.
Hello, everybody. Welcome back to the third session of MPLR. The first talk in the session is titled Transparent Acceleration of Java-based Deep Learning Engines, and Thanos is going to present it.
Hello, this is Thanos, and today I will present you the work that we did with my colleagues at the University of Manchester in collaboration with Zoran from DeepNets. The focus of our work is the transparent acceleration of deep learning engines directly from Java onto heterogeneous hardware, like GPUs. Let's start with the motivation of our work. It is foreseen that till 2025, the number of devices connected in the World Wide Web will reach up to 42 billion devices. And this large number of devices will be responsible for the generation of a large volume of data in the scale of zettabytes. So this can drive into two challenges. One is the fast data processing, and the second one is to take some smart decisions in order to trim this large data volume. Two ways to address these challenges are, first, regarding fast processing, to employ hardware acceleration, and the second one is for regarding the smart actions, to employ artificial intelligence and deep learning networks either on the IoT or the cloud side. Let's have an overview on deep learning. The main objective is to enable the computers make some smart decisions. How is this done? It is done by employing a mathematical model that is actually trained on some historical data, and then it can take some decisions at runtime. And these decisions can either be accurate or inaccurate, which can lead into the retrain and the refinement of the model. The characteristics of such workloads are that they offer some high computation, so they are computationally expensive, and that makes them ideal for hardware acceleration. From the programmer's perspective, in order to program a machine learning and deep learning application, programmers use some high-level languages like Python and Java. And this is because these languages, they are easy to programming and they are easy to maintain the code. The majority of the state-of-the-art of the current frameworks like TensorFlow, PyTorch, and deep learning for J, they offer bindings to these programming languages, and they offer support for hardware acceleration. However, they have some limitations. One of them is that they support precompiled code. That means that the code that they support that can be accelerated on a GPU, it is specifically compiled for this particular architecture, and the code is not portable on different devices like an FPGA, for example. So they lack of portability. What we aim to achieve in this work is to show how just-in-time compilation can be employed in order to enable the deep learning engines to be transparently accelerated on different hardware resources. Therefore, we utilize DeepNets, which is a Java-based deep learning engine, and TornadoVM, which is a Java heterogeneous programming framework. Let's have a look on DeepNets. As I said, it is entirely implemented in Java, which makes it easy to use. And it can integrate multiple neural network models, which gives the opportunity to Java programmers who know machine learning to easily integrate their own machine learning models. And it is the foundation of a standard API for visual recognition. However, it has some limitations. One of them is the lack of hardware acceleration, which actually results in slow training. This is an example of the training of a neural network. As we see here, we have three figures. On the left side, we have the artificial neural network, which is comprised by many layers, three types of layers actually. The input layer that has one neuron, the hidden layers that have multiple layers that are hidden and comprise multiple neurons, and the output layer that has the actual output neuron. So as we see here, it is a fully connected layer, and meaning that every neuron, it is connected with all the remaining neurons in the next layers. And starting from the input layer, each neuron inside it has an activation function based on which an output value will be generated. The output value is then forwarding during the forward pass on the next neurons, the neurons in the next layer, which they are actually triggering the activation function, and they produce a result that is then forwarded subsequently to the next layer until they reach the final layer, the output layer, where the actual decision will be made and the accuracy of the model will be assessed. If the accuracy is satisfying, then the model is ready. If it's not, then the backward pass, the back propagation phase will be triggered, which will readjust and refine the biases, the weights of the activation functions, and then the model will be retrained for the next pass. This is a structure of how DeepNets is built. So the programmers, they enter as input the data set and the network settings, the actual layers that they want to build a particular network. In this case, we are examining a fully connected layer, which is a network that we have targeted in this work. At the first stage, DeepNets will build a network, the actual structure of the network. Then the next step is the training of the network, which is the process that I described in the previous slide, the feed forward, the forward pass, and then the back propagation pass. And the final step is the testing of the network. In this work, we use the community edition version of DeepNets, which is open source. However, there is also the enterprise edition, which offers the multi-threading implementation. Now let's have a look on TornadoVM. TornadoVM is a JVM plugin that can transparently accelerate Java methods on heterogeneous hardware. It offers an easy-to-use API, which is task-based API. We will have a look later on an example. And the main advantage is that it is platform agnostic, as it abstracts all the hardware information, and it actually translates at runtime and specializes the code at runtime, depending on the characteristics of the targeted hardware device. This is the structure of TornadoVM. As we see, there is a modular design. It has three main layers. At the top is the API, then it's the runtime, and then is the execution engine that is actually includes also the compiler. At the top, we see the Java methods. Each method, it is assigned to a task. The Tornado API exposes an object called task schedule. This object is actually a group of tasks. Each task is meant to be assigned with one method that will be offloaded on a hardware device. So let's take into example that we have one method. One method is a task that belongs to a task schedule. The task will be transformed into a data flow analysis, and the data flow analysis structure will then invoke the optimizer, which will optimize the code. So for example, these optimizations could be optimizations regarding the data transfers, if data don't have to be moved into the device, into the memory of the actual device. Then the bytecodes will be generated, the TornadoVM bytecodes, which will invoke the compiler to perform the JIT compilation for the actual device. The compiler is the Graal compiler, which is extended to support some device-specific specialization of the code, depending if the code will be executed on an FPGA, on a GPU, or on a CPU. So different types of optimizations are triggered at the compiler level. And then the device drivers will actually compile the OpenCL code into the actual binary code. In this particular work, we have used the 5th version, the version 5 of TornadoVM. This is an example of how programmers can use TornadoVM in order to perform a matrix multiplication on a heterogeneous hardware device. So we have the compute class that comprises two methods. One of them is the MXM, which is the actual computation of the matrix multiplication. And the other one is the run that actually invokes the TornadoVM API. As we see here in the matrix multiplication method, there are 3 inputs, A, B, and the result C. And the type is an object, which is actually known at the compiler and the compile time, the layout of this object, because Tornado supports primitive types. And the only change that the programmers have to do is to add this at parallel annotation that is offered by TornadoVM, which is a hint to the compiler that these 4 loops can be executed in parallel. In case there is a dependency between these 2 for loops, then the compiler will not be able to parallelize it and the code will be executed sequentially. The second method, run, is actually instantiating the object of the task schedule, which is the group of tasks that can be executed on a device. So in this particular case, we have one method. So we have one task, we have the name of the task, the name of the method that will be offloaded, and the name of the parameters that will be the inputs of the method. Then we invoke the streamout method, which is actually the call of which data have to be copied out from the memory of the device to the Java code. And then we invoke the execution with the execute method. Let's have a look into the integration of Tornado with DeepNets. On the left side of this slide, we see the original code of the forward method in the fully connected layer of DeepNets. As we see, this code has 2 nested for loops, which are iterating over an array, which is a float array of an object. The actual computation that is performed inside the loops is the activation function, as I described earlier. So in this particular case, we have a multiplication of the way with the input array, and then the activation value is taken depending on the activation function that is used. And then there is a setter that will assign the value, the val, into the output array. The modifications that we had to do in order to make this code run with TornadoVM was that we had to flatten the arrays and make the arrays of primitive types instead of using the tensor objects. And then the other change was to add that parallel annotation in order to identify and notify our compiler that this code can run in parallel. The other change, the last change, was to actually invoke the Tornado API. and call the actual task schedule with all the parameters regarding this particular method and the inputs and the outputs of this example. The benefits of our approach is that we offer seamless acceleration of any part in the deep learning engine. So we don't rely only on the parts that have been already compiled for heterogeneous execution. This can be good in case of some new machine learning models or new layers that can be emerged in the future. So in this case, such an example will offload all the computation transparently without relying only on the precompiled binaries. And this way, we can target different platforms with the same code, the same Java code. So we can perform the same execution on an FPGA also. And we could potentially utilize the migration of execution from a GPU to an FPGA and backwards, which is a feature that is offered by TornadoVM. However, this feature is not investigated in this work and belongs to our future work. Let's have a look in the performance evaluation of our system. So we use as a test bed these characteristics of on our server. So we target two GPUs. One is the AMD and another one is an NVIDIA GPU. And as an experimental methodology, we execute our code 200,000 times in order to perform the warm-up. And then we report the median of the next 10 executions. At the bottom part, we see on this table the benchmarks that we use to evaluate the system, the accelerated system. These benchmarks are already integrated in the DeepNets engine. And we perform the acceleration on the fully connected layer. And actually, in particular, we utilize and we investigate 3 different types of workloads: low, medium, and large. And this, the size of the workloads is actually the width of neurons within each layer. This figure shows the performance, the end-to-end performance of our system against the Tornado vanilla code. As we see, on the x-axis, we have the 4 benchmarks, and each benchmark has 2 GPUs, AMD and NVIDIA. So we report the results for each GPU. As we see here, for the low and medium workloads, the vanilla code is actually faster than the accelerated Tornado DeepNets code. So in essentially, it's not accelerated. But in this case, we see that the actual size of the computation, the data that will be computed, they are not worthy of moving, of going into the GPU and actually performing the computation there. But when we go to the large data sets, to the large workload, that we increase the computation, then we see that the maximum performance that can be achieved is for iris classifier and up to 6.45x speedup. I would like to mention that this comparison is the end-to-end, so it includes also the data transfers. Now let's go to another figure that compares only the kernel execution time with the Java code, against the Java code. We see again that we have the 4 benchmarks, and each benchmark reports the timings, the comparison for both GPUs. So here again, we see that for small data sizes, the computation is not enough to be worthy for acceleration on a GPU. So we see that when we increase the data sets and we go to the medium and the large workloads, in most of the cases, in most of the benchmarks, the actual result is a speed up, even for the medium size. And then we reach the maximum performance speed up that we have seen so far. It is 88.5x for the iris classifier on an NVIDIA GPU. In summary, we have shown in this work that we can employ just-in-time compilation in order to transparently offload some part of the functionality of a deep learning framework on a GPU. In future, we aim to extend our work and utilize actually offload computation from other layers like the convolutional layer or the max pooling layer onto the heterogeneous hardware, and also expand our experiments on FPGA devices. In addition, it is very interesting to investigate the ability of migration, the execution from one device to another, or utilize in parallel both type of devices. This work is funded by a European project, the E2 Data project, and I would like to thank you very much.
Thank you very much, Thanos, for your talk. So I see somebody typing in Slack. Anyone else has a question? I will just start with a deep end. So when you talked about the evaluation, you mentioned that you did 200,000 iterations of the benchmark as a startup. Could you elaborate a little bit why you needed so many? And then I think you measured only 10 of them in the end.
Yeah, thanks, Stefan. So actually, this is a part of the deepness and the training process. So part of the training is to have some epochs which will repeat the passes, the traversal through the network. So the actual number is the number that will be used for the training of the whole network. And then we report the last 10 executions. We decided to take the last 10 just in order to have the JVM to be warmed. In order to report the exit code.
Thank you. So Florian on Slack asked, what is the reason OpenCL kernels times are slower than Java times for low data sizes?
For low data sizes, this is the case that we have examined also with other benchmarks in Tornado. The reason is that the data size is that small that it's not worthy to be copied through the bus, through the PCI Express, and go to the actual GPU or an FPGA. So the overhead of moving the data is significantly higher than the actual acceleration of the computation.
Right. So perhaps as a follow-up question here, do you have any kind of mechanism to automatically decide when to go to the GPU and when to do things on the CPU? Seems like
currently we have some heuristics in the Tornado VM infrastructure. So we start the compilation for all the devices. So we spawn a different thread for each heterogeneous device. And if the application has high latency requirements, the first device that will execute the kernel and will finish, it will be the one that wins for the execution. But currently we're using heuristics to examine this. And as part of the optimization, I could say that part of our API is to optimize data transfers in case we have chains of kernels executed on the devices, on the same device. So for example, if we have two kernels and the second consumes data from the first one, then the data, the results of the first will not be to copy out, and they are already in the memory, so they are ready to be consumed.
Okay, I think somebody else is still typing on Slack. So you know kind of used deep neural networks. Are there other machine learning systems that would benefit equally from that approach?
We hope so. So we have started this work with Zoran from DeepNets, and we're exploring currently in this work. We have examined the fully connected layer. It's a particular type of layer. But we want to examine also other type of layers and perhaps other types of models. For example, some classification applications and models which could benefit an FPGA to perform the execution on FPGAs also, which belongs in our future work.
Right. So when I look at the solution I'm seeing as a language kind of person, I'm wondering how much is actually specific here to the field of machine learning and to the application. Could you elaborate
Do you
that,
mean,
perhaps?
yeah,
So,
do you mean the actual integration part?
Yeah, from the overall system.
From the overall system, I could say that we haven't changed many things in the deep learning part, so in the algorithmical level of the DeepNet engine. The changes that we have applied, they are more into the Java layer, into the layer that we accelerate, and mostly on the how to invoke the API of Tornado. I'm not sure if I got the question correctly. If you want, feel free to rephrase it.
So these changes sound fairly general. So I'm just trying to kind of have a more clear picture in my mind what's specific here to deep learning engines.
So specifically to be accelerated, let's say in general, on so like a characterization. I could say that during the training, the number of tensors can be examined in parallel. So part of the parallelization is there, and we have utilized the parallel annotation to expose that for the Tornado compiler to understand it. And this is similar from with other frameworks, other machine learning frameworks.
Okay, thank you. There don't seem to be any further questions as far as I can see. So I would say we move on to the next talk. The next talk is going to be titled Efficient Dispatch of Multi-Object Polymorphic Call Sites in Contextual Rule-Oriented Programming Languages. And the speaker is Lars Schütz from the Technical University in Dresden.
Hi, my name is Lars Schütz and I'm going to present to you efficient dispatch of multi-object polymorphic call sites in contextual role-oriented programming languages. This is a joint collaboration between me and Geronimo Castellón. It's chair for compiler construction, TU Dresden, Germany. So let's consider a textbook example where we want to model the relationship between a person and an employee, which is often said to be implemented by using inheritance. But the problem here is that the type is decided at construction time, which means you could either be an employee or you could be a person. But when you cease to be an employee, you also cease to be a person. So what you can do is actually to decouple both entities and ease this relationship between them. This could be done, for example, with roles where it says that an employee is a role that is played by a person. The person is the base of this relationship. And this does not only make sense at the class or at the type level, but also at the instance level, because now we can have Joe, who is a person, and Joe is a student. Because Joe is a student, he also needs money, so Joe is also an employee, and because he needs a lot of money, he has multiple employee roles. So what you can see is that there's some dynamism. Roles can come and go, and we still have the same base object. So we have a decoupling between our roles and our objects we are representing. But you can use roles also for extending at runtime the behavior of your objects. For example, a person has a phone number, but when he plays the role as an employee, he also has a phone number, an office number. And you can also override existing behavior, which means that when a person is asked for its phone number, by means of interception, the office phone number is returned. So roles do not come alone, but they are encapsulated in teams. And those teams are also objects that are representing contexts in our application. And those teams can be turned on and off. And when you turn the team off, all its contained roles will be deactivated, and also the adaptation will not take place anymore. So this introduces some polymorphism on the object level, which means that an object could play at runtime different roles at different times. So we have this place relationship between bases, teams, and roles. And when this company team is turned on, we will have this triple inside this relation. That means that our person plays this employee role inside this company. And this concept is implemented in the language object teams, which is not implemented by me, but I just work on it. And this language is actually compiled into Java or bytecode, which is a single dispatched language. So let's have a look how the dispatch actually looks when you have such a nice concept. So consider a simple example where we have accounts, and you can withdraw money from accounts. And then you have checking accounts, which are played inside banks, which provide or add some fee whenever you withdraw money. That's what's written here. And on the right-hand side, we have a sequence diagram which represents some points in time and what's actually happening. So when you're withdrawing money from your account, you first have to find the related checking accounts role, and then you can call the function with fee, which does nothing else than adding a fee and then withdraw the money with the added fee, which returns us the original function. In order to implement all this in a single dispatched language, we have a lot of other things that are going on. For example, we have trampoline functions and stubs that are generated, and we have other stubs that are generated. And this prevents a lot of optimizations, for example, inlining or dead code elimination, but it also introduces a high runtime overhead, which means in this case we have up to, or we measured up to almost 60 times overhead instead of using a simple pattern to implement this role behavior here. And the problem is just this base role mapping that is actually statically compiled. So what we can do here is to take a closer look at this base role mapping. And therefore I want to show some of the team's code, which just represents what you've seen by now, where you have a call in that takes money and then just calls its base with and the added fee, and we have the replacement, which tells that our with fee method replaces the withdraw method in account. And the static compiler gives to every call in an ID, and this ID actually guides the dispatch. So what the compiler does is, for example, in our bank, to generate a code where we switch over the IDs of our call-ins and delegate to the correct instances of roles and the correct methods of those roles. And furthermore, inside the roles, our base call is compiled into something that is called call next, which means when there are more adaptations for these objects, we will first execute those before we execute the original behavior. So we have a recursive reversal on our runtime. The interesting thing here is that we can also display this as a call graph, which is generated ahead of time. So on the left side, you see this gray shapes, which means that we are still on a base instance. And when we call the withdraw method, then the ID is actually dispatched or forwarded. So we start to call a stub method, which then accesses the runtime state of the application. For example, there is a stack of active teams, which are then also forwarded into the framework. And then we dispatch on the first team in this data structure and call the replace function, which then This represents the switch statements, switches over the IDs, and then we are delegated to the proper lift state function, which is implemented inside the team and returns the role instance on which we are then calling the replace call-in. And this could even go further into this array structure here. But what you can do is actually, when you would partially evaluate this call graph, you would see that we already know, by having the ID and having our base instance, we already know which functions are going to be called. So what you can do is we can leverage this metadata that is already compiled into the classes, like the IDs and the respective team classes, and use the runtime data, like the team instances, to construct this call graph at runtime. Because the result could be something like this. We have our base instance and we call it the withdraw method. And just because of this knowledge, we already know that we have to call the lift method, which returns us the proper role instance, and then call the proper function on this instance, which is all decoded into the metadata of our classes. But the problem here is, what happens if the team instances change at runtime, which means return off a team, then it will be removed from this list. So this call graph is not valid anymore. So what we can do is we can define a guard which then guards for the permutation of this data structure here, which means that every instance which has the same class at the same position in this data structure is a valid configuration for calling the right-hand side of this call graph here. So those guards protect our dispatch plans we just constructed at runtime. And whenever this guard fails, which means, for example, that here is a totally different type inside this data structure, so we just construct a new graph, which is then also chained with this guard. So you can have a chaining of guards until an upper limit. When you'd say, okay, this does not make sense, we just use the prior way of dispatching functions. So what we achieved here is some polymorphism for our dispatch plans. But what we didn't have yet is not everything in this graph is statically decidable or even decidable at execution time, which means we have an iterative approach. What does it mean? Whenever we have this base call, we actually go deeper into our data structure that's representing the active teams. And this does the very same than we did before. It constructs a guard on the instances here, and then generates a call graph for the right-hand side of these dots. And in our case, for example, when this list here is empty, we just dispatch to the original function of our base. So what we achieved is a runtime compilation of those polymorphic dispatch plans. We could encode the role semantics into, in our case, we implemented this with method handles and evoke dynamic, and can do a repetition for each call-in that replaces the behavior and goes deeper to the chain. And instead of doing this in a recursive approach, as it was done before, we could do it in an iterative approach. So what we actually achieved is, at a call side, we could construct a graph that is representing the code that's going to be executed and late bind it into the call side. So on a higher conceptual level, we have late binding now for role dispatch. And we use runtime feedback, and we communicate this role invocation to the JVM by using evoke dynamic. and closes the money gap, because now the JVM can actually go over this data structure that is represented as a call graph and emit efficient code, so we can benefit from the optimizations with the JVM. So let's evaluate this. So we evaluate this in a very simple benchmark, which is a little bit bigger than what I just showed to you. So we have an account which can withdraw money or you can deposit money, and this account can play the roles of a checking account but also of a savings account inside a bank. And we have transactions, which are also teams, and these transactions have the roles where accounts can play the roles of source and target. And then we have two variations currently of this benchmark. One is a static one, where you just have one context, which means the transactions are not modeled, but we directly remove or withdraw and deposit the money of the checkings accounts and the savings accounts. And by this we could scale up the amount of iterations and the amount of redo. And then we have a dynamic benchmark, which is the full version here, which has less iterations, but a lot more roles. So we have almost 5 million roles. And because of the many transactions, we also have more than 2 million contexts that are played at runtime. The result is, in the static context benchmark, that we have a monomorphic call site, which means there is no state change and it's quasi-static. So we could reuse the whole call graph at every iteration. And what we see here is that we have a logarithmic scale, and we're actually comparing to the current implementation of object teams. But we're also comparing to the implementation of 2019 and to a prior approach which wasn't polymorphic. And we also measured our dispatch plans on Graal and on JVM 14. And what we can see is that we have a speed up from 3.8 to up to 4.5, while Graal has a speed up of up to 2.8. So we are not quite sure why this result from Graal is not the same as on a JDK or JVM 14. But you can also see here the standard derivation of the mean is enormously large for Graal. So somehow it doesn't seem to like the approach on the static benchmark. But what you see is that we can already leverage the JIT optimizations of the JVM, and also you could see that we're in the current implementation faster than in the prior implementation, because now we can also do a copy and write optimizations, which means whenever we gather this data structure of active teams, we can stop making copies whenever we execute a function, but just reuse the same instance of this array until there is a new composition of teams constructed, so until there is a team activated or deactivated. In the variable contexts, we have a polymorphic call site, which means we have these, in each of these iterations, contexts activating or deactivating, but still our guards could catch this case. And what you see here is that this was the old approach, which was not polymorphic. We are now in smaller number of iterations, whereas we are also faster. But because of the many objects that are constructed in these iterations here, the garbage collector plays a big role in the number higher here. So we could achieve a speed of up to 1.1x, but still here we have a slowdown of up to 2.3x. So the interesting thing is that Graal is better in this case with a slowdown of just up to 1.2, which means probably the partial evaluation that Graal provides is very efficient here with all the objects that are being constructed due to the dispatch plans. So what does it mean for future work? For future work, we think of extending the benchmark for more synthetic benchmarks, which could be even used for other role languages for comparison. But here we want to have some way of defining, for example, the depths of the chain that we are calling, or even the number of call-ins that are active at a call site to measure on the different variations that are possible. Also, it would be interesting to provide runtime support for these role-oriented execution semantics, in the sense of that we have or extend a VM which is able to manage those important data structures. And role-playing probably could be captured inside the object layout itself, and then we could use profile-guided optimizations to provide an efficient implementation of this language. And on the other side, we also want to provide a minimal type system for those contextual role-oriented programming languages. Because in a lot of papers, it's often said that those roles actually define the type of an object. But still, the current works just encode for contexts scoped adaptations. So what happens if we have a minimal type system for a language like object teams, where we could mimic this contextual changes with global effects? Would be quite interesting. So thanks for watching.
Yeah, thank you very much for your talk, Lars. I don't see any questions yet in the Slack, so I have a couple to start with. Could you perhaps elaborate a little bit on your experience and how these role programs work in terms of their dynamic properties? So I'm especially interested in perhaps larger programs. So when we think about a single lexical location, a program location, do you see a lot of variations in terms of the final target for your dispatch, or is that often kind of a low number of possible targets?
So this depends a little bit on where you want to use those languages. So object teams, for example, is often used with frameworks and to adapt frameworks, and there you have a low variation. But in the research school, I also do my PhD, we look into cyber physical systems, and there you really want to map the real world into your software system. And then you have more context changes, which also means that the roles that will actually be called, or the functions will be called on those objects that you represent, will be changing much more often. And there sometimes the question could be, how often do you really need to reuse such a call target? So when you change your context, but you don't come back to your other context, like it was actually, you have been wasting time in doing all those optimizations. So it's quite interesting also to find a boundary. So when do you start to optimize and when not?
Okay, I'm just curious, how large are these programs typically? So what are we talking about here? Is it a couple of thousand lines of code?
Yeah, we are in a smaller domain because all of those are currently research prototypes, and so finding real applications is often a bigger problem than finding real cases, and that's why I also try to go on synthetic benchmarks, and in some sense it's funny because the benchmark I just showed is so easy, and you would think of, why is it actually why do I write about it, but optimizing such a single program already is first this dynamism that is introduced in this concept, or the possible dynamism actually you would have to say, not so easy anymore.
Right. So Christos has a question in Slack. Could this approach of passing semantics to the virtual machine work also for other functions beside call dispatch? And then he refers to the example of memory locality.
Could you elaborate on you mean
Yes, if I may to use a microphone, I think it's easier. So, to my understanding, you pass the semantics of the target call, let's say the relationship, in order to optimize the inlining process, or at least no, the inlining, the call dispatch process. So let's assume now that we run this framework on a JVM, and now we want to exploit a memory locality, meaning that if I have a relationship with somebody else and I can, let's say, optimize this relationship, then to force the allocator to put us together, let's say in the same cache line. So do you think that could be possible with the same methodology to optimize further these programming languages?
Yes, indeed. So what I also spotted, like in doing my research on those languages, is that you have since the early 2000s, you have this research in context-oriented roles, and since then, like there's just only one approach that had been implemented in research, is where you have the roles encapsulated into the context, but probably it makes sense for to actually keep the roles with the objects also in memory more together, so you could do not have to have also some delegations to these context objects and then call these functions, or somehow execute this mapping to get the right role object. So it would be interesting how you could like keep the roles with the objects that replace the roles, and have the context separated, and then by adding or removing context, change all the roles or change all the objects that take part in these adaptations.
Yeah, because for example, if you know the relationship with the context, and then you do garbage collection, and somehow you could piggyback on this relationship during garbage collection, you could force those two objects to be evacuated together, so to increase the locality, right? You could do that, I mean, theoretically at least.
Actually, I want to do something like this with the dynamic object from Truffle, and so a couple of months maybe there's something ready.
Looking forward.
Yeah.
So I have perhaps one more question. Could you perhaps tell us a little bit more on how you did the benchmarking? And here I'm particularly interested in how you manage warm-up and things. So because you showed us that static context benchmark where Graal had that huge error margin, and I'm wondering whether perhaps in your data there's just still warm-up of Graal in there, so that perhaps Graal takes a little bit longer to actually optimize your program, and then you get these huge error margins.
So I think the real numbers we report in a paper. So for now, I've not possibly in my mind, but we use the rebench tool for configuring our benchmark. And this benchmark is also run, I think we restart the VM 3 times, and for every run we do some hundreds of runs, or run some thousands, because and then you have this inner loop which also does those million runs. So I fairly think the VM is warm, because we also have JMH benchmarks to just calculate the numbers for this dispatch, and they report or support the numbers that we report for in a bigger benchmark. So, but somehow I think a lot of those things are garbage collector related. Problem here is actually a little bit comparison between JVM 14 and the JVM 11, on which the GraalVM 20 runs. And our first benchmark have been run on JVM 14, so there's a difference in the JVMs. So I couldn't run my implementation on JDK 11 because I had hit some bugs in JDK 11 which hadn't been fixed yet. So I had to upgrade the JDK version, because before I also hit another bug in the compiler, and
would just be, I mean, I would just be curious to see kind of the plot's iteration over time, and then how the performance develops, just to kind of get a bit better understanding of what the underlying data for your bar chart looks like.
Mm-hmm.
Just to have a bit more precise idea. But yeah, that's probably not the right point in time to ask here. So do we have any more questions on Lars's talk? Otherwise, I would say we go on to the next talk. And the next talk is titled, "You Can't Hide, You Can't Run, a performance assessment of managed applications on a NUMA machine." And Orion is going to present.
Hi, my name is Orion Papadakis, and I'm a PhD student in the APT group of the University of Manchester. Today, I'm going to present you our recent work under the title, "You Can't Hide, You Can't Run, a performance assessment of managed applications on a NUMA machine." This is a joint work with Fivos Zakak, Nikos Foutris, and Christos Kotselidis. The outline of this presentation is as follows. First, I will be presenting the motivation for the current work as well as its contributions. Next comes a little bit of background to lead in our new profiling tool, the PerfUtil. Finally, we will be discussing the experimental results derived by PerfUtil, as well as the conclusion of the current work and our future steps. In the current ongoing work, we aim firstly to demonstrate the need for better tooling support to help in locating the bottlenecks of managed applications when running on NUMA systems. Secondly, to propose a new profiling tool, the PerfUtil, which tracks performance counters at the runtime layer. And finally, to perform a detailed experimental evaluation for a set of applications from the Da Capo and Renaissance benchmarks. As stated earlier, NUMA architecture has been introduced to cover the ever-increasing needs in systems memory. With a non-uniform memory access design, the cores are clustered into nodes as the ones shown in this figure. Each node has a memory controller and is interconnected with other nodes using high-speed interconnection links. Memory is shared and accessible by any core across the system, but with non-uniform access latency. The latency depends on the physical memory location of the data being accessed. As can be seen in the figure, the LLC is split in slices, each of them attached to a core. As a result, multiple copies of a memory block are allowed to coexist. NUMA implements cache coherency mechanism to keep the cache data up to date and accessible by any core. Big data and cloud applications are hosted by frameworks which are mostly written in Java, such as Apache Spark, Flink, and more. Consequently, the managed runtime of choice for the current work should be a Java virtual machine. We chose MaximVM, which currently is a state-of-the-art JVM in the context of research JVMs. It is a metacircular JVM, which means it is entirely written in Java. The offered programmability, along with its flexible and modular design, make MaximVM a good choice for tool development, research, proof-of-concept studies, and more. On top of those, it employs C1X JIT compiler, the Graal compiler optionally, and supports various architectures. Although there are several research and commercial profiling tools, none of them provide support for NUMA architecture. To that end, we decided to implement our own toolchain in the context of NUMA. However, through the current ongoing work, we only present a profiling tool targeting the microarchitectural layer. This work augments MaximVM with PerfUtil. PerfUtil provides access to the hardware-specific performance monitor units of the system through the libperf-OS library and enables the monitoring of microarchitectural performance events at the runtime layer. This way, we have fine-grained control over when to start or stop the measurements at runtime. For example, we can start measuring after 5 full garbage collections or 50 method compilations. Such an approach increases precision while it significantly decreases the noise introduced by the VM itself. To validate our implementation of PerfUtil, we compared its results against the standalone version of PerfStat tool. Perfutil is quite modular and flexible. It is able to model from a single performance event to more complex configurations. Perfutil also supports perf event groups and monitor scope. The notion of the group ensures that a set of architecturally related events are all simultaneously measured for the same period of time, and thus they are comparable. On the other hand, the monitor scope allows an event to be monitored either per thread or per core, or even both. One can use the thread scope to monitor an event only for the thread of choice. Additionally, a thread scope can also be combined with a core scope, resulting in monitoring a specific thread in a specific core. However, there are some PMUs that cannot be utilized per thread, such as those of the memory controller. Consequently, a per-core scope is necessary. The key feature of NUMA machines is that the memory access latency may vary depending on the location of the memory being accessed. For that purpose, we chose to track NUMA-related events to illuminate an application's behavior in the context of NUMA. The Perfutil tool was exploited to monitor the last-level cache misses, the node accesses, the node misses, and the request to the memory controller. A last-level cache read or write miss in a non-NUMA architecture leads in main memory access. However, this is not the typical procedure for the NUMA systems. On a last-level cache miss in NUMA, the caching agent initially broadcasts the miss event to the other nodes via the interconnect before accessing the memory. In case that a remote LLC slice has a valid copy of the requested data, the LLC miss is actually a remote LLC hit, and consequently, the main memory access is avoided. Otherwise, the local or remote DRAM memories have to be accessed. Consequently, an LLC miss in a NUMA machine actually should be considered as just a local LLC miss. The node access event refers to any memory access, either in last level or in main memory, which served locally. The node miss event counts any memory access served by a remote NUMA node. However, these accesses again refer either to the last level or to the main memory. So, this event should not be confused with the remote main memory access. Finally, the memory controller events count the read and write requests arriving to the memory controller. This type of event cannot be handled by any scope because it is designed to monitor the memory request by any running process on the system. Regarding our experimental setup, we use a NUMA machine with two sockets. Each socket is essentially a NUMA node with an 8-core Xeon E5-2690, 20 MB of last-level cache, and 192 GB of main memory. So, our system has 16 cores, 14 MB of last-level cache, and 384 GB of main memory in total. We used two different configurations, the single node and the dual node. The single node models an 8-core non-NUMA system, while the dual node models a 2-node NUMA system. We utilize 8 cores in both configurations. In dual node, they are evenly distributed in both NUMA nodes. Hyperthreading was switched off for both configurations, while the default NUMA allocation policy was used along with page migration for dual node. Before presenting the results for LLC misses, let's spend some time on the metric itself. As explained earlier, an LLC miss in NUMA does not necessarily mean an access to the main memory. Moreover, an increased amount of LLC misses constitutes a strong indication of a high volume of shared objects. We will use a visual example to illuminate this behavior. Let's imagine a NUMA system with two nodes and a thread, let's say thread 1, currently running on a core of node 0. Thread 1 allocates an object, the object A, in node 0 and performs a write operation. At any later point, thread 1 might migrate to another core in node 1 due to the operating system's thread scheduling. Then, thread 1 is about to perform another write operation to object A. However, this object does not exist in the local LLC, so a miss will occur. The object A will be fetched from node 0 with a remote LLC access, and it will be placed in nodes 1 LLC. The write operation of thread 1 is now ready to be performed, while the old object A copy is marked as invalid. In case another thread running on node 0, let's say thread 2, tried to access the object A, which is now a shared object, a new LLC miss will occur. Finally, the object will be fetched back to node 0, performing another remote LLC access. Considering the amount of the extra LLC misses occurred in this example, in NUMA, due to the shared object A, as this example highlights, we are able to understand the strong correlation between an increased LLC miss rate in NUMA and a high volume of shared objects in the application. On this slide, we evaluate the locality of our benchmarks based on the LLC miss rate metric. The figure compares the miss rate between single and dual node for each benchmark. A key finding is that 11 out of 16 applications, almost 42%, demonstrate a considerable increase in the LLC miss rate of the dual node setup when compared to the single node. This behavior is justified for Aurora and Zallan due to the already known high volume of write operations on shared objects proven by a previous study. For the other benchmarks, this behavior is attributed to the high number of cache invalidations. The fork join applications such as Scrabble, FJK means, future genetics, and parm mnemonics suffer from suboptimal utilization of the available compute resources, and they can't take the maximum advantage of the available parallelism provided by a NUMA machine. In particular, these applications generate a small number of big unbalanced tasks with data dependencies and lack of concurrency. That said, our LLC miss rate findings are also a natural explanation of this behavior. Moreover, we observe that the AKA-UCT and reactors show a high LLC miss rate on the dual node setup. Such a behavior was counterintuitive because they rely on actor frameworks. These frameworks simplify thread communication and synchronization through the event-driven message passing mechanism in order to minimize data dependencies. The analysis of the remote node access rate in relation to the LLC miss rate provides a better insight about the performance impact on a NUMA machine. As already stated, a remote node access is a memory operation served by a remote NUMA node, since it has missed on the local memory hierarchy. This figure shows the node miss rate for both read and write operations as a percentage of the LLC read and write misses. A high amount of shared object accesses results in a high node miss rate and in a moderate application speedup when running on a NUMA machine. For instance, Aurora and Zallan have the highest node write miss rate, 81% and 60%, since they encounter a high amount of shared write accesses. Additionally, AKA-UCT, FJK means, Scrabble, and many other benchmarks show a considerable performance slowdown when running on the dual node configuration. This behavior highlights the high correlation between performance and node miss rate. As expected, the single-threaded applications have lower node miss rate when compared to the multi-threaded, since they do not exhibit shared written objects. However, it is notable that other benchmarks of relatively high node miss rate, for example Zallan, which has the second highest node miss rate, show considerable speedup in the NUMA setup. Such a fact indicates that along with NUMA, various layers and factors of a modern stack practically interfere and might be decisive for an application's overall performance. The influence on locality of the object placement, related components of a managed runtime, for example the garbage collector and the threads, can possibly affect the application's performance. Many studies highlight the importance of having a load-balanced execution of workloads on the available hardware resources of a NUMA system. On this slide, we show the load distribution per memory controller. Each bar is the percentage of memory requests served by each controller over the total amount of memory requests issued by each application. Optimally, a linearly scalable application should uniformly distribute the memory request across all memory controllers. This is translated to a threshold of 20.5% of the load, depicted by the dashed horizontal line in the plot. The closest to that threshold a benchmark is, the more equally distributed each load will be. FJK means and Scrabble have the most unbalanced behavior. We observe a single over-congested controller to be serving the 35% and 49% of the overall load respectively. This observation verifies our previously stated benchmark analysis in which fork join applications suffer from suboptimal forking, which in turn leads to uneven task distribution. On the contrary, applications with explicit concurrency and parallelization, such as H2, Lucert's, and Sunflow, are able to scale very close to the linear scalability threshold. There are still some benchmarks in which NUMA performance doesn't seem to be easily explained with the metrics used so far. For example, Lucert's is totally balanced but slows down in NUMA execution, while PMD has unbalanced utilization for the memory controllers, but it achieves to speed up. Our analysis regarding the OS mechanisms such as the page migration, which will be discussed later on, might affect the performance of an application and explain this abnormal behavior. Page migration or AutoNUMA is an operating system optimization which aims to enhance performance by periodically moving memory pages across the NUMA nodes. The operating system periodically invalidates memory pages in order to provoke artificial page faults the next time a page is accessed. An artificial page fault handling results in page migration to the NUMA node of the thread responsible for the page fault. This way, pages get reshuffled periodically in order to increase locality and reduce remote node accesses. Indeed, by switching the page migration off and repeating our experiments, we found that the remote accesses were reduced in 22 out of 26 applications, almost 84%. However, such a locality improvement was not reflected in the overall performance as well. Page migration managed to speed up only 4 out of 26 applications, which is almost 15%. It's a fact that the overhead of migrating a 4 kilobyte memory page is significantly higher than a single remote node access. Consequently, the page migration mechanism comes at a considerable cost. In addition, as many other NUMA studies argue, data locality optimizations do not always guarantee improved performance, because other factors such as interconnect contention, memory controller congestion, and unbalanced load are of greater importance. So, two very important questions arise. Firstly, in what extent such a mechanism is beneficial? And secondly, should such a mechanism be an operating system's responsibility in the context of managed runtimes? The current work's experimental results essentially bring to the spotlight several aspects in the context of managed runtimes and NUMA. To summarize, we highlight the following. Regarding the thread scheduling, we observe that NUMA unaware scheduling leads to scattered shared objects across the system, and as a result, locality is reduced. A group of threads with shared objects should be scheduled as possible in the same NUMA node to avoid excessive remote node accesses and cache invalidations. In addition, unrelated threads should be scheduled on any available NUMA node to maintain balance and uniform utilization of the memory controllers. The managed runtime should be able to control the thread movements itself to avoid unnecessary migration that would penalize performance. Regarding the memory management and object placement, we highlight that load balancing and memory congestion factors should be taken under consideration along with locality to avoid triggering higher performance overheads due to those factors. We suggest that even the high-level programming frameworks need to be augmented with NUMA-aware heuristics to avoid data contention. As our experimental results demonstrated, the high variation in LLC miss rate between non-NUMA and the NUMA configuration is a strong indication of a high volume of shared written objects. OS-level mechanisms such as space migration appear to do more harm than good in the context of managed applications. Therefore, it is suggested to pass their control over the managed runtime. Research tools as Perfutil, which track microarchitectural events, essentially implement a bottom-up approach. However, sometimes it's difficult and risky to correlate a low-level observation with a high-level MRE component. Therefore, an additional higher-level tool, essentially in a top-down approach, is absolutely necessary to co-examine and locate further managed runtime bottlenecks in the context of NUMA. To conclude, in this presentation we demonstrated the need for better tooling support. We presented Perfutil as well as a detailed experimental evaluation through the current ongoing work. Perfutil is a new profiling tool, and the presented evaluation not only refers to the traditionally established Da Capo benchmarks, but also to the newcomer Renaissance benchmark suite. Our future plans mostly focus on bridging and co-leveraging the low-level metrics with higher-level metrics related to components of a managed runtime, such as garbage collection, thread scheduling, object placement, and more, which are critical to locality and congestion. Thank you very much for your attention. If you found any part of this work interesting, please feel free to contact me.
Yeah, thank you very much for your talk. I'm also a big fan of having better tools. So yeah, I really enjoyed your talk. So one question from Thanos from Slack. Do you have plans to run your tool in larger NUMA machines? Are there any constraints around that?
Yes, of course. This is one part of our future plans because the modern NUMA machines are more exotic than having only 2 NUMA nodes. They have multiple NUMA nodes, and in many cases they have more blades of NUMA nodes, consisting a system of tens of NUMA nodes and terabytes of memory. So, of course, it is on our plans.
Do you expect any specific issues with these kind of, I suppose, hierarchical configurations?
We don't. I can't see any issues related to the methodology when applying the same study on bigger machines, because those machines, the bigger machines, also have the same architecture, and they provide. They have the same hierarchy in the memory. They have shared memory as the traditional NUMA systems that we use for that study. The only constraint is maybe microarchitectural differences. Yeah, mostly on that stuff, related on that stuff.
Okay, cool. So I wrote a question in the Slack, which is, I suppose, yeah, very broad. So I was wondering whether there could be any way to build more high-level tools that kind of take these low-level issues into account, things like cache locality, different types of hardware counters, and all that kind of stuff, but don't necessarily require every programmer who wants to work on a NUMA machine to become essentially an expert in the hardware and possibly the processor design. Do you perhaps have any ideas around that?
Well, first of all, if someone wants to exploit more efficiently a NUMA machine, unavoidably, inevitably needs to know the architecture of NUMA, because the most bottlenecks are caused because of the unawareness of the underlying architecture. So, yeah, this the first I am thinking of. Secondly, I think that In order to measure, to do a microarchitectural study, again, it is inevitable to dig into the microarchitectural details. However, our plans, as we say into the paper and into the presentation, are to build more higher level tools, which will provide metrics of the higher level components of a VM in order to bridge and correlate the high level metrics with the low level metrics we have on this study. Because measuring only the last level misses, for example, or the memory controller congestion, you are not able always to illuminate the behavior of an application and the whole system totally. You need also a top-down approach.
Okay, thank you very much. Are there any further questions? At the moment, I don't see anything in the Slack channel. Anything on Zoom? Don't see any hands raised either. Okay, I think that's it, Dorian. Thank you very much again for your talk.
Thank you very much.
The next session is going to start, let me just check, at 12:30. So in UK time, it's now 3:50 in the afternoon, and we will start the keynote titled Hardware Support for Managed Languages, an old idea whose time has finally come, by Martin Maas at 4:30. So we have now about 40 minutes until the next session. Thank you, everyone. See you then.
The reasons you should work at ARM are first, technology, right? The massive impact it's had on the world. And you can see that from the 2,000 people we were a few years ago to the 6,000 we are today. Secondly, it's got an awesome benefits package. Next year I go on a month's paid sabbatical. And thirdly, the people are really smart, so they challenge you, and actually more importantly, they're really nice. So they're really fun to work with.
If you want to work on technology problems that affect everyone, and you want to do it in an open, trusted environment where you'll be empowered to get on with your job, then this is probably the right company for you.
Definitely, ARM has changed me as a person. I've opened my mind up to an awful lot that I'd never come across before. It's been an excellent experience.
There's a very nice culture where the emphasis is on the engineering, the quality of the engineering, and indeed the welfare of the engineers.
Looking after my own mental health is something that's really important, and I think ARM gives me a good ability to do that.
There's kind of never a dull day. I'm never kind of working on the same project for too long.
I was in the Budapest office last week, the design centre, and I noticed a poster. It said, "Great minds don't think alike." And I just smiled when I read that, because that's exactly what it's like working at ARM.
Racing, a competition of speed, set against an objective criterion, usually a clock. It is where the fastest wins, where the stopwatch doesn't lie, and success or failure is measured at the checkered flag. But for those who live racing, it really is more than just a race against the clock. The tension, the drama, and the unpredictability of the race, all of this adds to what racing really is. In racing, respect is earned the old-fashioned way, and greatness is built one victory at a time. Out there you are alone, with nowhere to hide. Any sign of weakness and you will be exposed.
And then neck and neck coming into the corner. He's down!
Lose focus for a single moment, and you will face the full wrath of the laws of physics. When the weight of the world comes crashing down on you, will you quit? Or will you dust yourself off and keep on fighting? Racing is where history is made, and where champions rise from the crowd, accepting all challenges fearlessly. Champions aren't only measured by what they have won, but by what they have overcome on their road to glory. Without obstacles, tough battles, and pain, victory is empty. So what is racing then? Racing is 100% commitment to everything you do. At KTM, racing drives us and makes our world turn. This is the world that awaits you. KTM, ready to race.
Hello and welcome back. It's been a long day, so we are very happy to have Martin with us. Martin will give our second keynote. He's currently at Google, and prior to that, he has been finishing his PhD at Berkeley, where he has been doing very exciting work on the intersection between programming languages and hardware. And Martin, today he will give us a keynote regarding hardware acceleration on managed languages, like an old idea, who he believes, and I also share the same opinion, the time has finally come.
Hi, my name is Martin Maas and I'm a research scientist in the Google Brain team, where I work on applying machine learning to systems problems. It's a pleasure to be here today and to give this virtual keynote. Thank you all for watching, and thank you to the conference organizers for inviting me. I will be talking about a topic that I've been interested in for quite a while and that I believe should be quite relevant for this venue: hardware support for managed languages. Given that this is the conference on managed programming languages and runtime systems, I probably don't need to convince anyone here, but managed languages are important and account for a large fraction of all compute cycles worldwide, on servers, on phones, on client machines, like when you run your browser, and even on embedded devices. In fact, the most recent Piper ranking shows that 7 out of the 10 most popular programming languages are managed, and 8 out of 10 are garbage collected. And so there's a lot of potential resource savings in making managed languages more efficient, since all of these different platforms would automatically benefit from it. But what makes managed languages such an appealing target for optimization? One aspect is that they provide certain opportunities for optimization that are not possible in unmanaged languages, such as dynamic profile-guided recompilation or dynamically reorganizing the heap based on profiling data. However, as part of providing a language virtual machine abstraction, managed languages also incur significant performance overheads, and addressing these overheads automatically saves a large number of resources across all devices that use that managed runtimes. And so to make this a little bit more specific, let's look at one specific source of overheads: garbage collection. So garbage collectors are part of most managed runtime systems and can account for a significant amount of resources. An ISCA 2012 paper showed that applications can spend up to 38% of their cycles in garbage collection, which translates to 10% of the total energy consumption. In addition to these resources, garbage collectors also introduce pauses which often exceed tens of milliseconds and cause stragglers in latency-sensitive systems. Now, given these overheads, it's unsurprising that there has been an enormous amount of work on improving garbage collection. Most of this work happened in software, but there's also been quite a bit of work on adding hardware support. However, none of this work has been widely adopted, and I think there are three reasons for this. First, most of this work happened when Moore's law was still going strong, which meant that it oftentimes made more sense to simply buy the next generation general purpose processor instead of a specialized processor that was built in a previous technology node. Further, many language runtimes at the time ran on servers in data centers, which were built from commodity components, and as such didn't really provide any scope for introducing custom hardware. And finally, many of the proposals that existed were very invasive, and it would have required changing things like the memory system or other parts of the chip, which is very difficult to do. However, all of these things have changed in recent years. Moore's law is coming to an end, and so that now there's actually a lot of renewed interest in custom accelerators that speed up certain aspects of your workload. Further, there's now a lot more custom hardware, including in data centers. So Google's TPU chips are one example where you use custom hardware to accelerate machine learning workloads. So this also provides scope to have accelerators for other workloads. And finally, instead of changing the entire chip, we are now used to actually building a system on chips around a large number of independent IP blocks. And so therefore, we can add accelerators in a non-invasive way. And this is what phones have been doing for many years now. And so taken together, this raises the question, maybe today is actually a good time to revisit the idea of hardware support for managed languages. And this is what my talk today is going to be about. Specifically, I'm going to be talking about three things. First, I'd like to present an example of what hardware support for managed languages can look like, by talking about work that I did while at UC Berkeley on implementing a hardware accelerator for garbage collection. Next, I'll talk about pathways to getting this kind of research adopted in the real world, and how the free and open RISC-V ISA provides an opportunity to standardizing hardware support for managed languages. And finally, I'm going to discuss what all this means for academic research, and why I think we're about to enter a golden age for working on hardware support for managed languages in an academic research setting. Let's talk about hardware support for garbage collection. And before we start looking at the accelerator, let's quickly remind ourselves what the garbage collection operation actually looks like. So if you have a managed language, typically an object-oriented one, you have a heap, the heap contains objects, and you end up with pointers between these objects where one field within an object points to another. Taken together, all these objects form a graph, and this is the heap graph that your garbage collector has to work with. When you start a garbage collection operation, you start by identifying the roots of this graph, which are things like pointers in VM data structures, pointers stored within static objects, or pointers that are somewhere on the application stack. And once you've identified those roots, you perform a typically breadth-first search traversal of the heap graph to mark and identify all the live objects in the graph. And then in the second step, you basically reclaim all the remaining memory. One way that you might do this is by compacting the graph into a smaller amount of memory, and then you can free the rest and reuse it for future allocations. So this is the operation that we ideally want to perform as quickly as possible. And it turns out that CPUs are actually not a very good fit for this operation. Specifically, a lot of this operation is about keeping a very large number of memory requests in flight as you traverse in this graph, which is something that a CPU is not always good at because it is limited by the size of its load store queue, where it needs to keep track of all the requests that are in the memory system, as well as of dependencies between them. Next, this operation is actually not using most of the functional units within the CPU. For example, it's not using the floating point unit, it's not using the reorder buffers, and so on. And finally, it does not actually use cache as well, because by definition, you are only visiting every object once. While there are things that you can cache, like for example, the mark bits, most of the objects are only ever accessed once and can therefore not take advantage of the caches. So starting from this insight, we found that you can actually improve this operation significantly by building a garbage collection accelerator that performs this operation in hardware. We proposed a design that is minimally invasive in that it doesn't require you to change your existing CPU or any part of your memory system, while at the same time giving you 4.2x speed up for the mark operation at a fifth of the area of even a tiny wimpy CPU core, which we think is the most competitive baseline for this kind of operation. So how do we achieve this? The key idea is that we add a new accelerator into our system on chip. So we don't change the CPU, we don't change the existing interconnect, and we simply drop in a new IP block that contains our GC accelerator and communicates with the CPU over the existing on-chip interconnect. This garbage collector consists of two components. One component that we call the traversal unit, which is responsible for the heap traversal that we just saw and identifying the live objects, and one component that we call the reclamation unit, which is responsible for cleaning up the no longer used memory and returning it to the runtime for future allocations. It turns out that the reclamation operation is embarrassingly parallel and can be parallelized really easily with a number of simple state machines. So what I'll focus on in this talk is actually the traversal unit. There are more details about the reclamation unit in the paper. The goal of the traversal unit is to perform the mark operation at a higher performance than the CPU while using less area. And to understand how we achieve this, let's have a look how a traditional CPU would perform this operation. So traditionally, since you're performing a breadth-first search, you have a mark queue which contains the frontier of your search. And at every step, you take out the front element of that frontier, which is a pointer to an object. That object in memory typically consists of a header and then a number of fields. Some of these fields point to other objects, while other fields contain basic types such as integers. And the first thing you do is you mark the header of this object to indicate that you've now visited it. Next, you need to identify all the outgoing references emanating from this object. The way that this typically works is that you look up the type descriptor of the object in the header. Then the type descriptor contains some kind of data structure that tells you which of the fields of the object contain references. And then you simply take all of these references and you copy them back into the mark queue. And now you simply repeat this operation until the mark queue is empty. Now this operation is highly efficient on a CPU, partially because the type descriptor is usually going to be in the cache for the most common types. However, since we want to perform this operation with as little area as possible, we don't really want to having to cache these type descriptors because that would take up a significant amount of chip area. And so therefore we need to get around this problem that each operation in this case requires you to look up the type descriptor in order to identify the outgoing references. The way we do this is by changing the object layout. We are leveraging an old idea called a bidirectional object layout, which has been used in software, but has actually turned out to not make too much of a difference there. However, this approach is actually very impactful in hardware. What you do is that instead of having a header and then you have all your fields to one side of the header, you place the header in the middle of the object and then you put all the fields that contain references to one side and all the fields that don't contain reference to the other side. What this means is that you can now identify all the outgoing references from an object without actually having to look up the type descriptor, which makes a big difference in hardware. So what does this mean? Well, if we're implementing this unit in hardware now, we still have a mark queue as before, and we still have a pointer to an object, but now instead of having to actually do this indirect lookup to identify the outgoing references, all we need to do is to access a single word in the object header, which contains both the mark bit and the number of outgoing references. And then this number of outgoing references is really the only bit of information that we need to know how much data we need to copy. And so we can simply update the mark bit and read the number of references with a single atomic OR operation, which is very efficient. Next, we still need to copy the references back into the mark queue. And this is the second area where hardware support can help. On a CPU, you typically have to perform one of these steps at a time. So you have to take the object, mark it, and then copy all the references. Which means that if an object contains a large number of references, you're limited in the amount of parallelism that your unit can achieve. For this reason, in hardware, we pipeline this operation. We now have two parts of our unit. One part that is just sending out requests in the memory system to mark objects, and then a second unit that is just responsible for, in parallel, copying the outgoing references back into the mark queue. And we simply decouple those two parts with a queue to have both of them run in parallel on most cycles. And finally, one thing that we can do in hardware that we can't do in software is that we can get around this problem that CPUs are limited by the number of requests that they can keep in flight. Because in our specific case, it actually doesn't matter in which order we process these requests. We just want to send them all into the memory system and we don't care about the order in which they come back. In whichever order they come back, we just put them into the mark queue. And so this is something we can do in hardware. Our hardware unit is simply issuing a memory request for every reference that it's meant to copy, and we don't actually keep track of them, we don't keep track of order between them, we just send them into the memory system. And so when these responses come back, we simply add them to the mark queue, and we're now not limited in the number of memory requests that we can send into the memory system. We just basically send whichever many the memory controller lets us. And that means we can now achieve much higher throughput than a CPU through a combination of having fewer accesses per object, pipelining the operation, and not having to take care of ordering of memory requests as they go into the memory system. Of course, there are a lot more implementation details, such as, for example, how to parallelize the reclamation operation, how to keep only a part of the mark queue in on-chip memory and spill the rest into DRAM, how to cache mark bits, and finally, how to integrate all of this into the JVM. And I would like to defer you to our ISCA 2018 paper, which has all of these details to look up. However, there's one additional aspect that I would like to discuss. So far, I've only shown you how to speed up the mark operation itself, which would improve a stop-the-world garbage collector, but does not entirely solve all of our challenges when we have a concurrent garbage collector where the GC runs in parallel to the application. In this case, the garbage collector and the application are modifying the heap at the same time, and the GC can move objects while the application is trying to access them. To address this, runtimes use barriers to handle these cases. So for example, a read barrier would be a bit of code that is executed in every load and checks whether the object has been moved by the garbage collector. Now the challenge is that barriers can introduce significant overheads. There's typically a fast path that quickly checks whether an object has been moved, and if it has, then it traps and branches to slow path code that identifies the new location of the object. This is expensive since this redirection typically requires flushing the CPU's pipeline. To address this, we proposed a new redirection-free hardware mechanism. It adds a special load instruction that always returns the latest location of an object. The way this works is that the CPU uses the TLB to transparently identify whether an object has been moved, and if so, it will look up the new location in the background by sending a memory request to the hardware GC unit. The important idea here is that this operation does not cause any pipeline flushes, and to the application it actually just looks like a cache miss. However, in contrast to the GC unit itself, which you could just integrate into any system on chip, this mechanism actually requires us to modify the CPU. This is challenging, and I will talk more about how to do this in the second part of my talk. So how did we evaluate our approach? It turns out that this is actually quite challenging, because there are very fine-grained interactions between the software and the hardware layers. So for example, in order to evaluate the software stack accurately, we actually need to run the full operating system, a real runtime system, as well as an application on top. At the same time, we need to accurately be able to simulate our new hardware components and their interaction with other parts of the system. We therefore decided to not use a simulator, but implement our design into a real system on chip. We used a rocket chip SoC, which uses the RISC-V ISA, and we built our hardware accelerator into this SoC as an independent IP block. We run a full software stack, including Linux and the GraalVM research JVM. GraalVM has a framework called MMTK, which is a memory management framework that allows us to implement new garbage collection mechanisms. We dropped our garbage collector into the SoC as an independent IP block, which meant that we didn't have to modify any other part of the system, so the CPU and the memory interconnect, they all stay the same. And then we added software support by introducing a new garbage collector to MMTK, which doesn't actually perform garbage collection itself, but instead it calls into a library, which calls into a driver, and then this driver is responsible for communicating with the GC unit over the existing interconnect, set up things like the page table base register so that the CPU and the GC unit have the same view of the virtual address space, and then start garbage collection. We also establish a region in virtual memory that can be used to communicate data between the unit and the CPU without going through the driver. And this is used to, for example, communicate routes to the GC unit. Using this approach, we're able to evaluate our design. And we show that compared to a wimpy RISC-V CPU, we get 4.2x speed up for the mark phase and 1.9x speed up for the sweep phase of a mark and sweep garbage collector. Compared to the same CPU, our unit takes up less than a fifth of the area, which means that our performance per area improvement is over 20x. And finally, we don't just improve performance and area, we also reduce the overall energy consumed for the GC operation by 15%, and this includes DRAM energy. So overall, we show that moving garbage collection into hardware is quite beneficial. So taken together, we have shown that garbage collection can be made much more efficient by moving it into a hardware accelerator. The resulting hardware block is very small, about the size of a 64 kilobyte cache, which is a small fraction of modern SoCs. However, I don't think the potential for hardware-assisted garbage collection stops there. There's still additional overhead, such as the read barriers that I mentioned before. If those are moved into hardware as well, I believe that it should be possible to actually build a system where garbage collection is entirely performed in hardware, and the application doesn't even have to be aware that it exists. From the runtime's perspective, memory would just automatically free up in the background, and we wouldn't have to worry about GC pauses, or implementing GC mechanisms, or scheduling garbage collection threads. There's also significant potential, I think, in reducing the overheads from barriers, as well as their memory footprint. And so with this, I'd like to pause for a second and take some questions before we move into the second part of the talk.
Okay, thank you very much, Martin. So we have already a couple of questions in the Slack channel. So since we have a break in the keynote, let's ask them, probably not all of them, but a couple of them. So the first one is from Christian, who's asking, rather requiring hardware support in the CPU, could we achieve some of the same results with hardware support in memory? So we transfer the support from CPU to memory.
Thanks for the question. So I think you could. I think there's actually been some proposals quite a long time ago about doing something very similar, where you move the hardware accelerator much closer to the memory module. In a sense, this accelerator is actually already doing something relatively similar. It's moving the garbage collector from the CPU to much closer to the memory controller. So you could take this further and move it across the bus to memory. The challenge is if you have multiple DRAM DIMMs and you have a heap that can cross multiple of these DIMMs, then you might need to think about a strategy to distribute that operation. But this accelerator, basically, you could implement it in the DIMM, near the memory controller, somewhere else. Basically, anywhere on the path between the CPU and memory is fine, I think.
Christian is referring to that the DRAM modules, they have a lot of undersea hardware that you could add a very tiny FPGA there, which will speed up enormously the mark phase, and would also be scalable.
That makes a lot of sense.
Yeah. Thank you, Martin. So Christian has another two questions, which I will ask them at the end. So one more question from Jeremy. That the hardware block that you described, could you use it for something else apart from fundamental GC operations? For example, could you use it for graph algorithms?
I think if you extended it, you could. At the moment, most of the functionality of this operation is hard-coded, including the object layout. Now, you could imagine that you might want to make this accelerator a little bit programmable anyways. So for example, if you want to support different kinds of object layouts for different languages, you'd probably want to add at least a little bit of programmability there. And so one thing you could do is that there is this portion in the accelerator that is performing basically the same operation for every object, which at the moment is just marking the object and checking whether it has to copy any references. That could instead be a really tiny microcontroller where you could add any code. And if you did that, you could probably use it for graph operations, at least graph operations where you have to perform one operation per vertex.
Thank you very much, Martin. So we still have additional questions. I will keep them noted, and we can ask them all at the end of the keynote. So I will continue.
Good. All right, let's continue. So I hope I've convinced you at this point that recent trends in hardware mean that hardware support for managed languages is now feasible and can have a major impact on performance and energy. However, this is only part of the story, because for such hardware support to actually get adoption, it needs to be widespread enough that it is worth it for runtime systems to make the investment of adding it into their mainline code. But that's actually only part of it. The interface for this hardware also needs to be standardized so that runtime systems don't have to implement support for, say, 10 different hardware garbage collection mechanisms on different platforms. And this leads me to the second reason for why I think the time may have finally come for hardware support for managed languages. And that reason is RISC-V, a free and open instruction set architecture, or ISA. Why is an ISA so important? In a way, it is the most important interface of a computer because it connects the software to the underlying hardware. Software such as operating systems, compilers, or language runtimes are ported and compiled to a particular ISA, and then they can run on every hardware that implements that ISA. So the challenge is that most ISAs today that have wide-ranging software support are proprietary. This means that while anyone can compile their software for those ISAs, hardware implementations that the software can run on are typically proprietary and are only available from a limited number of vendors. Building new hardware that is not using any one of these major ISAs is therefore difficult because there isn't a lot of software that you could run on it. This is actually a similar problem to other areas, and over the past decades, we've seen an increasing trend towards open standards that address this. For example, websites are written in standards such as HTML or CSS, and any browser can implement these same standards. Network protocols are standardized, and network equipment from many different vendors can implement these standards. And standardized interfaces such as SQL mean that database queries can run on different databases without major changes. RISC-V provides a similar open standards for the instruction set. It is free and open, which means that anyone can use it free of charge, and that it is being developed in the open using a transparent process. RISC-V started at UC Berkeley in 2010 to support computer architecture research within our research group, but has since been seeing an increased industrial adoption since around 2015. It is now being managed by a standard body called RISC-V International, which now has over 700 members. This includes companies such as Google, IBM, NVIDIA, Qualcomm, Samsung, or Western Digital. This standard body is responsible for maintaining the ISA and developing new hardware features. And so over the past 5 years, there has been a growing open source community around RISC-V with a large number of working groups, meetups all over the world, and involvement both from industry and academia. For example, there's now an annual RISC-V summit, and while this year's edition will be virtual, last year's summit in San Jose had over 1,600 attendees, which demonstrates an enormous interest in the ISA. And there's now a growing number of projects and applications of RISC-V, both in industry and in academia. For example, one RISC-V project that we at Google are involved in is the Open Titan project, which introduces an open source root of trust based on RISC-V. So how is RISC-V different than existing ISAs? The difference is that it is free and open, which means that anyone can take it and implement hardware based on it. You can also take it and extend it for your specific project and add features or accelerators that are relevant. RISC-V processors can therefore still be proprietary, and you can buy development boards, for example, with RISC-V cores on them. At the same time, this opens up new models as well, such as you can license cores from third-party designers, or even have open source cores that are developed by the open source community, similar to other open source projects like Linux or MySQL. At the same time, because the RISC-V ISA is maintained by a standard body, software developers can rely on a well-defined ISA that stays consistent over time. This means that over time, RISC-V can grow into an ISA with a wide-ranging software support, which means that future hardware can run a large fraction of available software without additional porting efforts. In addition to hardware implementations, RISC-V also enables an ecosystem of debug tools and additional IPs such as interconnects, since there are no limitations to how people can target RISC-V. One of the features that sets RISC-V apart from other ISAs is that it provides a single ISA to be used in a wide range of different scenarios, ranging from microcontrollers to embedded cores to high-performance servers. The way it achieves this is by being modular. So the base ISA is very small and contains only around 40 instructions. And all other features, such as floating point operations or atomics, are added as standardized extensions. At the same time, there are different variants of the ISA, so there's one for 32-bit, one for 64-bit, and one for 128-bit. And so while a simple microcontroller might only support the 32-bit ISA, a server core could support the 64-bit version with most of the standard extensions, as well as support for supervisor mode. Compilers disambiguate between these different versions of the ISA through a configuration string. So for example, the string shown here would indicate the 64-bit version of the ISA with all of the standard extensions such as floating point, atomics, and multiply divide. While most of the extensions shown here are now frozen, there are several official task groups that are working on new extensions to further expand the ISA. These task groups are working under the umbrella of RISC-V International and are bringing together experts from industry and academia. Some of the extensions that are currently being worked on include vector support and support for bit manipulation instructions. The extension that I would like to talk about, however, is the J extension, which is responsible for adding managed runtime support to RISC-V, and which I'm chairing. The group started in 2018, and its charter is to work on RISC-V extensions to better support managed languages, which includes features such as hardware support for JIT compilers, garbage collectors, or dynamic typing. We have a large number of fantastic contributors from industry and academia, and it is truly a group effort, with different parts of the extension being led by different members. So I believe that RISC-V, for the first time, provides an opportunity to standardize a wide range of hardware features for managed runtimes and get widespread adoptions for them in real hardware. In the J extension group, we're specifically looking at a number of topics at the moment. For example, we are looking at instruction and data stream synchronization. In a multi-core system, when a JIT compiler on one core generates code, it isn't immediately visible to the instruction stream on the other cores in the system. So to ensure that all cores see the latest version of the code, we therefore need a new synchronization mechanism that makes the code visible and makes sure that every core has a consistent view of that code. So this is a mechanism that is crucial for running JIT compiler on multi-core RISC-V systems. There's also potential to work on read and write barrier mechanisms for garbage collection, such as the ones I talked about earlier. In our ISCA paper, we proposed the read barrier mechanisms, but we didn't actually implement or evaluate it. So there's a lot more work to be done here as well. There are also other areas that language runtimes can benefit from, such as hardware support for array bounds checking or object zeroing. And finally, there are a range of hardware features that can be beneficial for language runtimes more broadly, such as memory tagging or pointer compression. One of our focus areas at the moment is memory tagging, so I want to tell you a little bit about that and what we're working on in this area. In particular, I want to tell you about a proposal that we're working on that will add pointer masking to RISC-V. So what is pointer masking? The idea is that you want to change the behavior of every load and store instruction in your code to ignore a certain part of the address. So for example, imagine you have a processor, in this case a simple 5-stage pipeline, which is accessing memory via load and store instructions. With pointer masking, you specify a mask in the base, and when you enable it, the mask will be applied to every address that goes into the memory system, and the base is added to it. You configure this mechanism using a set of control registers where you can set a mask for each privilege level and switch the mechanism on and off. By default, you can only change the mask of lower privilege levels, but you can configure the mechanism to let privilege levels set their own masks, which is important for some use cases. So what is this mechanism useful for? It turns out there is actually a fairly wide range of things. One example is sandboxing in runtime such as V8 or WebAssembly, where you can use the mechanism to save the extra instructions that you would need to transform an offset within a sandbox to the actual address. The mechanisms can also be used for pointer compression, using a similar approach. In addition, there are a range of different scenarios where you want to store tags within addresses, such as tags for GC barriers or dynamic checkers, such as hardware-assisted ASAN for C++. We also think that the mechanism could enable new research ideas, and we are very curious what ideas people are going to come up with. We have a draft spec of the proposal on GitHub and are currently working on software support and moving this proposal towards ratification and turning it into a fully frozen RISC-V extension. In addition to pointer masking, we have a number of different extensions in the pipeline, such as the instruction data synchronization mechanism that I mentioned before, and several other directions. We are quite excited about this, and we always welcome new ideas and contributions. This brings me to the end of the second part of my talk, and once again I'd like to pause for a brief moment and take some questions.
Thank you very much, Martin. So if you have questions regarding the second part of the presentation, please feel free to ask in Slack. Of course, we have pending questions, which we're going to circle back to them at the end. I would like to ask one question, Martin. So you mentioned the word ratification. So as soon as in the RISC-V extension group, you do some work, then what is the ratification process entails? Is it voted, or how it works?
So this is basically something that happens within the RISC-V community, and there are different steps that we need to work through in order to until basically an extension gets frozen, and involves things like, for example, that there is an implementation of the approach, there is the final spec that doesn't change anymore, and then eventually there's also a comment period. I think there is some documentation on GitHub that explains it a little bit more in detail. But yeah, there are many steps in order to basically tick all the checkboxes until an extension can actually become part of the full ISA.
Thank you very much. So another question from Jeremy, it is, if you see an overlap or commonalities between the CHERI initiative from University of Cambridge in relation to the RISC-V J working group, particularly for pointer tagging and offsetting?
Oh yeah, absolutely. So there are several applications of memory tagging for managed languages, and the CHERI tagging mechanism, I think, has been shown that it can be used for some of these managed runtimes use cases. The pointer masking proposal that we have is, I think, a lot more specific and requires a lot fewer changes to the processor, because it is really just applying this mask. But of course, it doesn't allow you to have fully fledged memory tags in the way that CHERI does.
Thank you. And one last question in this part from Christian. He's saying that AMD claims to have used machine learning to optimize the batch predictors on their Zen architecture, and he believes that this is just another small reconfigurable circuit. So he's asking if we can build a more open version of this reconfigurable circuit in RISC-V. So it's open to the programmers that can influence batch prediction, class behavior, and custom instruction decoding. So would it be possible, I mean, probably both from a technical perspective and also from an impact perspective, like if those can be actually pushed through the foundation?
Interesting. Yeah, so there is, so neural branch predictors have quite a long research history. And one thing that already exists today in the RISC-V ecosystem is a fairly wide range of configurable hardware. I'll talk a little bit more about that in this third part of the talk. But for example, there is the Boom out of order, like the Berkeley out of order machine, which is an open source out of order superscalar processor. And that design can be configured in many different ways. And so including components like the branch predictor. And I think it should be definitely possible to add new components to this kind of design, be it a neural branch predictor or yeah, other hardware units. I think this is a very fruitful area, actually.
Thank you, Martin. So, and one last question from Stefan regarding like a statement in this part of the presentation. So Stefan is asking, what is long term in the context of the slides here? So, what is your time frame for that?
That's a very good question. I think it varies a lot. So many parts of the RISC-V ecosystem are moving very, very quickly right now. So for example, as I'll talk about in the third part of my talk, the software ecosystem is coming up fairly quickly. For more complex extensions, I think there's a certain higher bar to prove that they're universally applicable. And so the time horizon there is probably more like multiple years, but it's still, I think, within the kind of range that makes sense as a project. So it's not like, oh, in 20 years we're going to have this. I think it's much shorter than that. But it's probably we're talking about years for a modestly complex extension.
Thank you very much. So we have plenty of questions for you to answer later. So just unpause for now, and then we're going to circle back.
At this point, I've hopefully convinced you that there is both ample opportunity for improving managed languages with hardware support, and that RISC-V is a unique opportunity to standardize these insights and get them adopted. But what does this mean for academic research in this area? So in the last part of the talk, I want to tell you why I believe that these trends enable fundamentally new approaches to research on hardware support for managed languages, and why I believe that we are about to enter a golden age for research in this area. It goes without saying that hardware support for managed languages is not a new idea, and that plenty of work has been done in the past. However, most existing work shared a number of limitations, many of them related to methodology. In the past, academic research on computer architecture typically had to rely on simulators, which is a challenge when used with managed language runtime systems. managed runtimes typically require a full software stack, run in parallel across a large number of cores, and need to run for a long time. This means that they pose a challenge for cycle-accurate simulators such as DREM5, which provides accurate simulation results, but are typically too slow for long-running multi-core applications that require a full software stack. An alternative would be to use functional simulators such as QEMU, which are fast enough to run a full software stack. However, they do not typically capture fine-grained details in the hardware. And this is a problem for work on hardware support for managed languages, since this work typically focuses on very fine-grained interactions at the hardware level, such as the read barriers that I talked about. And so therefore, neither the functional nor the cycle-accurate simulation approach works particularly well for this kind of work. In addition, having to run a full software stack introduces additional challenges when doing this kind of research. Even when a suitable cycle-accurate simulator is available, it's often challenging to get a full software stack to run within a simulated environment. And finally, while research on managed runtimes is often transitioned back into upstream code bases, this is much more difficult for hardware changes. And so I would argue that RISC-V helps us with all of these problems. Instead of implementing research ideas directly inside a simulator, it is now possible to actually take real open source RISC-V hardware implementations, implement the changes in real hardware, and evaluate this hardware by running on FPGA boards. Since the hardware is running on FPGA speeds, perhaps something like 100 MHz, this setup can now run the real full software stack and give much more realistic and fine-grained results. At the same time, this approach makes it possible to contribute changes back to the open source community and get them adopted. Implementing ideas into an open source hardware design means that people can directly use the research prototype, and working with the RISC-V community could enable standardization and adoption of the best features in the official RISC-V standard. This leads to an approach that is much more similar to how open source JVMs are used in academic managed runtime research, or how Linux is used in academic OS research. To give you an example of what is possible, here's what we did at UC Berkeley for the garbage collection accelerator that I mentioned in the first part of the talk. We built on a framework called the Rocketship SoC generator. Rocketship is a highly parameterizable generator for system-on-chip designs that allows you to configure and instantiate a wide range of cores, interconnects, and accelerators. One thing that's nice about it is that it's written in a new hardware description language called Chisel, which can be much more productive than developing RTL and Verilog. Rocketship can target FPGA and VLSI flows and has been taped out many times. As a result, while Rocketship has been used in real chips, academic researchers can take the same RTL and run it in FPGA-based simulation. For this paper, we ran it on top of an FPGA simulation framework called FireSim, which takes the full RTL and simulates the cycle-accurate performance that you would see from an actual ASIC. This approach therefore allowed us to get a detailed approximation of how a real chip would perform using the exact same code base that a real chip would use. Of course, as I mentioned before, we also need to run a full software stack, and so one of the things that I worked on when I was at Berkeley was to bring up a full Linux distribution on RISC-V, which meant that we were able to run scripting languages like Python on RISC-V. I then ported the GraalVM research VM, which is what we then used for our evaluation. I want to point out that this didn't have the optimized JIT compiler yet, so there is still some more work left to do in this area in case someone is interested in continuing this work. This setup allowed us to run the complete software stack, running the Da Capo benchmarks in GraalVM on top of Linux, on top of a full RISC-V based system, on top of an FPGA at over 100 MHz for billions of cycles. Since the paper, the hardware and software ecosystem around RISC-V has expanded further, and there's now a large range of suitable infrastructure for managed language research. So for example, on the hardware side, there are now several other hardware platforms besides Rocketship, including LowRISC, Pulp, and OpenPython. Some of these projects have multiple choices for CPUs. For example, Rocketship supports both an in-order implementation called Rocket, as well as an out-of-order implementation called Boom. There's also been a lot of recent progress on the software side. For example, there's now a RISC-V port of the Maxine VM that was done at the University of Manchester, and a port of OpenJ9 is in progress. Overall, 90% of Debian packages are currently available for RISC-V, which means that a large portion of important software can already run on RISC-V today. As a result, it's possible to take an off-the-shelf RISC-V system and use it in research on hardware support for managed languages. This approach is particularly useful for research problems that have very fine-grained interactions, such as anything involving the memory system, speculative execution, or GC barriers. One thing that I want to mention is that while it is possible to take an existing RISC-V implementation and run it on an FPGA, this approach may not be enough for a full evaluation. The reason is that an FPGA behaves differently than the actual chip would, For example, the FPGA speed is usually much lower relative to the memory system than it would be for an ASIC. To address this problem, a design can be combined with infrastructure that enables FPGA-based simulation. Fortunately, this infrastructure exists for RISC-V. For example, the FireSim framework that I mentioned before combines the hardware design with additional logic that adjusts the timing within the circuit to simulate the performance of an actual chip while running an FPGA speed. Taken together, I would argue that the RISC-V ecosystem has enough available infrastructure to enable realistic research on hardware support for managed languages in an academic setting. And I think this is a tremendously exciting opportunity because it makes it possible to revisit problems in this space that haven't been investigated in a long time since the infrastructure wasn't available. So what kind of topics might be interesting to work on? I think there is a wide range of areas, and some of them I have already talked about in this presentation. For example, I think there is a lot more work to be done on hardware support for garbage collection, and I also think that we are only scratching the surface of what can be done with pointer masking and memory tagging. In addition, however, I would like to highlight a couple of additional research areas where there hasn't been a lot of work in the past and where I think there could be quite a lot of impact by applying hardware support. One such area has to do with speculative execution. Managed runtimes use speculative execution in many different places, such as barriers or trace-based compilation. The typical approach is to generate very fast code for the common case that is speculatively executed, and if the speculation turned out to be incorrect, the VM branches to slow path code that recovers from this misprediction. This slow path code is typically very expensive, and speculation therefore only makes sense if the fast path is much more common than the slow path. However, the proposed read barrier in our Part4GC paper shows an example of how hardware support can be used to make the slow path much cheaper by performing the correctness check and recovery in hardware, but allowing the CPU to continue executing in the meantime. I think this approach generalizes beyond garbage collection and could allow the use of speculative execution in areas that are currently too expensive. Another area that I think could be interesting is support for more fine-grained profiling. JIT compilers and managed runtimes rely on profiling information to make decisions, but some profiles are extremely expensive to collect. So for example, detailed hotness profiles or fine-grained execution traces are expensive to collect in software, which means that JIT compilers typically have to rely on coarse-grained, cheap-to-collect approximations of this information. I think an interesting research area would be to ask whether hardware support could help collect more fine-grained profile information that could then allow the JIT compiler to make better decisions or enables other optimizations. And finally, one of the advantages of managed languages is that they can dynamically recompile code at runtime. This means that they could dynamically recompile code for specialized architectures transparent to the application. So given RISC-V's unique customizability, I wonder whether there would be scope for building RISC-V cores that are specialized for certain operations in managed runtimes and can be transparently targeted by the JIT compiler. Some prior work on JVMs for heterogeneous architectures go a little bit in this direction, but I think there is some great opportunity here for hardware-software co-design between these cores and the runtime system. In each of these cases, RISC-V could be leveraged for this work by prototyping ideas in open source RISC-V hardware and evaluating them using the real software stack. If successful, partnering with RISC-V task groups or industrial collaborations could then provide a pathway to standardizing the approach and making it part of the official RISC-V standard. So this brings me to the end of my talk. During the course of this presentation, I've hopefully convinced you that hardware support for managed languages has a large potential for impact, and that there now exists infrastructure that makes this kind of hardware research feasible and opens up a wide range of new opportunities for research in this field. I also hope that I've convinced you that RISC-V provides a new pathway towards real-world adoption of this kind of research that didn't exist before. Taken together, I believe that these three factors create a fundamental change that make this the perfect time to work on research in this area. And so maybe the time has finally come for hardware support for managed languages, but it is up to all of us as the research community to make it happen. And with this, I'd like to wrap up. Thank you all for listening, and I look forward to taking questions.
Thank you very much, Martin. That was a very interesting presentation. So I would like to start with some pending questions we have in our Slack from the first part. I will go back to the beginning to the question from Christian. Christian asked 3 questions, so we just relate the first one. So the second one, it is, if we add an additional IP core then you have the benefit of not polluting the cache for client code. And the question is, could you get some slice of the performance gain in software GC by paging out the cache before the GC freeze and paging in after?
So I think there are certain operations, certain optimizations that we can do in software to improve GC. I think the ones mentioned in the question are among them. There are some things we can only do in hardware. So for example, this optimization of keeping a much larger number of memory requests in flight is something that, that to my knowledge, you can't really do in a software core. And this is actually one of the aspects that allows us to get much higher bandwidth out of this unit. Another aspect of where this unit has an advantage is that it cuts out a lot of components that a CPU just needs to execute code, but that we don't need in the unit. Caches or functional units like floating point units are an example of that. And so the result is that from the system's perspective, this GC unit looks almost like a separate core in the system. It's just, it can only perform this one operation, but it is much, much smaller and can achieve higher throughput than a CPU could at that operation. So I think in principle, instead of having this IP block, you could take the IP block out, you could put a CPU in, and it would work. But I think there are optimizations that we can do in hardware that you couldn't do on a CPU core.
Thank you, Martin. And then Christian, follow up with a question that relates first to your first argument of why how support didn't make it, let's say, yet, or at least some of the efforts, like the Azul Vega systems, they were discontinued. So the question is, if it would be fair to say that a more plausible reason for the lack of our support for managed language would be the cost. So the cost of fabricating a chip, which is really hard for a small to medium company.
So I think this goes back to a little bit of why I think 20 years ago was a very difficult time, or I guess, yeah, like the early 2000s, I think, were a difficult time to do this kind of work, because it was a time when really CPUs were progressing extremely quickly. And so even if you got some fantastic advantages from hardware support, you basically had to keep up with the advances in process technology as well. So I think that is one aspect that's different today. I think another aspect that's different today is that the way SoCs, for example, are built. Most mobile phones have SoCs, for example, that are assembled from different IP blocks. So it's a much lower lower risk to drop an additional IP block into a modular SoC than building an entire chip that's single purpose and has major changes. So I think there are just all these little changes that have happened over the last 20 years or so that I think make today a good time for this, even if it may not have been 20 years ago. Having said that, it's a hypothesis. I don't exactly, to my knowledge, there are no major systems right now that really have widespread adoptions that have hardware support for managed languages. And so, as I said, I think it's up to the research community to figure out, is this something that can happen today?
Thank you, Martin. So the next question is from Thanos. Again, regarding the first part where you described your optimizations you did in Berkeley, if you consider near data processing or in-memory processing for accelerating garbage collections.
Yeah, I think that goes back to a little bit to Christian's question as well. I think it is feasible. To me, the biggest challenge is that your heap is going to have pointers across different memory DIMMs, very likely, and communicating. That means that you now have communication between different DIMMs, and that can be challenging. So, to me, it seems like a good place for the garbage collector is similar to where the memory controller is, because that a component close to the memory controller can bypass a lot of the interconnect on the chip, while at the same time being able to send memory requests to all DIMMs in the system. Having said that, I could totally imagine that that there would be a way to build something directly into the DIMM and have the DIMMs communicate somehow, or have some kind of multi-phase approach. So I could imagine that being a feasible design. And if you can get it closer to the DIMM, it does avoid the bottleneck of having to go over the memory bus. Having said that, we found that because it's a graph traversal, I don't actually think the memory bus is oftentimes the limit. I think it's really the keeping the memory request in flight and doing this pointer chasing. So that's something that will need to be benchmarked to determine where should the unit be placed.
Thank you very much. Stuart is asking, how does the DC unit scales versus, let's say, dozens of cores ability to generate garbage?
That's a very good question. So it's a similar problem as determining on CPUs how many cores you should put aside for garbage collection. The main advantage of the unit is that it achieves much higher bandwidth for the tracing than a CPU, but it's still a tracing operation. And in tracing garbage collector, the challenge, of course, is you can create a lot of garbage very quickly. On the other hand, it is really the life graph that you need to traverse that determines primarily what your tracing time is going to be. And so we don't give any like guarantees. Like I remember there was, for example, this paper by David Bacon a few years back where they had a FPGA-based garbage collector that actually gave you guarantees about being able to catch up with the CPU creating garbage. This proposal doesn't provide any guarantee like that. It's really similar to a CPU where you need to balance the system and where you could still potentially have pathological cases where it's difficult to catch up. I do think given the bandwidth that you can achieve, you can probably provision the GC unit aggressively enough that it would be very difficult for at least a small number of CPU cores to generate enough garbage to saturate the unit. And one thing that you can also do is you can dynamically balance the unit and the CPU. So when you have a limited amount of memory bandwidth and you need to decide how do you split it between the GC unit and between the CPU. And so if you find that your GC unit is running behind, you can assign a larger fraction of the memory bandwidth to the GC unit and say, okay, let's actually get the garbage collection out of the way so that the CPU can continue executing. And so if you balance it like that, I suspect you should be able to keep the two in sync somehow.
And probably also this balancing could be part of the use case, like if you do a UI application to guarantee the fluidity, like giving more to GC if it has to do GC versus another server application where you do some data warehousing. So moving on, Thanos is asking about the chisel and RTL interaction. So when you go from the chisel to RTL, has it been efficient in terms of footprint and time requirements? And also, what was the target frequency for the FPGA IP?
So we've been when I was at Berkeley, we've been using Chisel a lot, and found it generally very practical. Like basically, it generates Verilog, and so then you use the same design tools that you would use if you wrote Verilog directly. And so I think that the efficiency wasn't really a challenge. Like in both languages, there are patterns that you can write that are less efficient than others. So you need to figure out how do you actually get the critical paths into your limit, etc. But I don't think we had any problems with that back at Berkeley. And to the question of what frequency we're targeting, I don't remember exactly, but I think it was 100-ish megahertz of FPGA speed.
So, I mean, you mentioned in your presentation the challenge of using the 2MU and the Gen 5, let's say, software stack, which I mean, we have used it in our group, and it is slow and it takes a lot of time to do some research if you have to run for days to get a result. So, how does it compare, let's say, to run the same simulation on the Gen 5 stack versus the FireSim, at least for the specific core?
So do you mean about the
yeah, the performance? Like, is it like a much faster, or it's just, let's say, a little bit faster?
So I don't know the latest number. I also know that they continued developing FireSim quite a bit in recent years at Berkeley. It is a bit slower, but I don't think it was slower to an extent that it would have prevented us to do the evaluation that we needed to do. I think one thing to keep in mind is that if you for a research experiment, if you want to simulate, like, say, a minute of an application running, and it takes you a few hours, that is perfectly fine. But it is still much faster than, say, a cycle-accurate software simulator would be, where oftentimes you're really limited in by executing, like, oftentimes less than a second, which is not enough for managed runtime, unfortunately, to capture all the different program phases.
Thank you very much. So Juan is asking, you have mentioned already some, in your opinion, directions for research regarding virtual machines for acceleration. So Juan is asking, what are the challenges for accelerating other parts of the VMs, for example, bytecode interpretation or bytecode verification?
That's a very good question. So one way we look at this in the J extension is that there are different kind of target systems. And so something like a garbage collector, for example, can help any system that uses garbage collection. But then other proposals only help specific scenarios. So say, for example, you have something that improves an interpreter. That can potentially be really useful for embedded systems that are running, say, Python code or interpreted Java code or some other interpreted language, Lua maybe. But it might be less helpful for a system where anything is JIT compiled anyways. And so I think it is very important to be very careful about which scenario a particular proposal is targeting, because things that make a lot of sense in embedded might be less impactful for, like, large servers and vice versa.
Thank you. So Jeremy is asking whether you're presuming to support only non-moving collectors, or you also do accelerate the memory copy also.
That's a very good question. So the prototype that we had was non-moving collectors, but part of the reason for separating this design into a traversal and a reclamation unit is that this reclamation unit could eventually also become compacting, for example. If one goes down that path, it means figuring out read and write barriers and how they would interact with the traversal unit as well. I think we hint a little bit at that in both this paper, and I think it's also mentioned we had a workshop paper before that, but we certainly didn't build it out. I don't think it's a fundamental limitation. I think it just requires basically being careful about read barriers particularly.
Thank you very much, Martin. I think we have, if I'm not mistaken, we have covered all the questions related to the talk. There are some other questions for the Ask Me Anything a little bit after. So I would like to ask our attendees if you have any further questions related to the talk. Of course, you can raise your hand in Zoom, or you can ask them in Slack. And we'll transition now from the keynote to actually more generic questions we can all discuss here. So I would like to relay a question from Stefan, because you mentioned speculative execution, and this is a scary word for us nowadays. So Stefan says, whenever I hear this phrase, I always think of speculative meltdown. And he's wondering whether we as a community of the managed programming languages, first, if we have any idea how we should, or methodology, I assume, to keep pushing speculation boundaries without breaking or creating any vulnerabilities. And also how, this is my question, my follow-up question, or comment, if it's time for us to factor in also the security concerns, or at least the security, the safety of our optimizations when we propose high performance optimizations.
This is a fantastic question, and I think this is exactly right. This kind of speculative execution is a major side channel, and I don't have evidence, but my hypothesis is that managed runtimes have more of these sort of side channels than a lot of other applications. It's actually somewhat of a connection to work I did early in my PhD on memory trace obliviousness. So there we were looking at what information is leaked through memory accesses in an application, and which is also a very rich side channel. We had this paper called Ghostwriter, which was about how to eliminate these side channels in the compiler. And the idea there is, I think, one that's applicable here as well. So the idea in Ghostwriter was you basically figure out what are the paths that you can take through the program, and which of these paths depend on secret information. And then you have basically, through a type system, you figure out how do you need to pad all these different paths that the observable signals look the same, whichever value of your secrets you had. And so I think this kind of work actually could be really impactful in the context of managed languages, because managed languages have JIT compilers. Managed languages already have a notion of trace-based compilation, and so it should be possible, I think, in the JIT compiler to basically like see, okay, how can we make sure that knowing what our secret values are that we don't want to leak, how do we need to pad all these different executions? It's also something where hardware support might help as well. There have been so part of that Ghostwriter paper was actually some hardware support to make it easier to make these executions predictable, so that your compiler can then target them.
Yeah, that was going to be also my follow-up question. So at least for the context of the J working group in RISC-V, is there any intersection between the security group and the J working group to make like strengthen the security of the proposed solutions?
Yeah, we talked to them, and RISC-V has a security standing committee that is responsible for thinking about these questions, yeah, we talked to them.
Thank you very much. Any more questions regarding the presentation, or open questions for Martin? I do not see any raised hands on Zoom, or any questions in Slack. If I skipped any questions, please let me know. So Martin, once more, thank you very much for your time and for your very interesting keynote and your take regarding hardware acceleration. There are a couple of people that are typing on Slack, so I'm just waiting to see any other different question. Juan is asking if there's any similar to RISC-V, let's say at least this concept for GPUs, or if I rephrase, if the RISC-V foundation also works on GPU style of the same community building process.
That's a good question. I just typed this into Google. Some results come up. So yeah, that's the best answer I can give right now. But one thing actually I can say is there is a vector extension under active development for RISC-V, and that vector extension is a general interface for vector-like computation. And so I think the question about is there a GPU and is there like a vector interface is very related, and I think the vector spec is probably the best starting point for finding what's available. This is actually an area where there's a lot of activity right now, because of course GPUs have many applications.
Yeah. So the vector, but for example, it could be possible to actually get the IP, RISC-V IP, and then if you have your own GPU design, then bundle them together, right? I mean, it should be possible if you are a GPU designer to actually plug in a custom design of the GPU, assuming you have the toolchain ready for in a RISC-V, let's say, board.
Oh yes, with RISC-V, one of the advantages is that well, of course, the ISA is standardized, and if you want to target standard software, then it has to be the standard ISA. you can always just take a design and add to it. It will just not be standardized by default.
Oh, that's a good question from Stefan. If you would have 10 PhD students / engineers, I like the fact that you put / engineers. What would be the research that you would focus on as a high risk, no questions asked project?
Oh, that's a good question.
Yeah.
It's the kind of question where I'm probably able to give a better answer in like after thinking about it for a little bit. But I think the things I mentioned towards the end, I think are really interesting areas. Like can you build a so one of the big problems with or not problems, but one of the challenges with JVMs today is that they still have jitter. Like for example, they still have GC pause, even if you have a concurrent GC, they still have like they might stall for compilation, etc. And if we can use that kind of hardware support, like the speculative execution support, to build a JVM that is just never stops, never has anything worse than like a cache miss, for example, and where you can basically factor out a lot of the complicated parts, like for example, scheduling the garbage collector, I think that would be a pretty exciting existence proof to build that, and then figure out how can you actually make this a standard feature, because this would allow you to use managed runtimes in a lot of areas where you currently don't use it because of overheads or because of pauses and things like that. So I think that would be an exciting direction. I actually think the Spectre meltdown direction that we talked about earlier is also really interesting, because that is a very interesting challenge. And I think there is actually things that you can do in the language runtime system that you might not be able to do in other scenarios as well.
Thank you very much, Martin. So Christian is asking whether there is something like a runtime optimizer IP core, for example, to manipulate the instruction cast based on runtime that updates, and maybe doing dead branch elimination. If I'm not mistaken, I think the one I knew was the Transmeta CPUs, where they were doing bundle translation during runtime, and they could do something similar for dead branch elimination. But don't quote me that. I think I have read in a patent somewhere.
I'm not completely sure I understand the question. So is the question about like adjusting your code on the fly, or okay, interesting. I don't know of work in that area, but it is the kind of thing that where like the RISC-V platform is a nice environment to evaluate it, because you can modify the instruction cache, you can modify the decode stage of your pipeline. So I think this is the kind of area where RISC-V is a pretty good fit.
Thank you very much, Martin. Any more questions? So we are approaching the end of the or Ask Me Anything session. Of course, we have a provision another let's say 15 minutes to our virtual hallway, which is in Slack. So if everybody has more questions, they can transition there, and I can open a new Zoom channel in Slack, and we keep discussing. So I would like Martin to thank you one more time for giving us this the keynote, and I would like to make some closing remarks for MPLR as a whole. It has been a long day, and I would like to thank everybody that has been attending and participating and presenting, of course. And one more time, I would like to thank our sponsors and our program committee and local organization committee, and of course, Steve and Martin for the keynote. I would like to give one update regarding the mirror. replay. So after we finish this live session, we will do some minor editing, and then we're gonna replay all the videos from all the presentations. Fortunately, we don't have the time to edit the questions and the answers inside, because it will take more time than the actual buffer time we have to start the mirroring. So from 8 o'clock UK time, we will start replaying just the presentations without any questions. And in the next couple of days, we will release on the YouTube a new edited video with everything, all the presentations, plus the questions and the discussions we had with our speakers inside the same video. So this channel will be closed temporarily, and then it will be reopened for the mirror session. And then I'm guessing that Stefan or myself will follow up with an email with a new link to the YouTube video, so you can all rewatch the presentations in your own time. So on my behalf, I would like to thank everybody for joining MPLR. It's sad that we didn't manage to see each other in person, but hopefully next year we can repeat MPLR and meet up. Nevertheless, it was great even to have this visual conference. And Stefan, would you like to say a couple of closing words as the program chair, of course?
Yeah, I just want to thank all the speakers, so of course all our keynotes, but also all the authors of papers. I want to thank the program committee once more, the sponsors, and of course you guys organizing the practical side of things. So thank you very much. So far it was a nice conference, given the situation we are in. So yeah, that's pretty much it. Thanks everybody.
Thank you, thank you. Have a nice day, and we will of course send you updates with the YouTube version of the videos, which will be full edited. So I have to close this session for editing the videos, starting the mirror session. So please continue discussions on our visual hallway. Thank you very much, and have a nice day or night, wherever time zone you are.